Sir, good morning.
Good morning. Good morning to all of you. I
Sir,
hope.
we'll start. Yes, sir. Yes, sir. We'll start by within 2 minutes
Okay, no
because
issue.
this is a morning session, so people are still joining.
Yeah, sure.
Good morning to Dr. Ashutosh also.
Yeah, good morning. Good morning, sir. Good morning, Mahesh.
Good morning. Yeah, already 57 people joined. I can see 60. Yeah,
Yes.
very good number. So, how many
Yeah.
total registrant, Mahesh?
Sir, it's around 120.
Oh, okay. Huge number.
Yes.
See, this
Yes,
is
sir.
the
Yes, sir.
advantage of online. I think
Yes,
Right,
sir.
sir.
because offline, if it would have been, you probably could have accommodated probably maximum 50 or so, right?
Right, sir. Right, sir. And probably also because of your lecture, the number will increase.
No, that I don't know.
But that we know. Because otherwise, the idea was to start with your lecture yesterday. So, but it's okay. You were so
No,
very
I am
much
really
busy.
sorry. Yesterday, suddenly an important meeting came. Even after
Yes,
this,
sir. Yes.
also this IS code 2911 meeting is there actually today.
Yes, sir. Yes, sir.
So
I
from
fully
here, I will
understand and
join there.
right. And thank you very much because we all understand that how much busy you are now. So for
No,
taking out
everyone
time
is
for
busy in their own respective field, but still we want to accommodate as many as possible. And now because of this online, I think events, etc., has increased many folds because
Yeah.
yes,
True.
people are jumping from one event to another event very easily.
yes, sir, absolutely. Sir, I think we can wait 1 minute more because 75 are there now. So
Yeah.
maybe, yes.
Fine. Whatever you suggest.
Sir, I think we can start now. It's already 5 minutes we are late. Dipankar sir, can you hear me?
Yeah.
Yeah.
So, can I share the screen?
Yeah, you can share the screen, and then I have to give a brief introduction, which is one of the privileges I'm having right now. Yeah, you please share your screen. I think, sir, you are muted. So, yeah.
Is it visible now?
Yes, sir, it's fully visible. And so, good morning to all the participants from, who are joining us throughout the country. And also, I think there are 3 or 4 participants who have joined us also from US and Italy. So, a very warm good morning to everyone. I welcome you all to the second day of this faculty development program on disaster resilient infrastructure. So today we have with us Professor Dipankar Chaudhary, a renowned professor known for his research in the area of geotechnical earthquake engineering throughout the world. So, sir, thank you very much, and a warm good morning to you also for giving this time in the first phase of the Tuesday morning to us. So, I would like to start this session with a brief introduction about Professor Dipankar Chaudhary. Professor Dipankar Chaudhary is Professor Tarun Kant Chair, Professor and Head of Department of Civil Engineering, IIT Bombay. He has stood always first class, first rank holder and gold medalist throughout his academics. Did his BTech from prestigious university, Jadavpur University, Kolkata, and then master's with gold medal in civil engineering from IIC Bangalore, and then PhD also from IIC Bangalore. Professor Chaudhary has also worked as faculty IIT Kanpur and mentored new IITs at Gandhinagar and Dharwad, both on deputation from IIT Bombay. And he's also served as visiting faculty to National University of Singapore, University of Wollongong, Australia, University of California, Berkeley, TU, I'm sorry if I'm not pronouncing it right, but TU Darmstadt, Germany, etc. He was also associated with CSIR and as an adjunct faculty, as a professor of academy and of scientific and innovative research of CSIR laboratories connected to CSIR CBRI Roorkee. Professor Chaudhary is the only geotechnical engineer of India who is also an elected fellow of oldest society, Science Academy of India, that is the National Academy of Sciences, India. Internationally, he is elected fellow of American Society of Civil Engineers, USA, Alexander von Humboldt Fellowship, very prestigious fellowship, GSPS Fellow of Japan, TWAS Fellow of the World Academy of Sciences, Italy, in addition to National Fellow of Institution of Engineers, India, Indian Geotechnical Society, Indian Society of Earthquake Technology. Professor Chaudhary, a recipient of Professor C.S. Desai Medal of International Association for Computer Methods and Analysis in Geomechanics, ICMAC, which in short we call it, USA in the year 2017, also received Excellent Regional Contributions Award of ICMAC in 2014, and Excellent Paper Award of ICMAC in 2008 for ASC International Journal of Geomechanics paper. He received several Young Scientist Engineer Awards from various academic societies of India like INSA, NASI, ISCA, INAE, IEI, DST, DAE, ISTE, and from abroad like APASCM, SP Research Foundation, ICMAC. He is an associate editor of ASC International Journal of Geomechanics, Indian Geotechnical Journal, Journal of Civil Engineering of Institution of Engineers, and was founding associate editor of INA Letters. He has served as editorial board member for Canadian Geotechnical Journal, currently EBM for Geotechnical and Geological Engineering, Geomechanics and Engineering by Tilley and Francis. Professor Chaudhary's major research areas are civil geotechnical earthquake engineering, computational geomechanics, sustainable foundation engineering, soil dynamics. The newly developed pseudodynamic method, which is very much popular now throughout the world, has been proposed by Professor Chaudhary's research group for earthquake-resistant design of geotechnical structures, which are highly popular across throughout the world, as I already mentioned. Professor Chaudhary's video lectures that we all, I also always try to go through it, are also very much popular for all the academicians, researchers, among all the academicians, researchers throughout the world. Professor Chaudhary received Professor S.P. Sukhatme Excellence in Teaching Award 2017 of IIT Bombay. Also, his outstanding research work have been recognized by IIT Bombay through various research awards of IIT Bombay. Professor Chaudhary has already supervised 27 doctoral theses and many more are continuing. Many of his students, I think not many, I think almost all, student theses, PhD theses especially, have received Best PhD Thesis Awards of IIT Bombay, IGS, INAE, ICMAC. His former PhD students are, majority of them are faculties in IITs presently, and few are doing postdocs from prestigious universities in the world. He has co-authored textbooks on foundation systems for high-rise structures. Besides authoring around 300 technical publications, which includes 160 keynote invited lectures at various reputed conferences all over the world. He is the current secretary of Technical Committee TC207, that is Soil Structure Interactions and Retaining Walls, of International Society of Soil Mechanics and Geotechnical Engineering. In short, we call it ISSMGE. And he was also the former secretary of TC212, that is D Foundations of ISSMGE. In addition to the present and former member of TC203 and editorial board of ISSMGE Bulletin, Professor Chaudhary executed several national and international projects of importance in India, Iraq, Mozambique, Vietnam, in the domain of his research expertise. Currently, he was involved in several mega and prestigious national projects of India. Professor Chaudhary was the organizing vice chairman of IIT JE Advanced 2015 and was founding member of first ever joint seat allocation JOSA, what we call in short, Committee for IITs, NITs, IIITs, CFTIs together in 2015. As one of the members of International Committee through MHRD at IIT Bombay, he was actively involved in starting IIT JE Advanced 2017, GATE 201 International. He was organizing chairperson for All India GATE 2021, zonal chair of 2020, and JAM 2020. He acted as external expert member of MHRD review of IIT Patna, expert member for NB accreditation, and Professor Chaudhary is in academic council, board studies members for various IITs and other prestigious institutes of the country, such as IITs, NITs, DRDO, ERB, and other organizations. He is an advisor of Department of Engineering of IIT Kanpur also, a member of board of studies of several IITs, NITs, and institutions of repute, and a member of Bureau of Indian Standards. So it's a brief CV of him. I'm very proud to be his student also. So it's my privilege to welcome Professor Dipankar Chaudhary, my guru, for this workshop. And I again welcome him and thank you very much, sir, for taking out time for your busy schedule. I fully understand that you are so much busy every day, but still you are taking out time for this faculty development program in the early morning. Thank you very much, sir. Over to Professor Dipankar Chaudhary.
Thank you so much, Mahesh, for such detailed introduction. And good morning to all of you. Namaskar. I hope all of you are fine and staying safe. I am really delighted to be here for this faculty development program. And thanks to the organizers, mainly Dr. Mahesh Sharma. Of course, he was my former PhD scholar at ACSIR, CSIR, CBRI Roorkee. So I'm very delighted to be here in this program. However, due to the shortage of time, probably my lecture and along with my another former PhD scholar, Dr. Ashutosh, we will share the presentation on this earthquake resilient foundation system. I tried to align the topic of the FDP along with my topic of presentation, because this is a very important area, disaster resilient system. Actually, there are several disasters, and I will be talking about only the earthquake component of it, and that too the foundation system. So some of my recent doctoral scholars at IIT Bombay who worked on this similar topic are listed over here. There are many others who have worked earlier as well. Like as I said, Dr. Ashutosh Kumar from IIT Mandi will take over soon after my presentation. And there are many other scholars who actually contributed. So this contribution is essentially from my students' contribution, because they are the one who actually developed several important theories, and those are getting practiced in several projects also, not only in India, but various parts of the world. There are industry partners for the project, and today I will just briefly explain that which are the projects we executed from IIT Bombay with the financial support from these companies which are shown in this slide. There are many others, but today, because of the restricted time presentation, what I will do only, I will specify few of them in this presentation. We all know that natural disasters in 20th century, this is the percentage distribution which actually given by authors Welling and Mohanty in way back 2009. If you see that among all the natural disasters, earthquake takes the major share of close to about 51%, and then followed by floods, and then followed by tropical storm, then volcanic eruptions, which may not be that frequent in this our country, but all other natural disaster, even tsunami, landslide also we see quite often in India and surrounding region. If we see the regional share of this natural disasters in 20th century, Asia and Pacific region, that takes actually the majority of it, about 85%. Some of the examples of failures of structures which are supported on various types of foundations during the earthquake are very well known. There is no need to tell about these things, because all of you are, I understand, faculty members, so you are very aware about these various failures. So how to make these structures which can withstand earthquake, that is the job of for us as a civil engineer overall, and also as a foundation engineer or geotechnical engineer, or with the knowledge of earthquake engineering. So how to make these foundations earthquake resilient, that is what we are going to talk about. So if you see here over here, like piled $1 million bridge after 1964 Alaska earthquake, or piled Shoah Bridge failure after that Niigata earthquake, or pile tanks after 1995 Kobe earthquake. These are some of the classical reported examples of failures of foundation system due to the earthquake. How to make the earthquake resistant construction? You can see the one of the example for a bridge. You can see the bridge deck along with this arrangements where you can have the vibration isolation as one of the technique. This is from Japan when I visited the site as a JSPS fellow. That is what is shown over here. Then slope stability using earth anchors is another way of protecting the slope as a geotechnical engineer. This is also from a Japan case study, which I myself has visited the site. So I can say there is no need to cite any reference because these are my own photo. Coming to the foundation systems, we all know that industrial structures, including the power plant facilities, oil refineries, fertilizers, storage shelters, or tall buildings, all these actually can survive, or their failure will be associated with the effect of economic development of any nation. So we have to make sure that this structure never fails or these foundations never fail. So more challenge always comes when such kind of foundations are constructed in earthquake-prone region. And classical examples, of course, in the worldwide, there is a aim to go higher and higher. You know, the Burj Khalifa is so far the tallest building in the world, but soon it will be taken over by Kingdom Tower. So when we, as a geotechnical engineer or as a civil engineer, actually go for the site investigation or site selection, what are the criteria we look into? You can see that, first of all, desktop study, but more importantly is geological model and risk assessment is required if your site, whether it is earthquake prone or not. Then from that, you can find out there are various components of it. One is called hazard, another is called vulnerability, another is called exposure, and all these three together what we call as risk. So when we talk about risk, whether your site or chosen site of the construction, whether it comes under low risk zone or moderate risk zone or high risk zone, that need to be obtained. Based on that, you can see that for low risk zone, what are the things required? Like ground investigation is the must for all cases, like disturbed sampling, coring, etc. Then general testing of all these ground investigation materials, and finally use of empirical correlations. So that is the bare minimum. Even if the site is low risk area, still one is supposed to do all this testing. Coming to the area where it is moderate risk zone, so ground investigation, again, it is essential, and along with that, in situ testing is also essential in such case, along with general testing for lab. Also, site-specific correlations need to be used for moderate risk areas. Whereas for high risk area, if suppose your site, you don't have any option but to construct your structure in the high risk area, then preliminary ground investigation along with detailed ground investigations are essential. And in situ testing, high quality undisturbed samples, high quality laboratory testing, all these are essential. And remember, site specific correlations is very, very important for such kind of high risk site before you go for actual design. Coming to a typical type of foundation system which we generally use for mega structures, either we use shallow foundation raft for mega structures depending on type of soil and loading, etc., or we go for deep foundation like pile foundation. But recently, about 20-25 years back, it started already the practical use of this combination of both shallow and deep foundation, which we typically call as pile raft foundation or combined pile raft foundation, CPRF. This is a composite structure where it is like you have a component of raft present as well as few piles are also present. So that is also gaining its importance and applicability because of several reasons. Of course, today's lecture, I am not focusing on CPRF. Maybe my former student and colleague now, Dr. Ashutosh Kumar from IIT Mandi. He may be describing about this topic in detail. Some of the applications of combined pile draft are available, which started since late 80s or early 90s, I will say. It's like Messeturm Tower of Germany is the first example, practical example, where this CPRF was used. And after that, there are many structures, including the present tallest building of Burj Khalifa. The foundation of that is actually what is called on combined pile draft foundation. There is an international design manual or design guideline available, published by ISSMGE from the TC212D foundations. And this is a manual only available as of now internationally, which talks about the design aspect, how to design a combined pile draft foundation. So you can easily search in Google and get the copy of it and download this. This is available for free. So here essentially pile soil, pile, raft soil, and pile raft, all these four types of complex interactions are involved, where we always try to identify that how much load of the total structure is getting shared between this pile and raft component. So pile resistance we compute from its end bearing and skin friction, as you know, whereas raft resistance essentially gets computed based on what is the base pressure getting generated, which is a function of settlement, of course. So this is more of a serviceability based design, that is where you have your requirement of how much settlement you need, and accordingly you design the structure. There are books available on this topic, and I would like you, if related to dynamics or earthquake, if you want to use, you can see on the left-hand side, there is a book available, Foundation Systems for High-Rise Structures. This is a textbook actually, not only for academicians, faculty members, but also for practicing engineers. So this is co-authored by me along with my two other colleagues from Germany. And we also talk about here how the foundation design need to be done, even under the dynamic loading condition. There is another book available. This is the book edited book actually, the Pile Draft Foundation, how the design and analysis components are available. So coming to a few practical examples, I will just try to emphasize here how we proposed for actual real field problems the earthquake resilient foundation system to the structures. And just three case studies I have picked up. Just quickly, I will show the example, and maybe Dr. Ashutosh Kumar may detail some of this. So foundation system for oil tanks in Iraq, we were fortunate to design this actually, and also foundation system for a reactor building of a nuclear power plant, which is coming up in Hisar, Haryana, in India. And then Mumbai Trans-Harbour Link, MTHL, India's longest sea bridge. It will be actually, when construction is completed, it is on progress now, 21.8 kilometer long. A foundation for that, it is in Mumbai. So the first one is the dynamic soil structure interaction analysis for the oil tank foundation in Kabza, Iraq. This project, actually, the owner is British Petroleum of UK and SK Terminal of Iraq. And this project came to us at IIT Bombay to do the seismic design, actually, because that region is moderately earthquake prone. And actually, Dr. Ashutosh Kumar was one of the PhD scholars that time who was involved in this project. And also other geotechnical consultant and team were involved from Arup, Mott MacDonald, Fugro, and Chemitech. You can see this is the site in Iraq, that is this location, which is called Basra, and the detailed design details and analysis method considering this dynamic soil structure interaction you can get in our journal paper, this one, Geotechnical Engineering, published by ICE London in 2016. We actually got this paper. This is the soil profile, typical soil profile at the site. You can see over here, and this is the various N values reported from the field test. Actually, Fugro Dubai office, they did the testing in this Iraq site, and the data were made available. So make the structure for the oil tank earthquake resilient or earthquake resistance. What we did, we have, for each oil tank, we have proposed 89 numbers of piles of 800 millimeter dia, and this is the arrangement you can see, and we have done all the analysis, numerical analysis, analytical methods, everything for the site. And this is based on our design, seismic design. This construction took place, and finally it got completed in the end of 2015 year. There are several tanks with our design method under earthquake resistance condition it has been designed. Coming to another mega projects or classical project, I will say, for our new nuclear power plant, which is coming up in Hisar, Gorakhpur, because why this is unique, I will mention to you that most of our existing power plant in India, all those are in the site where rock is available at certain depth. Whereas this is the peculiar site, this is in purely on alluvial, being the region you can understand in Hisar, Haryana, Gorakhpur. So there it is completely alluvial, no rock is available. So that is the challenge. This is the first nuclear power plant which will be constructed completely on a soil strata. There is no very hard strata like rock strata available, even if you go several hundreds of meters below the ground. Of course, owner of this project is NPCIL, Nuclear Power Corporation of India Limited, and various involved geotechnical consultants and companies are like ITT Cementation, Fugro, NGRI, IIT Delhi, IISc Bangalore, IIT Madras, and at IIT Bombay, we did the foundation reanalysis and checking and redesign actually. So in this project also, at the beginning, Dr. Ashutosh Kumar was involved, and later on, my present various students, Mr. Dilli Rao, Mr. Aniruddha, they are actually involved deeply in this project. So various news articles you must have seen that these facilities will actually solve severe power requirement of the country, because there are 700 megawatt units of GHAVP 1 and 2 have been proposed in this Gorakhpur site of Haryana state. This is the location of the site. You can see this is the site of our NPP, nuclear power plant. And you know about the seismic map of India as per IS 1893 part 1 2016. So this is essentially coming in this location where it is actually selected such that it is in the seismic zone 2. As you know, seismic zone 2 is the least seismically hazardous site as far as Indian seismic zonal map is concerned as of now, as of today. So this is one of the case study. Just I am showing you how we have conducted a rigorous study. You can see that not only the foundation and foundation system we have modeled along with the soil, but also we have modeled the entire superstructure, because effect of height of superstructure, everything is so important, mainly in the dynamic analysis. You can see this is the reactor building, then we have reactor auxiliary building, this is the raft region, this is the pile region, and this is very complicated, as you can understand. This is not a very well symmetric structure, not like that. So even the raft thickness, everything is changing. So this is the isometric view of our one of the iteration of the analysis. As you know, there are various iterations. Obviously, for sake of I will say confidentiality of the project, we don't disclose the final one. This is only, we are just showing how this analysis was carried out in one of the iterations. So this is just one of the iterations which we are showing over here. Then here actually the CPRF has been used for first time, I will say, in India for such a mega project. Actually, there may be some other project, but such a large mega project of size even 100 meter by 100 meter area covering that. You can see the total number of piles is this many in RB area, reactor building area, and reactor auxiliary building area. This many number of piles, and pile diameters of 1.2 meter and 1 meter of different length, like 36 meter and 30 meter are proposed to be used. You can see the raft region, the raft thickness. This is also very, very huge and mega, as you can see, compared to whatever raft thickness you can think about. So, and that too, it is non-uniform, because at the central location, it is about 7.7 meter thick of raft, whereas at the periphery region, 3.5 meter thickness of the raft. And accordingly, we have done the entire analysis to find out how much settlement. Coming to the third project, actually, in which we were involved, and or the project was given to us by L&T. This is the reanalysis for pile soil interaction structure for the Mumbai Trans-Harbour Link MTHL phase 1 actually. And total length of this sea bridge will be India's longest one, 21.8 kilometer, and owner is MMRDA, Mumbai Metropolitan Regional Development Authority. And you can see the involved geotechnical consultant was L&T, and L&T approached us to consider the seismic design or earthquake resistant design of this foundation, whether it is okay or not. So you can see MTHL connecting the Navi Mumbai and Mumbai mainland. This will actually reduce the travel time extensively because of construction of this bridge. And this sea bridge is 21.8 kilometer. Already I mentioned width of the bridge will be 27 meter. It is a 6-lane highway, and design period is of course 100+ years. So for this project, what we did, we have conducted the analysis in 2 parts. First of all, we did the site seismic response analysis using SHAKE 2000. As I mentioned, for important structures, it is always required that for seismic analysis, you should do the site-specific seismic hazard study or seismic response study, because otherwise borrowing it from some other site or mapping it to some other site doesn't make sense. Dynamic soil structure interaction was done completely for the entire bridge foundation using Plaxis 3D. And as you may be knowing that Mumbai comes under seismic zone 3 as per IS 1893 2016 seismic zonation map. And you can see these are the various soil properties and data. Actually, this is as per the various layer. So as you know, this area, this is actually Arabian Creek. If I go back to this picture, so initial first phase, which is about 10.1 kilometer, which came from L&T to us to check the seismic design or earthquake resilient design, whether it is ensured or not. You can see there will be a standing water height for this creek region. Arabian Sea Creek region is about 10 to 13 meter. And after that, you get a very soft clay. And beyond that, you will get some rocky site because close to Mumbai region, that is the typical soil profile, as you know. So you see typical layer of one of the piers has been shown in this picture, for which analysis has been done. Of course, analysis has been done for all the piers and the critical ones have been obtained. You see that this is a very, very mega structure which you can think about, because look at the pile length, which is 36.5 meter. It is okay. But look at the diameter. Diameter is 2.2 meter, which is a huge pile diameter. And we actually went for the site visit, and we were actually astonished to see when our proposed seismic design method they're actually executing at the site. It was really worth visiting that site, I must say. So along with all my PhD scholars, we had been invited by L&T, and we visited the site also when after our design, the construction started. And it is now at a very advanced stage. Hopefully in the next year is the deadline. By that, this bridge will be completed. So piles are connected to 3.3 meter thick pile cap. So this is of course not CPRF, because you can understand, because this is not a raft which is distributing the load, because as I said, initial few meters, it is just water because it is the Sea Creek region. So you can see these are the thickness, or like seabed here is about 3.3 meter you get. After that you get very soft clay, and then you get about stiff clay, and then around 20 meter onwards, one can get basalt actually. So Mumbai region, that way, I will say that at a reasonable depth, you can, founding depth, you can get a good quality rock for the foundation. And you see, this is the pier head, and on top of this, your deck slab will come for the bridge, and this is the pile cap. This is the pile, and of course the pile soil interactions have taken place. So bridge deck is rested on pier head with help of the elastomeric bearings, and pile cap supports 2 pier shafts. So 15.134 meter length and pier head of 3 meter. So you can see that 2 piers, they are supported by 4 piles. So 2 by 2 arrangement actually. And for each of these, we have done the seismic analysis. You can see one of the result from our study, that how we have done this MTHL seismic analysis, lateral displacement direction and in both the direction X and Y under earthquake loading. So these are some of the examples which we have actually executed, how earthquake resilient design in practice can take place. So this is what I was mentioning when we went for site visit on invitation from L&T. These are those massive pile foundations getting constructed. You can see 4 piles, 2x2 arrangement. And on top of that, this is another pier locations where the after pile cap, then piers are getting constructed. Now 2 piers you can see over here. And once completed, this will be having actually a beautiful view, because one side you can see Elephanta Cave, some portion also, and another side Trombe, this the directions you will get. And this will be beautiful natural way to actually the travel through from the Mumbai to Navi Mumbai, connecting these 2 areas. And one of will be the longest bridge of India once completed, 21.8 kilometer, as I say. So with this, I conclude now with the summary that the evaluation of the displacement stresses resultant are highly important factors which you have seen for the response of foundation components, and connection rigidity is very important in CPRF when you are using for raft and pile design together. And soil raft interaction dominates the design at the initial stage of loading, but later on always it is found that the pile soil interaction plays an important role, and this peculiar behavior of CPRF can be utilized always for the actual design depending on the tolerable lateral displacement. For seismic design of CPRF, the condition of resonance must be checked, and also the effect of superstructure need to be considered carefully, which I have mentioned for both like a nuclear power plant foundation system. With this, I conclude my presentation as of now. So, and my former student, Dr. Ashutosh Kumar, now take over. Thank you so much. Dhanyavad.
Thank you, sir. Thank you for taking our time. And we understand that you have another meeting that was scheduled to start at 10:30. It's already 10 minutes late. So thank you very much, sir. It would be great to host you next time in person in the beautiful hills of Shimla. So that's my request to you. With these words, I thank you once again on behalf of organizing committee, Himachal Pradesh University. Thank you very much, sir.
Thank you so much. And I also look forward to meet all of you in person. I think there is no comparison of meeting in person, of course, because we can interact
also in
one-to-one.
Shimla.
Yeah, right.
Yes,
interact
yes.
one-to-one. Yeah. Okay. Thank you so much. Namaste, everybody.
Okay, sir.
No. Thank you very much.
Thank you, sir.
Thank you, sir.
Thank you.
So, dear participants, now we have with us to take it further Dr. Ashutosh Kumar, who is currently working as assistant professor in School of Engineering, IIT Mandi. Before joining IIT Mandi, Dr. Ashutosh was working as postdoctoral research associate at the Durham University and part-time lecturer at Teesside University in the UK. I hope I pronounced it right. Teesside?
Yes, yes, yes. It is,
okay,
it is,
okay, thank you. His work in Durham relates to understanding the performance of transportation infrastructure with changing climatic conditions. I think that is very much relevant in today's world, where climate change is something topic of town now. He has also worked on investigating the causes of the collapse of UNESCO World Heritage Sites in Nepal through a British Academy funded project. He obtained his PhD degree from IIT Bombay, and the wonderful thing is he's the recipient of IIT Bombay PhD Thesis Award, which was conferred to him by none other than Prime Minister of India, Narendra Singh Modi. I think he's also a DART Fellowship awardee from Germany. He has been awarded 2019 Outstanding Reviewer Award from ASC, International Journal of Geomechanics. He served as 2016 DART Young Ambassador for DART India. He has also been selected as an early stage researcher to attend and present his research work in Research Link workshop that was organized in Brazil during September 2018, supported by a Newton Fund of UK. During his PhD, he was involved in the design and analysis of foundation system for a reactor building of the proposed nuclear power plant in Haryana. His research encompasses highly relevant areas of civil engineering. The first topic is soil structure interaction, engineering behavior of unsaturated soils, geotechnical earthquake engineering, seismic performance of heritage structures. He has published around 30 papers in various journals of international repute and in various conferences, and is an active reviewer of several international journals. So I welcome Dr. Ashutosh. It's also very proud for all of us that you have joined IIT Mandi. So definitely you are going to play a direct role in upliftment of this state, directly or indirectly, and especially in tackling disaster resilient infrastructure, like how we can come up with it. So that was the reason to get connected to Dr. Ashutosh. And I'm very much grateful to him that he took out time from his busy schedule, because he's a young researcher. He's always in the laboratory or in the field. So thank you very much, Dr. Ashutosh. You please continue. You can continue now. Thank you. Thank you, sir.
Yeah, my screen is visible, right?
Yes, it's visible
okay,
now. Yes.
Okay, so before I start, so first of all, I would like to thank the organizers of FTP and especially Dr. Mahesh. And it was really nice to know that he returned back from US and joined Simla University, and it is really nice to connect and really happy to be invited here. And coming to lecture, so I'm really grateful for my PhD supervisor, Professor Dipankar Chaudhary, to kindly agreeing and agree also for his kind agreement also to share the lecture with me. And you could see that he has made my job very easy in order to, like, he has given brief overview of what are the work which has been done in his lab, particularly in the areas of foundation engineering and when the foundations are subjected to earthquake loading. And especially we are now in this FTP program, we are just touching the earthquake part of the disaster. So I'm really grateful, and my job would be now to give you more emphasis and to make you aware about what were the intricacies that we like encountered during handling the project, which he has explained already. So I'm really grateful to him, and it is really an honor, I will say, that in order to share a time and share the podium with him, I will say. So in today's discussion, what we are going to discuss about how we can design foundation, especially when it is subjected to earthquake forces. So let's see what I have got today. And today I will be mainly talking about, like, what are the research which I have done during my doctoral time at IIT Bombay. And in that line, I would discuss about that, what is our job as a foundation engineer, and how we can design this particular foundation system when it is subjected to earthquake forces. And the most important part that I will discuss is how to make a foundation system an economical one. Of course, it should be having and satisfying the criteria of safety. There is no compromise on that. So, as Professor Chaudhary has already discussed, and I would just like to echo with him that you see that how the world has developed over the years, and you should be surprised to see the number of buildings which are increasingly becoming very, very high in number all over the world. And if we talk about high-rise building, the first building that comes to our mind is none other than Burj Khalifa. And if you see the trend, the way the buildings are increasing, having height, and you could see that how over the time these buildings are increasing in number. And it has been all over the world. But during 90s, actually, many of the high-rise buildings were like within, I will say that in European countries or in US. But after that, a lot of buildings have come up in the Middle East and especially in the Asian countries. And you see why we need infrastructure which is very high rise in nature. It is going to touch the clouds. Why is that? It is not like we are fond of making something marvel. It is also the requirement. You see, in today's world, the population is going and increasing very high and high. And in that case, what has happened is you cannot extend laterally. The only way to extend and expand yourself is vertically, and that's what we are doing. You count any country, like you count any metropolitan city, I will say, like be it Dubai, Mumbai, London, Tokyo, you will see same reasons. So it is also, you see that how we are extending up because we cannot grow laterally because of the crunch of the land which we have. And when we talk about growing, so all the civil engineering infrastructure that comes to your mind is going to be rested onto the ground. And if you see here, the way the civil engineering infrastructure or mostly the skyscrapers have taken over, here we have Mumbai, where the height of the infrastructure is around 200 meters. And we have 3 buildings in there, but Dubai is leading it. So you can see that how Asian countries are now building more and more civil engineering infrastructure, which is a kind of skyscrapers in nature where the buildings are very tall and more than 200, 300 meters. So when we talk about these infrastructures, the idea is how to provide a sustainable foundation solution which can make these infrastructures straight. So there comes the role of a foundation engineer. Our job is very, very important. So what we do as a foundation engineer? So our job is to understand the principle or mechanics of soil and apply them to the practice or apply them in selecting the suitable foundation system for the envisioned structure which is already planned by a planner, by a structural engineer. Our job is to make them stand firmly onto the ground. So I will say here that whenever you see any marvel Taj Mahal or you see any other marvel Burj Khalifa, you must thank geotechnical engineer because it was his responsibility to make these structures stand and to make this structure what you are looking at it and admiring it. So our job is to determine how in a best possible way we can transfer the forces which are getting generated from these infrastructure to the soil. So I will come into more detail that what is exactly foundation doing. So let us see. So when we design foundation system, we must have information about the ground. I will come into more detail that what are the challenges that we have currently, and if we do not take up these challenges very, very seriously, what repercussions it might give. So let us see that what I have got. Is my slide entirely visible? Because first top part, I think it is like little bit not visible. Is it correct, Dr. Mahesh?
Yeah, it is perfectly visible, Dr. Ashutosh.
Okay, thank you.
Yeah.
So when we talk about foundation and when we talk about design, so what are the things that we should consider while designing? Of course, the capacity of the foundation and overall stability of the foundation should be satisfied. So whenever we talk about capacity or overall stability, then we have to think about what possible way we can transfer these forces to the ground and how the ground is going to behave when any superstructural load. And by superstructure, I mean whatever portion of the structure you are able to see or visualize, admire, whatever whatever it replicate, whatever it resembles. Then comes what should be the settlement, differential settlement, tilt, distortion. So these are the criteria which should be considered. Then comes what is the condition of the ground, whether the ground is loose enough or when you start constructing, it will start moving. So that can also be one of the consideration. Then comes effect of cyclic loading. And you see here that when we talk about cyclic loading, these are the loads which can be imparted onto your infrastructure. I'm not going to the detail where other loading like tsunami or other forces can also come to the infrastructure that are going to be constructed to the offshore sites. I will not go into detail, but mainly when we talk about constructing the foundation system, we have to consider these forces. Then comes what is the response of any foundation system to earthquake forces. Is there liquefaction phenomena? I will discuss in detail about that as well. Further to that, actually, the structural strength of the foundation element, as Professor Chaudhary has highlighted, that when we talk about foundation element, we talk about whether it has got piles, whether it has got raft. So it can be solo raft foundation, pile foundation, and it can be combination of raft and pile foundation as well. And then comes the durability of the materials which we use in the foundation. So all of these factors are extremely important in our design when especially we think about designing a foundation system which is earthquake resilient. So the idea of designing that you will get to know now. So when we talk about foundation system and when we talk about structures, so the challenge that we have is whether it is a sustainable planning process or not. And by sustainability, I mean that whether you have used your material judiciously, whether you have used your space in a better way, or how much optimized your design is. And for that reason, we as an engineer interact regularly with architectural experts. And we try to optimize the resource, we try to optimize the time, and by doing that, we optimize the cost. Because in our profession, time and money is very, very relevant. We do not have infinite time, we do not have huge sum of money to put into the project, and that can and we cannot rely on delivering the project in infinite time. So these are the various things that as an engineer we have to think. So whenever we do any project, we are always asked that how much time you will take. So these are the things that we must understand, provided we must ensure safety, we must ensure serviceability, we must ensure stability, and at the same time, we should be cost efficient, we should be energy efficient wherever possible. So as an engineer, your job is as towards the society is manifold, I will say. So, and once you will get involved in any project, you have to satisfy each of these. So as a geotechnical engineer, it is not going to be very valid in saying that you will just satisfy whether the structure is safe in terms of taking or in terms of satisfying the loading which is coming or not. You should also provide a solution which is cost efficient. And for that, today I will bring you
I think there is some signal problem. So Dr. Ashutosh will be joining us back. There is some glitch. Yeah, that may be because of bad weather that we are facing in Mandi and Shimla. So dear participants, I hope that it's adjustable. You will be joining us back within a few seconds. Thank you. So in the meantime, I would like to tell you again that the AICTE certificate will only be given to those who have attendance more than 80%. The attendance part is being taken automatically from the Zoom platform. And the second thing is about the quiz, because AICTE has made it mandatory to conduct a quiz regarding this faculty development program at the end of the sessions. So the participants are required to score at least 60% in that exam to be eligible for that certificate. Thank you. If you have any other query before Dr. Ashutosh joins back, I think I can take one or two queries. You please can raise your hand in that case, or put your query in the chat box. Dr. Ashutosh says WhatsApp me back that there is the power cut in his campus at Mandi. So I think he will be adjusting and joining us back within a minute, I think. So thank you again. I think there is a query from one of the participants regarding the quiz. So we'll try to keep quiz very simple, so that it's not only for those people who are experts or done their studies only in this part of geotechnical earthquake engineering. So the quiz will be in a way that it will try to cater into it the requirements or from every participant. So I think there's no need to get much tensed about it. Yeah, it will be very, very simple quiz based on the broader agendas that we have been discussing in this program. Okay, I think he's back. Allow करिए उनको, आशुतोष. Okay, ask to unmute. Dr. Ashutosh?
Yes. Yeah. I cannot start my video. Is it like?
Wait. Yeah. Just wait a minute. Video start करिएगा जरा. I understand, Dr. Ashutosh. So
yes, really, I'm very sorry for this. Yeah.
No issue.
So,
no need to be sorry because that is not in your hand.
Okay.
Yeah.
So there is some problem in the video, I guess.
No. I think it's from my side.
Okay.
Yeah. So I need to give you permission to, my team is trying to do it. Okay. I think you can continue, but I think it will take a minute.
Yeah, all right. So I will, but yeah. I cannot share the screen. Screen sharing is also disabled.
Okay.
Yeah.
Okay. Wait a minute. Allow to multi-pin.
Otherwise, if you can make me co-host, then I can do that as well.
Right. So I think the issue is whether. Okay, just a minute, huh? Just a minute.
Yeah, I think I am able to share the screen now.
Right. You please carry on now, huh? Sorry for
yeah, no problem at all. And so, okay, let me resume. And I'm really sorry for what has happened. So let me start from where I was. So I think I was here on this particular slide, right? Dr. Mahesh, could you please confirm?
Right. Yeah. Yes.
Okay. So let us now see that whenever we talk about providing an economical or sustainable foundation solution, what are the challenges we face and how we overcome those challenges? So when we talk about combined pile raft foundation, so that is the idea of combining two foundation, which is shallow and deep foundation together. So if you see here, the idea of any foundation system is to transmit the load which is coming from the superstructure. So basically your foundation system is acting as a bridge between your soil and the superstructure that you are seeing. So the total overall idea here, we see that we have to transfer the load. And when we think of transfer the load, then we think about what should be the design philosophy when we design the foundation system. So for pile raft foundation system, there can be two cases in the design philosophy. If you only raft foundation cannot provide an adequate bearing capacity, or if raft is unserviceable under working load condition, By unserviceability, I mean whatever the design criteria in terms of deformation to the foundation system, which has been given by structural engineer. The possible solution in that case is to introduce few piles beneath the raft foundation to satisfy both the serviceability criteria as well as the bearing capacity criteria. From this particular picture, you should be able to see that provided we have applied a uniformly load onto the foundation system where the maximum deformation has been observed at the center of the foundation. And if this criteria is not accepted, or this level of deformation is not accepted by the structural engineers, then we have to introduce few piles beneath the raft foundation in order to satisfy the requirement of the superstructure. And in doing so, what we are doing, you can see here. The idea is whenever the load of the building is coming onto it, it is going to be resisted by the combined action of piles and raft. And when we talk about combining these two components, then comes how the different components are interacting with the ground. And those interaction, we term it as soil structure interaction, where the soil structure interaction can be divided further into, as you can see that it has different components all together. We can call it as pile raft soil interaction, soil raft pile interaction, raft soil pile interaction, and so on. So these interactions are going to govern the load bearing mechanism whenever you think of any superstructure which is going to be constructed here. So this is very, very important for us to understand. Another case that might be prevalent in any infrastructure, because if you see the infrastructure which we are constructing and the foundation which is acting as a bridge between that is going to be subjected to not only vertical load but also the lateral loading, and that lateral loading can come as a result of wind loading, earthquake loading, and so on. And if you think about only raft foundation, you could see that raft is going to mobilize its load because of the resistance which is getting developed at the base of the raft. If you introduce pile only and if you don't consider the effect of raft there, so the entire resistance is going to be carried out by the combined action of only pile group here, where the passive resistance that you could see that is getting developed and it is taking care of your lateral load which is coming due to the either it can be wind loading or earthquake loading or whatever lateral loading you would think of. But if you are combining and utilizing the capacity of raft foundation, in that case, your raft as well as pile are taking the load. So this is a kind of optimization in design that we do and try to understand what portion of load is going to be carried out by raft and piles when it is loaded either vertically, laterally, or we have combined loading condition. So this is one of the foundation system that make use of both the foundation components and provide safety and serviceability to the infrastructure that comes to it. But whenever we design the foundation system, we try to follow the different codal provisions where we usually interact or ignore the different interactions that are available that I have just told. And those would be your pile to pile interaction or raft to soil interaction. So these types of ignoring foundation interaction may changes what actual behavior would be. So the codal provision sometimes would try to oversee these effects. Whenever we design only pile foundation, we do not carry or we do not consider the contribution of shallow foundation. We try to assume that your raft foundation is rigid or it is acting as a pile cap. Its job is to only transfer the load to the pile. Its job is not to share any load with the soil. So these are the things that we try to design when we try to follow, or these are the things we try to follow when we try to design the foundation system. One of the most important part, you see that we try to oversimplify the geotechnical profile. We ignore the contribution of ground movement.
Our speaker is facing. I think our speaker is facing some kind of technical issue, so we can wait for 1 to 3 minutes. After that, we will continue. So currently, we are waiting for 1 to 2 minutes.
Dr. Mahesh? Dr. Mahesh, am I audible?
So you may continue now.
Okay, okay, all right. Okay. So you see here that whenever we talk about superstructure and whenever we talk about when the superstructure is going to be rested onto the soil, these are two different entities. You see here we have a soil which is natural in nature. We have structure which we are going to be constructing over it. So when the two different entities are going to interact, especially we are going to say it as in terms of technical term as soil structure interaction. And in terms of structure, this structure, when it is going to be constructed or when it is going to be resting here, it is going to impart, let us say, dead load plus live load. Whenever we have such loading combination which are present here, and the idea is these are going to be imparted and going to be transmitted to the ground. Another load that will exist over there would be your wind loading. And ultimately, the wind load also is going to be transmitted to the ground. Another type of loading that you can think of is earthquake load. And obviously, earthquake is not happening somewhere here. It might be happening or somewhere below the building, 100 kilometers away from the building. And if an earthquake is happening 100 kilometers away from the building, these earthquake travel in terms of seismic waves. And they are going to hit the entire buildings. And your foundation design should be such that it should be able to withstand the forces which are coming due to the earthquake. So I will give an example. Let us say that you are standing in front of very heavy wind, and that heavy wind is trying to, and you as a body are trying to provide a stability to yourself in response to that particular wind forces. You can easily think of that particular situation. Similar thing happened to the buildings when it is getting hit by any earthquake. So it is a wave, and that wave is a kind of stress wave, and it imparts some forces onto the foundation, and using your foundation, which was sometimes, and I define it as a bridge, it is getting transmitted, and then your building tries to sway left and right, and eventually it transfers the load. So there are two types of phenomena which is getting generated here, which we as an engineer say it as inertial load, which is only where the earthquake is using the mass of your building. I will discuss more in detail about that. And the other part would be your kinematic loading that is coming to your building. And that kinematic loading is because of the movement of the ground which happened during the earthquake event. And when I combine these two events together, which is combination of your static load or combination of load that your IS 456 gives, our Indian standard gives, and the dynamic forces we combine, we call it as dynamic soil structure interaction phenomenon. So whenever we design a foundation system, we must consider the effect of earthquake forces onto the infrastructure that we are constructing. And of course, what is the foundation which we are choosing for that particular construction. So you see here that one of the building has toppled. So the idea is, if you do not consider the forces or you do not consider the ground properly, you may encounter such condition. And these conditions are everywhere actually. So as an engineer, I will say that we learn from the failure. We don't learn from the success. So it is, so in terms of civil engineering, I will say that if some building is standing straight, it is very hard to say that your design is perfect. It is very hard to say, but whenever any building has failed, you can say that, yeah, there was some flaw in the design. So because this is going to rest on the natural environment. This is your natural environment. You don't know that how this is going to behave because you have done the geotechnical investigation, not for the entire site, for a representative site you have done. And because you see that these three buildings looks similar in nature, two of these buildings are standing straight, but one building where you should be able to see that the pile has come out from the ground, the building has toppled. The ground investigation must be carried out there, but the forces which are going to come either because of the presence of the building or any external ground movement which is happening in there, that might not have been considered in particular, and that might be the reason. So we as a civil engineer try to learn from the failure that happened in civilian infrastructure. This is well-taught case history of 1964 Niigata earthquake, where you should be able to see that how this building has toppled, how this particular building is sunk inside the ground, how this building is trying to go inside the ground. Similar condition for this building. So in this particular situation, what you can observe that the ground was not sufficient enough to carry the load which is coming because of the superstructure. And why it has happened? It has happened because of the effect of an earthquake. What earthquake usually have done to the soil is it has liquefied the ground. That means the strength or the shear strength in particular, if I will say, shear strength of the ground has reduced such that the load of the building which is coming onto it, it has been exceeded the shear strength of the soil, and the effect of it you can see here. So soil liquefaction is one of the phenomena that we encountered during earthquake event, where the shear strength of the soil reduces due to the development of pore water pressure within the saturated soil matrix. And this was observed a lot during 1964 Niigata earthquake in Japan, 1964 Good Friday earthquake in Alaska, and since then, a lot of research has started on understanding the effect of earthquake onto the infrastructure, understanding the liquefaction itself, a lot of research has been started. So you could, and also one other point which I would like to highlight here, that you should be able to see that why only couple of buildings have collapsed, not the buildings which are particularly lying into this region, not buildings which are particularly lying into this region, not particularly buildings which are lying into this region. And you should be able to see that if we consider this as a planned area where the ground investigation might have been conducted into this region, into this particular region, or design consideration might have been conducted into this particular region, not specially into this region. There can be n number of scenarios which can happen. So a thorough ground investigation is required. Why the ground has lost the strength only into this side, not here, that is another question that we as a geotechnical engineer have to think on. So lot of research has started, and you could see that these are the types of failure. We try to call it as bearing capacity failure. So when we say about the event of liquefaction, you usually see the water along with the mud try to come out of the ground because of the saturated soil media, and that soil media is trying to push out because of the seismic shaking or the dynamic loading which it has been subjected to, and that you can see from here. This is the picture from Bhuj earthquake, and you should be able to see that how the muddy water has, or the water which is muddy in nature, I would say, has oozes out of the ground. And if you can imagine, if any infrastructure which should be here, what will happen to the fate of that infrastructure if we do not consider the particular event of soil liquefaction when we design our infrastructure. I will give you an example that will illustrate that what will happen when a soil is subjected to a dynamic loading. And you should see that a very nice intact sample, and this you can simulate in the laboratory condition, and you can see that very nice intact sample that you should be able to see here. And when it is subjected to dynamic loading, which is a kind of cyclic in nature that we can simplify as an earthquake loading, when it is subjected under saturated condition, you should be able to see the dimples here. And I will say that if you have any infrastructure onto this particular soil and the soil is showing some dimples, because I cannot show the failure here in the laboratory environment, we can easily control whatever happening, and we can see the pre-failure phenomena. You can imagine if there is a foundation or a structure standing, what would happen to that particular structure. So these are the things that are very, very relevant in our design when we consider. Another beautiful example, which I would say, of SOA bridge collapse, which was observed during 1964 earthquake, and you should be able to see that how this particular bridge has fallen. The deck of the bridge got separated from there, and this was mainly because of the lateral spreading of the ground. Because during the liquefaction phenomena, your soil is losing the entire strength which it has. And because of that, if your ground is slopy in nature, the soil would try to flow. And once the soil itself has gone out, what would happen to the fate of any infrastructure which is resting on it? You can imagine that. And that is what has happened during SOA bridge collapse. You can see here that there was a bridge deck here, and that particular bridge deck, it has just fallen because the foundation itself, the pier itself has moved. And if that will happen, this is the condition that you will encounter. So there was a study which was reported by Takata et al. In 1965. You should be able to see that how the pile foundation has buckled. What has happened to the pile? you should be able to see. So these are the study which was reported way back in 1965. This is the study. You should be able to see that if the foundation is passing through the soil strata, which is liquefiable in nature, which has tendency to lose strength, and which lost strength during 1964 earthquake, what will happen? The additional stress, because the ground is not present there, this is your pile, and the soil is there to provide the resistance, either in vertical direction or in lateral direction. So in terms of confinement, all gone during the case of earthquake. If this condition disappeared, entire stresses are going to be coming onto the pile foundation, which is there. And that is the reason, if you have not designed pile to consider that the bending stresses or shear stresses which are developing, you can see this particular condition and what would be the fate of your foundation, and especially it is going to be affecting the infrastructure. You could see that some of the reinforcement coming out. These are the examples which you should see from this. Another example you should see from 2001 Bhuj earthquake, and for that particular foundation or for that particular structure, this is a building which was lying close to the shoreline, and you should be able to see that the building has just tilted. It was one of the reasons was because it was pile raft foundation was used there, and whenever the pile raft foundation is used, you have capacity because of pile component as well as because of the raft component. And in that condition, you should be able to see that if this foundation or pile is breaking anywhere, the raft can redistribute the load because it is connected. It can redistribute the load to other piles, or it will not allow the complete collapse of the building. If it will not allow the complete collapse of the building, you will have sufficient time to move out of the building. Safety can be ensured. I will not advocate about this foundation system is very good in terms of taking the seismic loading, but I will advocate about this foundation system can provide sufficient margin of time so that you can move out of the building and the building will not undergo complete collapse, which may happen because of the complete failure of the foundation system. Another thing which is very, very important when we design foundation system is how each earthquake forces are going to affect different building. So I will just discuss in few moments that earthquake is a force which is going to affect your buildings differently. If a building is 5-story building, it is going to be affected in a different way compared to a building which is 10-story, 20-story. And there are a lot of examples starting from I will say like Kobe earthquake, if I will name the example of Mexico City earthquake, your Nepal earthquake, lot of examples that provides an idea about whenever these earthquake forces are going to hit the building, it is going to excite the building in a different way depending upon the natural time period of these buildings. And buildings which are highly more stories or high-rise buildings are going to be within this particular time period. Buildings which are lower stories are going to be within this particular time period. And from that, you can think of that how it is going to be affected. Usually, we represent it in terms of spectral acceleration response. And for a building having a time period of 5 seconds, it is going to be affected or applied with the spectral acceleration response of 0.4 g, which is the mass of the building multiplied with 0.4 times acceleration due to gravity. That will give you what is the lateral force which is going to come up to the building, and your design or your seismic design must be sufficient enough to consider these forces. So when we talk about foundation, there are two sides of it. First of all, our success remains buried inside the ground, but our failures are obvious headlines. Why it is? Because you see that we admire the infrastructure that is resting above the ground and that is feasible to us. But when it comes to failure, we always criticize that something might have happened because of some of the intricacies of the project which were not considered by geotechnical engineers. So we must understand what is the nature of the ground. We must do thorough geotechnical investigation. So ground characterization is very, very necessary, and which we must know about the geological condition of the site. We must have the data about the field and laboratory to understand how the ground is going to behave under the condition of loading which we are going to subject to. So whenever we talk about earthquake, we always feel that is earthquake different compared to other forces, like we have dynamic loading which is coming due to wind, we have dynamic loading which is coming due to the movement of train. There are many other ways of bringing the dynamic loading into it. So you should see here that we have a response here which is represented in terms of acceleration and time, which is going to positive and negative direction, which represents that at particular instant of time, you have acceleration, which is positive in nature, and at other instant of time, we have acceleration, which is negative in nature. It is something like a cardiogram. You should be able to see. So when we measure the earthquake, usually it looks like this. So you should be able to see that it is applying the load to one direction. At the second instant, it is changing the load to the other direction. So earthquake is not a force. You should be able to see here that a building must resist. It is the force that earthquake is using the mass of building against itself. I will give you an example. Say here that you have the acceleration here, and from Newton's law, you can calculate, you know, the mass of the building. Higher the mass of the building, higher the inertial force it will impart onto the structure. So stiffness part becomes really, really important. So during the event of earthquake, the earthquake event is using the mass of the building against itself. So this is very, very important. This is not like any other force. This is not like your wind force. So because it has some acceleration, and that acceleration usually is going to apply higher load considering higher mass. And because of that, actually, the stiffness parameters, ductility parameters, and the natural period of the buildings becomes very, very important. So these are the various factors that we should consider while design. Additionally, earthquake is going to hit your building again and again. You should be able to see here the way it is changing its magnitude from positive to negative. So it is going to hit your building again and again in a short period of time. And this makes it far more destructive compared to any other forces. And that is why when we design any earthquake resilient infrastructure, we focus about the stiffness of the infrastructure. We focus about what is the energy absorption system that we have. And in that line, Professor Chaudhary was showing you the vibration isolation system, which has the idea of isolating the energy which is getting transmitted from foundation to superstructure. Another important part in earthquake is we have aftershocks. It is going to hit your building to already damaged, which is already in damaged state. So this is very, very important for us to consider when we think about earthquake forces. So I will give you an example about energy absorption. Let us see what I have. So this is very nice example of energy absorption, which we can observe in Taipei Tower 101. And if you consider the effect of, or consider the location of Taiwan, it is located in the region of area which can experience heavy typhoon, as well as it can experience earthquake, and you should remember Chichi earthquake. So this particular building is unique in nature because onto the top deck of this particular building, they have installed a damper system so that whatever energy which is going to come because of either earthquake forces or because of the wind event, it can help to dissipate. One of the most important part in terms of earthquake analysis we consider is the stiffness and the restoring nature of any infrastructure. So you see that whenever there is a sway is going to happen, that sway must be able to restore itself because of the stiffness it has. So dynamic problem must have stiffness present in that. And you should be able to see that there are big pistons here, and this is a very big bearing ball system where this one is going to help to dissipate whatever energy which is going to come to the infrastructure. So you should be able to see, I suppose that I have a small video clip that can help you to understand how it is happening. So this is the video which I took 5 years back, if I remember. So let's see what it has got. So you should be able to see that how this part is moving during one of the typhoon which the building experienced. The idea is how we can dissipate the energy. So with that idea, as an earthquake engineer, we should probably move that how we can dissipate the forces which are coming to the edge. So I would give one line that earthquake, if you think that earthquake kills, no, earthquake never kill. It is the collapse of the building that kill the people. It is the state of civil engineering profession that we have not considered all the forces in a relevant way. And because of that, building collapsed and that killed people. Earthquake never kill. So these are the things that we must understand. And when it comes to high-rise buildings, when it comes to any infrastructure, we have to think about what sort of foundation this will provide. And this was the picture that Professor Chaudhary also shows, where we should be able to see that many high-rise buildings are now getting supported onto the combined pile raft foundation system, where we are utilizing the capacities of both the foundation component, which is pile and raft. And if we could talk about the performance of these foundation system, so it will be in terms of displacement, in terms of angular rotations, it should be in terms of bearing capacity. So all of these needs to be satisfied. These are the various histories which are case histories which are available on this particular foundation system, and you should see that they have extended beyond the codal provision. And these are the limits. We have certain limits that code provides, but this foundation system gave rise that, okay, you can go beyond whatever the settlement criteria which our codal provision provides, provided you satisfy the criteria which is required for structural engineers. This particular foundation system has performed really well during 2011 Tohoku earthquake of Japan, where the region experienced the earthquake magnitude of 9. So this is another important case history where the building which was resting on combined pile raft foundation system performed really well. When it comes to providing a cost-effective foundation system, so this is the picture which I took while I was in Germany during my dad's scholarship program. So you should be able to see that this particular foundation system was able to save around 5.9 million US dollar because it has used the concept of combined pile raft foundation system, and it should not be able to save this cost if only 316 piles or only pile foundation were supposed to be used there. So this particular foundation system, they have used 64 number of piles, and they have used the capacity of raft as well. So this is the foundation detail for that. And when we talk about the advantage of this particular foundation system, you should be able to see that it provides the improvement of serviceability in case of shallow foundation by reducing the settlement, differential settlement, tilt, and avoid eccentricity. So these are the challenges that we encountered when we design the foundation system. The idea is you place the pile strategically beneath the raft foundation so that you will not have higher differential settlement and you can avoid eccentricity. Whenever we design the foundation system, and if the water table is present, we usually see that there is high contact pressure variation because of the lowering of groundwater table during summer season and rise of the groundwater table during monsoon season, and that foundation can take care of this event as well. Pile can act as a settlement reducer where raft can take a portion of load. Lateral load that is getting induced during the dynamic loading condition, it can be shared by both the foundation components. And as we have seen that in case of liquefiable soil strata, which was observed during 2001 Bhuj earthquake, raft provide buckling stability to the pile in case the foundation is subjected to excessive load that we have already seen. So I will not go into detail about explaining the advantage of this, but in a nutshell, I will give that if we are thinking about a sustainable foundation solution for earthquake forces, I would say that CPRF can give you a cost-effective foundation solution in case of earthquake as well. But it comes that how to design this particular foundation system. And when it comes to design this particular foundation system, it comes about obtaining the capacity of this foundation system. So what we have developed, and this was the work which we have developed during my doctoral research, we have tried to obtain the combined capacity or the capacity of combined pile raft foundation system at various settlement level. So if you look into the codal provision there, you will not get a capacity which is dependent on settlement. But what we have tried to do here, that we have obtained the capacity of combined pile raft foundation system at various settlement levels so that it can allow flexibility to the designer to adopt at any settlement level he would like it to. And for that, we have utilized the capacity of single pile, unpile raft foundation system by adding various interaction factors which I was talking earlier. So you should be able to see that whenever we have foundation system which is combined in nature, we have pile components. So because of that, we will have pile-pile interaction present. We have pile and raft here present. So we have pile raft interaction, we have raft pile interaction, and all these interactions are going to affect the load bearing mechanism, and we try to add everything together. And also we know that load settlement behavior is not linear. So linear nature of load settlement behavior we avoided into this prediction. We obtained the hyperbolic model in order to incorporate non-linearity into the behavior of soil. And based on that, we proposed the expression for pile raft interaction factor, proposed the expression for raft pile interaction factor. So if you know the capacity of only raft foundation only single pile that you can easily obtain from IS codal provision, you can put in here and you can obtain the capacity of combined pile raft foundation system at any settlement level. I would give you an example that how pile-pile interaction works. And the idea is when you keep two piles together, they are going to be a superposition of stress and displacement field, and that will affect the overall behavior of the foundation system. So you should be able to see that these are the two piles which are present, and if I am separating them together, how the displacement fields are getting separated. And because of that reason, we should consider these interactions. So this is one of the examples which I have given. You can think about a raft pile interaction factor and pile raft interaction factor. Accordingly, that would give rise to a complex load bearing mechanism when we think about combined pile raft foundation system. And if you consider this load settlement behavior, you should be able to see that if you just consider only single pile, let us see that we take the capacity of 9 single pile, and if we have the capacity of 9 single pile which is placed in a group at various settlement level, how the capacity varies, that you can see. And this gave rise to pile-pile interaction. And accordingly, we have developed the expression based on the way the load settlement behavior varied actually. When it comes about earthquake loading, we have a lateral load which is coming onto the infrastructure, and that lateral load is going to be transferred to the pile, which is usually done in terms of combination of vertical load, lateral load, and moment loading. And for that, actually, we have a method called EY curve method that we can adopt in order to design the pile foundation when it is subjected to combined nature of lateral and moment loading. These are the various design goals that we consider when we design the foundation system, that there should not be a large deflection that can lead to structural damage. There should not be a slippage between the pile with respect to soil, and no large lateral deflection that can cause non-structural damage. So these are the things that we should consider when we design the foundation system. Dr. Mahesh, how much time we have?
Dr. Ashutosh, we have time for you. How much time I think it will take from your side to wind it up?
Well,
it's a wrong question to ask a teacher, right? Teacher can always go on, right? But we were expecting to wind this session by 12 o'clock with some questions or queries from our participants also.
I think in that case, what I will do is I will discuss one case which Professor Chaudhary was discussing, and then I will wind it up then. Okay?
Sure. Yeah.
So I will not discuss more into design, but I will discuss about this thing. Okay.
Sure.
So let me give you a brief example. Whenever our infrastructure or mainly foundation system is going to be subjected to combined earthquake event, of course, it is going to be subjected to the loading which is coming from the superstructure. But whenever we apply a seismic load, which is going to be applied or which is going to be coming below the ground, and it is going to hit your infrastructure. So this is one of the study that we have done, and it is published in International Journal of Geomechanics. So you should be able to see and follow this study from this particular journal. But what I would like you to show you that whenever a seismic shaking is happening, how the foundation system is going to behave in response to that. So you should be able to see that when we apply the seismic load at the base of the soil model, how it has developed, and in response to that, how pile is displacing and how bending moment is going to develop into that, and how bending moment is changing with respect to time, that you should be able to see. So this study highlights about the nature of load, which is this particular soil model is able to transmit through the ground to the foundation system, and this is the way the pile is going to show bending moment, which is the important criteria for the design when it is subjected to earthquake forces. So these are the things that we should consider while designing the foundation system. Another important part that I would like to highlight here is the importance of analyzing the foundation system by applying the acceleration time history. So here you should be able to see the development of bending moment for various earthquakes time history, which is El Centro 1979, Loma Prieta 1989, Bhuj earthquake and Sikkim earthquake, where we have received maximum magnitude of bending moment in case of Loma Prieta earthquake, which has peak ground acceleration of 0.279 G. But if you consider the El Centro earthquake, which has magnitude or which has PGA, peak ground acceleration we call, which has 0.43 G. So you should be able to see that even though peak ground acceleration was higher in case of El Centro earthquake, it has lower response compared to Loma Prieta earthquake. That gives importance to analyzing the foundation system, subjecting it to acceleration time history, because there is a phenomena of resonance, there is a phenomena of matching of the natural frequency of the foundation system with the natural frequency of the predominant frequency of your seismic excitation. So these are the various papers. If you are interested in understanding the effect of earthquake on foundation system, you can easily find it out, and if you need, you can definitely contact me. I would be happy to share with you. And I will discuss very briefly the case study which Professor Chaudhary was highlighting and where I was involved as a and you can find the details of it in to this particular paper, where we have designed the foundation system for an oil tank in Iraq. And when we talk about the foundation system, idea is what are the challenges that we have to consider? What are the intricacies of the project that we must consider? And for that, you need a thorough joint soil investigation report, which was carried out by Fugro, Dubai. We needed probabilistic seismic hazard analysis report, which was carried out by Mott MacDonald, UK. For that, and based on that, we performed ground response analysis. The idea is to subject the ground to earthquake excitation and to understand what is the behavior of soil under the condition when there is no structure present. We investigated the liquefaction potential of the ground using the established procedure given by Idris and Bolanji 2008. Then we designed the pile foundation based on our IS codal provision. We tested the pile at the site both vertically and laterally. We performed the numerical simulation. We performed the entire modeling of soil, pile, and draft, which Professor Chaudhary was also showing in FLAC. And then we performed the dynamic analysis as well. So this is the ground profile that you should be able to see. It has soft clay, and below that it is a very weakly bedded clay stone which is present. We have designed the pile foundation based on various loading combinations which we have got, and this is the final model, and this is the you should be able to see the soil property which we have chosen for designing and for considering the constitutive relationship and for considering the low deformation behavior for soil part as well as for the pile part. This is the simulation of the result, and these are the various results that you should be able to see, and we try to establish that under the vertical loading condition, whatever settlement which is happening should satisfy the permissible criteria for liquid storage tank. And based on that, we try to analyze. This is the various contours which you should be able to see that can give you an idea about how the piles are developing the load which were within the permissible value that we have got while designing the pile foundation. This was the acceleration time history which we have developed for the site based on the spectral response that we received from Mott MacDonald, UK. And in case of earthquake loading, as you know, that liquefaction event and liquefaction phenomena can happen, and for that you have to monitor these things very, very carefully, so that there is a volumetric straining of the ground, and your numerical models, you should be able to capture these things. And we have considered this using the Mode Coulomb model and Fin model, which is available in FLAC, and that can give you an idea that what is happening to the foundation system. Whenever there is an earthquake, you should be able to understand the development of pore water pressure, and you should be able to understand the forces which are getting or displacement, and forces which are getting into the pile as well as into the raft. So these are the various results. These are the various pictures that we have received from the site during the design period that you are able to see. So with this, actually, I would like to end. And if you are interested, you can also go into this particular paper, where you can obtain the details about various studies that we have conducted, and some of those studies where which Professor Chaudhary was showing. So with this, actually, I have come to an end of this session, and actually I would like to acknowledge and thank, of course, my PhD supervisor and the supervisor during the DAT program, Professor Rolf Katzenbach, and my colleagues from IIT Bombay, and one of the master student who is currently doing PhD at University of Utah. We were involved in understanding and designing this particular foundation system. With this, I am really, really sorry if I have exceeded the time, but thank you very much, and I am very happy to take any questions which you have.
Thank you, Dr. Ashutosh, for the wonderful lecture. I think, no, you have not exceeded the time. You completed exactly on 12 o'clock. So no issues. We have some time with us. We can take. So I think one of the participant is asking, can you please share the presentation? So I just want to inform all the participants that we are having a dedicated YouTube channel where everything is being streamed live. So you can go there. I think we can go back into that, right? So you can check out your presentation, whatever you want to see. But asking Dr. Ashutosh to send his presentation personally, I think that won't be much justice also from my side. So I think my request to all the participants, you can go on the YouTube channel. You can check it out there. It is being recorded there directly. You can watch it there again and again. So I think that would be better.
Yeah.
So
Dr.
Ashutosh,
if you have any question, yes.
Yeah. So it was wonderful to listen to you again. I just wanted to know, like, how you are focusing, about the future scope of your research now, because now you have landed up in IIT Bandi. So are you also taking care of this research, your core area of research, besides taking into consideration? Yes. Okay.
Yeah. So considering, you should be able to see that, okay, we have worked more on the foundation behavior. But one thing that we are also interested in investigating is that how foundation is going to behave, especially pile raft foundation system, when it is subjected to earthquake and when the ground is liquefying. And for that, actually, one of my master student, I don't know whether he's here or not, but Mr. Rahul. So he will be working with our colleague who is based in Technical University, Damster, Professor Hauk Chakar, and he will be going as an exchange student, and we will be continuing with that. Another, my PhD student, Sonu Kumar, is also working on understanding the behavior of this foundation system when we have a phenomena of climate change and how this particular foundation system would behave when we have a rainfall, which you see that in Himachal Pradesh region that we have frequent rainfall and our infrastructures are heavily affected during monsoon season, and we always say that in first rain we have more of landslide compared to the subsequent rains. So the idea is we have understood this foundation system under the condition when it is subjected to saturated ground condition, but more understanding is required when we subject the ground to different cycles of drying and wetting. We subject the ground to different cycles of loading, and of course we are considering the earthquake event, which is and how it can bring the liquefaction and how the foundation is going to behave, that we are doing with our colleague and collaborator based in Technical University Darmstadt in Germany.
Oh, okay. That's nice to know. And now at IIT Mandi, because I've been constantly in touch with you, so definitely we have many, I think, area where we can collaborate.
Yes, definitely.
And definitely we can.
Siddharth has raised hand. So Siddharth, have any question?
Yes. Sridhara, I think. Okay. Yes, sir. Yeah. You can go ahead, sir. Yeah. Yeah, please tell me. Yeah, go ahead, sir. Oh, okay, he has been unmuted. Yeah, please go ahead, sir.
Am I audible, sir?
Yes, you are perfectly audible.
Please go ahead. Yeah.
Yes, sir. My question is this effect of pore pressure, that is liquefaction, when the water table is already in the superstructure and when the water table is well below the foundation. The effect of this pore pressure or liquefaction in these two conditions, just relating these two conditions.
So your question is when water table is just below the foundation level, right?
Yeah. One more is when the foundations are inside the river or inside the water itself, wherein water table will be in the superstructure.
So in order to analyze this condition, so two conditions that you have highlighted, if the foundation is, let us say the river foundation, the foundation for bridge pier or abutment, and another condition is the building where you have variation of water table, but let us consider the worst condition, which can be the condition where your water table is just below the superstructure. So in both these conditions, we see that we have a phenomena of, let us say that we have a phenomena of earthquake. So in order to liquefy a ground, there must be a condition that has to be satisfied. First of all, the ground must be saturated. So considering that water table is satisfying that criteria. So once this phenomena is coming up, what happens during saturated condition when it is subjected to shaking? You have a development of pore water pressure, which happens within the three-phase soil matrix, or in this case, two-phase soil matrix. Whenever the pore water pressure or excess pore water pressure increases, it reduces your effective stress, and eventually your effective stress becomes zero. So in that case, the foundation experiences excessive settlement. In that case, the foundation experiences the loss of strength or loss of contact pressure which it is supplying to the foundation elements. So in terms of design, what we usually do, that if, let us say, there are two ways to design it. One way that you estimate the liquefaction potential of the site and you say that ground is liquefiable. Then you extend the foundation below the liquefiable ground, and during seismic demand, whenever earthquake will come, it will not consider, we consider this as the liquefaction will happen and the ground will not be able to provide any resistance. So this is one way to consider and to design. While designing this condition, we also consider that whenever you have liquefiable layer, non-liquefiable layer, because liquefaction is a shallow depth event. It cannot go beyond 50 meters or something like that. The codal provision that suggests, and also the evidence of the literature suggests that liquefaction is predominant at shallow depth, let us say 10 to 15 meters. And in that case, your foundation can go beyond, or you improve the ground another way. So as a geotechnical engineer, there are many strategies that we adopt for investigating. So I will give you an example that you can find out in one of the paper that I have shown in the last last slide actually, that you can find out from there that we have improved the ground for a site which is where the ONGC or Indian Oil is constructing the oil terminal. It is sharing the border with India and Nepal in Motihari, actually, Motihari in East Champaran. And there we have used the ground improvement in order to satisfy that the ground is not going to liquefy under the condition of any envisioned earthquake for the site. So understanding the seismic hazard is very, very important here. So because it cannot happen that, okay, some soil has liquefied in Nepal earthquake, it will also liquefy in Sikkim earthquake. Okay, so understanding the seismic demand is also very, very important, because when we evaluate liquefaction potential, we try to estimate the seismic demand, and that seismic demand will come from the whatever earthquake magnitude that is coming onto the site. So all of these things you should consider, and we also consider actually while designing.
Yes, sir. So I got the precise. Yes, sir. I got the precise answer for my question. I got it. Thank you, sir. Thank you, sir.
Good. Thank you. Any other questions? Please go ahead. I am very happy to interact, because interaction is more important in my opinion. So rather than lecture, so please interact. If you have any doubt regarding foundation engineering, don't hesitate to ask. Or you can write also in chat box, I guess. If you're
right. Otherwise, also they can always reach out to you.
Yes, definitely.
So
definitely.
Yeah. Because Dr. Ashutosh is a young academician, so interaction is something that he loves to do, and always you can reach out to him through his contact number and email ID, which you can get definitely from IIT Mandi website. Any application of this study in Himachal Pradesh, sir? Dr. Ashutosh, Ankit is,
yes.
Mr. Ankit is asking. Yeah.
Yes, definitely you should be able to see that in Himachal Pradesh, of course, we have hills. And we are in the hills, so the idea is that how we can provide a sustainable foundation solution for the buildings which we are constructing. So one thing that you should be able to see here, that today I have focused on understanding the behavior of foundation system when there is a high-rise buildings which are present. All right. And in that case, actually, I have tried to provide an application for that. But if there is a slopy ground which is present there, and in case of slopy ground, of course, we need the foundation system. And for that, we can easily adopt the foundation system, which is a kind of pile raft foundation system. But I would only suggest this kind of foundation system if you are going for high rise. Let us say for Simla region, that okay, in Simla region, why we are going towards high rise building, that you also know that because we have space crunch and we cannot move laterally, we can go vertically. And in that case, if you are trying to adopt this particular foundation system, then it can give you a good solution, provided you do thorough analysis, because currently we do not have codal provision that we are currently developing the Indian Standard Code for this particular foundation system. But there are sophisticated analysis which are involved and available that can help you to design this particular foundation system for Himachal Pradesh as well. Yeah,
I think we have, Partha is there. First of all, hi Partha.
Hey Miles, how are you going?
It's going well, and Yeah, Dr. Ashutosh is with us. It's great to know that you've also joined all the way from Australia.
No, I really wanted to hear Professor Chaudhary and Dr. Ashutosh's presentation. So I apologize that I was not there for the entire time, but did listen part of it, and it was really an educational experience. I was educated, so thank you for that. I have a small question, Ashutosh, if you do not mind with that.
Yes, please go ahead. Yeah.
So I wanted to ask, I understand that a part of your research also deals with unsaturated soil conditions. And do you see that if we include these unsaturated parameters while designing earthquake resistant buildings, we can do some cost saving, or is there any kind of advantage? Is there any kind of research agenda that you have where in future you are planning to include these parameters from unsaturated soil perspective to your analysis?
Okay, I got your point, and thank you for that. Actually, so we have recently started working on understanding the behavior of this particular foundation system, considering the unsaturated behavior. And I fully agree with you that the behavior of the foundation will change when the foundation system is going to be subjected to the events of wetting and drying. Because you see that whenever we load the foundation system, and we consider the long-term loading condition. But these long-term loading conditions are not usually long-term when it is subjected to wetting drying phenomena, which is going to be exacerbated during the event of excessive rainfall. And that will change the soil behavior, which in turn can be accounted in terms of soil suction. And if the soil suction is changing because of the changes in the degree of saturation, so this is going to change the strength of the or shear strength of the foundation system, and that can affect the behavior. So our current research is now getting focused on understanding how the contact pressure variation within the raft, as well as the development of resistance or the mobilization of resistance at the pile interface is going to change when we are changing the foundation, or when we are changing the or subjecting the foundation system or subjecting the soil in there to continuous wetting and drying. So what we have done currently is we have started this study by investigating the behavior of pile when it is subjected to this kind of loading condition, which is drying and wetting in nature, which is a kind of hydraulic loading instead of structural load or earthquake loading. So the idea is to combine these things together. So we are currently working on that, but of course we are very, very interested in understanding that how the contact pressure beneath the raft and the skin resistance at the pile interface is going to affect when there is a changes in soil suction brought by wetting and drying phenomena.
I think Partha, you have another question, or is it,
If there is any other question, I would be very happy.
Yeah, because Partha is, is an expert in the field of unsaturated soil mechanics.
Yes, yes.
So, yeah, Partha, we can always, take it up. I like your idea, and it can be taken up for collaboration also. Right. So, I think we're already late. So, thank you, Dr. Ashutosh, for giving us this opportunity to host you here. And next time, definitely it will be in person in the beautiful hills of Shimla.
Definitely.
Okay.
Thank you very much for inviting. It's really a pleasure for me. Thank you.
Yeah, pleasure also for us. So thank you very much. So dear participants, we'll be back at 1 p.m. With a lecture from Dr. Uday from IIT Mandi. He will be joining us at 1 p.m. So my request to all of you to join before, I think 12:55, so that we all are there at the right time. Thank you, everyone. Thank you, Dr. Ashutosh, once again. Thank you.
Thank you. Thank you.
Okay. So, dear participants, I think you can keep yourself. There's no need that you should leave this meeting right now. I think it will stay like this. So we'll be back at 1 p.m. Before 1 p.m., I think, at 12:55. Thank you. Thank you once again. Dr. Ivday, I think you have joined, right?
Yes, Dr. Mahesh.
Thank you. Thank you. I think we'll start by 1-5. Is it fine? Because our last session got a little extended.
Okay.
Yeah, yeah. So
In the
we'll
meantime,
start at 1.
Can I do the check, regular check?
Yeah, yeah. Please, please, Sean. Go ahead. So Dr. Uday, you are back, right?
Yes, yes.
Okay, okay, sounds good. So I hope, because we just had lunch, our last session was a little bit got extended till I think 12:15, 12:20, 12:15, 12:20. So I think participants also, we had around 115.
That's great.
Yeah, so I think now we are right now 67, 68 now. So we'll wait for 1 or 2 minutes.
No
and
problem.
then we'll start the session. Yeah.
Surely, surely, Dr. Mahesh. No issues.
Yeah, thank you. Yes, so I hope participants are still joining. Now it's 75, 74, 75. Yeah. Let's wait for 1 more minute.
Yes. Just can you confirm if my slides are visible? And
Right, right. Yeah, it's perfectly visible.
Okay, audible, right?
Yes, I think you have shared your screen, right?
Yes, I have shared.
Yeah, but I'm also seeing myself. What you can do, you can just go ahead with the F5 option, so that
already
only
on major screen.
Yeah, right.
You're able to see now?
Yeah, I think it sounds good now. Great. Okay, so 1 more minute.
No issues. So I'll quickly stop share.
Right.
Okay. You can take over.
Right. So a very warm good afternoon to everyone. So we'll be starting our next session. I hope all the participants have joined. Okay, but we'll start it now. Okay, Dr. Uday. So we have with us Dr. Uday from IIT Mandi. Dr. KV Uday is currently working as assistant professor at IIT Mandi, and he has done his PhD from IIT Bombay. He has more than 12 years of experience, out of which 2 years was in the industry, 3 years in the research, and then more than 7 years in the academia. He is one of the pioneer faculty of civil engineering at IIT Mandi, because I think he was the one of the first lots who joined IIT Mandi School of Engineering, right? And it's great to know that he's working in Mandi, which is in the Himachal Pradesh, and Himachal Pradesh also feels proud that academician like Dr. Uday is not limited to laboratory, but also we can find him always in the field. So when I was trying to get connected to him, the first question was, when are you having your field visits and when you can be free? So again, I thank you, sir, for taking out time from your busy schedule, and that also in the monsoon season, where so many landslides are happening and you are a landslide expert of the state. So thanks for that.
Thank you.
Apart from that, his research area includes landslide disaster risk reduction, nature-based mitigation solutions, biogeotechniques, and something interesting, that is machine learning in geotechniques. He is author of more than 10 research articles. He's more sort of a, what you call a technology guy. So he's having patents in his name. 2 patents he has already received, and 4 patents are in the pipeline. And he has received more than 3 crore rupees of grant from state and other organizations at the national level. He's also founding director and part-time CEO of startup of IIT Mandi, which is incubated by IIT Mandi Catalyst. So it's great to have Dr. Uday with us. I requested him to also make us learn from his field experiences, and you can always find him also in the news. I think 1 or 2 years back, he did a wonderful, remarkable work in the area of early warning system for landslide mitigation and for landslide detection. And that was very much covered in the media at the national and state level. So we are very proud that we have with us Dr. K.V. Uday, a young academician and researcher, and also an engineer. I should not miss it, because I think he's more engineer. Academician comes later on. So thank you, sir. Thank you that you are with us. And I again welcome you. You can share your screen and go ahead with your lecture. Thank you very much.
Thank you. Thank you very much for your very detailed introduction, Dr. Mahesh. It's always good to talk to people. So that's how I will say again, thank you very much for inviting me to the variance of audience. I'm seeing here, and definitely most of them towards Mandi in Himachal Pradesh mostly, or is there a spread across?
Spread across India.
That's great. That's great. That's
Yeah.
one more great thing. So yes, aligning very much to my introduction, brief introduction, detailed introduction, should I say, given by Dr. Mahesh. I will in today's sessions will be mostly talking on my journey in Himachal Pradesh, especially when I joined Himachal Pradesh in 2015. So I was mostly looking forward for my work in this area, and when I find that the major area or the major expertise of myself comes from geotechnical engineering, and the problem is always just behind or just besides you. That's what I learned from my esteemed faculty from IIT Bombay. So here I can see that when I joined IIT Mandi in 2015, I could see that there are so many of landslides happening across. And as a geotechnical engineer, I should say it's a paradise for me, at least for my research and my area. So thereby, I thought that I should be working in these aspects, and I will be probably through my slides taking you through what exactly I have tried to do and what we could achieve a little in these particular lines. And at any point of time, if you have any doubt, it's good if you can drop in some questions from the chat, so that to the end of the session, it need not be that you are retaining everything to the end. So it normally happens that you forget the questions as we go across, because I'm going to change in different lines. As you can see, first, though I'll be starting with landslides, we'll talk about a little on quantitative risk analysis, followed by a little on disaster risk reduction. What do you mean by risk reduction? Is it only about constructing something, or does it have a bigger impact or a bigger approach towards it? So as a part of it, definitely we have to see how this disaster risk reduction can be approached, or what are the various options we have in this. Then, of course, most important thing we are discussing about machine learning. So for the data is the most important part. So what is the relevance of the data and how we are collecting the data and all. Followed by this, I'm going to give a slight idea about machine learning and how it can be used in various contexts. And lastly, again, the outcome of machine learning is always on prediction. For example, I'm sure all of you in your mobile phones today, or even in your Gmail or whatever, when you're typing, you'll be seeing that you'll be getting a prediction of a word. Or can I use this word, or maybe this word can be preceded on whatever you're trying to write. So that's where machine learning plays a major important role in prediction. So when you're using machine learning, we always are going to end up somewhere in prediction. So I'm going to talk a little about all of this possibly on these particular aspects. So before I go ahead, I always recognize, or I always acknowledge my team associated with me, Dr. Varun Dutt, who is from computer science. So it's not that I am the expert of machine learning, but I'm learning it from him, from being in computer science. And of course, we do a lot of work together. Again, you will be seeing to the end of this particular presentation. And followed by this, I have a collection of students, should I say again, one who comes from geotechnical engineering, the second person who is from computer science, and the third who is from electrical engineering. It's not again that I, being a civil engineer or a geotechnical engineer, will try to solve this worldly problems, should I say, by using only the technology and everything available only from civil engineering or associated branches. So I have a passion of working across branches, not only again restricted to computer science. I'm these days working also with biotechnology and all these related aspects. So because again I asked, that's why to the host of this session, Dr. Mahesh, whether the participants are only from Shimla, only from Himachal Pradesh. However, I think that the participants are across India, so this will be something wonderful to other people who are seeing this. So this is a wonderful presence of IIT Mandi within the valleys. As you can see, we have wonderful hills across. We have two campuses. One we call it as a north campus, and the other is in the south campus. Probably I'm sitting somewhere in this particular zone currently when I'm giving you the presentation. And then across the campus, we have, of course, very typical of Himachal Pradesh, that you will definitely see snow peaks around. And apart from this, we also have a river just crossing the campus. So you can see this is the profile on which the river is flowing. So we have a small channel which is adjacent to our main campus, whereas a major river, which is Ohul River, on which the first Indian hydraulic power system has been tried on by the Britishers, and it comes on the same river, which is just as adjacent to us. So when we are talking about such a natural prejudice, then definitely, we are making IIT Mandi, or in fact there is a lot of settlements which are going across. We are going to make roads, we are going to make buildings and everything. So because of which we see that the disaster has started taking its time and its term in this particular area, where if in around should I say 14 kilometers from the district capital or district center of Mandi to IIT Mandi, if you are traveling, you are coming across 65 landslides. Okay, when I say landslides, yes, these are typical landslides. Though again, for most of the Himachalis, it may not look the same, but yes, for people who are coming abroad and across, it is really something. It's a sore on eye, we call it. It's not good scene that you see that so many landslides are happening, and we have been facing a lot of issues. When we call any faculty or any major experts to IIT Mandi, they fear only one thing, which is called as landslides. Okay, so we can see again, as a part of this particular landslides, you can see different types of topologies or different types of material associated with these landslides. So this is typically a fractured rock mass, where we are having different rock particles which have come down in this particular slide. Whereas again, you can see that there is a typically not really fractured, but yeah, it is not very severely fractured, but this is lightly fractured, but still it is solid, but still we could see some rocks caving in. And here, this is something very typical. These two slides are to say that they are my favorite in the total list. Whereas when I say that hardly the thickness of this is not even more than half a meter. Sorry, Dr. Mahesh. Okay. Sorry.
Yes, please carry on. Sorry,
I heard something from you. Sorry. Okay. So these two are of my interest, where I talk about a very thin crust, very thin crust falling down with huge amount. We can see the area. If you can see, the area is very big. So the volume which is running from this particular material is very high. Okay, so now currently these particular slides have been in phase of getting modified or rectified over the time. Apart from this, there are a few interesting slides where you will see the combination of rock or maybe stones, big aggregates or rocks or rock particles, and along with the soil which are coming down, whereas sometimes it's only typically soil. Okay, and when we talk about all this, the morphology is again something like, should I say, like a textbook where we talk about it's like critical slip surface which happens in typically soils. Okay, however, the materials, as I just told you, are different from each of this, and as we understand from our different technologies, that the same medicine will not work for all the problems. So we need to see how this medicine or this particular mitigation measures can change over this particular thing. And I am sure when we are talking about all this, we have seen another major landslide, which is Kotropi, which happened in 2017, when almost like 46 lives were lost. And when you talk about the width or the Magnus effect of this particular landslide, it's almost like 200 meters. So if I talk about any of these techniques which can be used to stop 200 meters and 160 meters height to 300 meters height and 200 meters wide, it's difficult to control any major phenomena which is happening in this place. So it's not that we are going to talk about only stopping the landslide. Sometimes it's very difficult to stop the landslides, whereas we sometimes should allow it. So when we're talking about all this, India tops actually the disaster associated with landslides, very pathetic situation across the world, that we keep. It's not that we are not spending amount. The amount we are spending is even much higher than what much of the developed countries spend on this disaster management. But however, it seems that there is a lot of issues because of which we are unable to get into a particular situation, and especially controlling the deaths associated with this particular disaster. So we call it disaster whenever there is a death, whereas if a simple landslide happens, then we simply call it as a hazard. We call it hazard if the landslide happens. If the happening of this landslide will initiate some issue either to life or property or any types of loss, then we convert it in from hazard to disasters. So there is a typical saying which says that hazard is most welcome, but disasters are not. Okay, so that's where we started looking into various options on how this disaster can be reduced, and that is the main focus of my presentation on disaster risk reduction. So when we are talking about disaster risk reduction, or whenever we are talking about landslides, just now before I came onto the slides, I showed you different material, like it can be rock, it can be a debris, which has different types of materials, and we can also have fine-grained soils. Apart from this, or based on these particular materials, we can say then their movements also gives an important point when we talk about a rock fall. A typical rock always fall, and the same rock normally topples. There can be rock slide and also soil slide. Then there is always a soil spread. Then all this, when most of the things are mostly dry, whereas when the water comes into picture along with the soil or maybe rock, then it initiates something called as a flow. So this is how we try to differentiate these materials and movements. So we will try to understand probably when we go inside how this categorization is important to understand or to tackle with the disaster associated with this. So typically when you're talking about disaster risk reduction, we are trying to see to reduce how the disaster can be reduced. Now, when I'm talking about disaster risk, then the risk is slightly different than exactly the hazard, as I told you. Disaster, again, we have discussed, whereas risk reduction is something again different from how you can do it. So a typical aspect of this contains of two options. One is structural measures and the other is non-structural measures. So what are structural measures? What are non-structural measures? Sorry. We need to understand what type of measures are we going on depending on the type of the risk we are looking at. So without taking much time, I will just try to quantify you what exactly are we talking about risk analysis here. So when we are talking about risk analysis, then it's actually a typical combination of hazard multiplied by consequences. Okay, so this is the word which comes into categorizing a hazard and a risk. The way I just told you that a hazard and disaster, similarly a hazard and risk. So when we talk about risk, it's about hazard as well as consequence. Okay, so in very typical mathematical words, they talk about the risk being H into E into V, where H is the hazard, which is the temporal probability, where E is the element of risk and V is the vulnerability of elements at risk. So when we talk about these type of issues, then I probably in the next slide, I'll try to show you how the risk becomes different from hazard. Okay, so typically when we talk about the hazard, then it comes in with probability, annual probability. So for example, in Himachal Pradesh, what is the temporal probability of happening of a landslide? So typically if I go back to your first slide, somewhere here, you can see, 100 kilometers square of area is falling or sliding because per year in Himalayan region. Okay, then every one person is getting killed across this particular thing. So this is the consequence part of it. Okay, whereas I don't know whether should I show you, 15% of this particular of the Indian area is falling into this particular line. So typically the hazard associated in this particular area is 0.15 according to these numbers, and element of risk we need to understand, and vulnerability, as I told you, we will just talk about it probably in the coming slides. Okay, so probably there's something. So I will do one thing quickly before I go to the next slide. I will try to show you what exactly these parameters mean. Okay, so yeah, I will try to show with the same diagram over here. So please bear with me on this. So for example, if I have a hill slope in this particular region and I have some settlements here, okay, some houses or some structures. Okay, so just for convenience or just for understanding, I'll show you two points where I have a small settlement and a large settlement. Okay, when I'm talking about a small settlement, large settlement, try to understand that this is typically on the number of people or the number of habitants in this particular line. Okay, so for example, now if suppose there is a rock over this particular place and it has come out and it is ready to slide. So when it is sliding, then with the moment you see something like this, I'm sure even if you don't apply the slope stability theory or rockfall theory or whatever mathematics we have in this particular aspect, even if you don't consider it, you can easily understand that this particular rock will definitely fall over time. Okay, so now when we talk about this particular rock, then we are talking about the hazard. Okay, so here we say that this rock indicates that there is a chance of a hazard. Okay, so in a case, for example, if there are no settlements, okay, then still the hazard is happening. Even if there are settlements, hazard is happening. So hazard has nothing to do with the establishment or the people or whosoever are staying in that particular area. Okay, now the point comes is element of risk. Element of risk. So if you look into, then typically, again, if I don't go into deep topic or deep understanding on this, then I will say that there is a good amount of chance that because of this particular rock, there are chances of 1 and 2 both getting disturbed, both getting disturbed or both getting affected. Okay, so now how does this element of risk change? For example, if I don't have a small settlement here, just for understanding. Okay, so for example, I have a bigger settlement here, and a smaller settlement here. Okay, now the question is, the element of risk changing? Is the value of element risk changing? Okay, so now the question is, I can take 2 probabilities. One, that this particular thing hits this particular settlement or this particular building. Okay, and partially it is damaged. Okay, whereas this is saved. Number 2 is this particular, if at all, or the second option is, if at all this comes and fails and this falls, then again there is a chance that both of the elements are at risk. That we need to understand depending on the probability, vulnerability, and all the particular analysis what we are trying to do. So there was still a good amount of chance that the other building which was on behind was saved because of the presence of a mighty structure or a building just near to the rockfall. For whereas in this particular situation, now again the chances are 2, whether this rock will hit the small settlement and stops here, or number 2, the rock damages the small settlement and also enters into the large settlement, large settlements. Okay, so now the element of risk depends on how much of these particular things can be are put on danger. Okay, so now if you ask me how to do it, there are a number of options, a number of softwares, a number of mathematical analysis which can be done to understand all this particular scope. Next is vulnerability of element at risk. Now the question is, for example, if I remove this, okay, now if I make the same, I don't know if I have an option to, okay, fine. So Dr. Mahesh, can you just confirm if you're able to see this label above, or is it only for me?
Yes, we can see it.
No, I'm saying the label with this mute.
Yeah, what you are writing, right?
Yeah.
Like marking with red.
Yeah. Yes.
Yeah.
Okay.
We can perfectly see it. Yeah.
Okay, perfect. Thank you. So now when we talk about the vulnerability of these particular elements at risk, then for example, earlier I showed you a slide somewhere here. Now what I'll do is I'll probably pull it somewhere here. Okay, on a slide, and again I have the same rock, typically with the same slope. If I say this particular rock is falling, now we can see, I am not again 100% sure, but yeah, again I will bring into the concept of probability that this particular rock may simply fall, stop here, or it may still get in here. But still I will tell you that in this particular situation, there is a good amount of chance that this rock may not hit the other one. Okay, so now if you look into the hazard, the vulnerability profile, then this particular thing is not vulnerable, whereas this is probably vulnerable. So there is a probability, if it says that there is a good amount of chance, 70% of the chance that this building will hit, but not this. So if you look into various cases and all, then for risk, if I'm talking about risk 1, the first situation where both the buildings were getting into effect, then 1 into 1 into 1, the risk is 1. Normally we normally look risk scale somewhere between 0 to 1, just for making it simple for you. Okay, the second case, when the bigger building was in front and there is not a good chance that the second building is getting affected, then the hazard is still 1. However, the element of risk is falling to half. Okay, and the other vulnerability was also less, so I will reduce it. Now the risk becomes 0.25. Okay, now I have third option in this particular case. For example, okay, this building is not at all getting affected. Okay, only this particular building, and this particular building also has a probability of only 70%. Okay, so now I'm talking about a different case altogether. Okay, don't worry about the numbers. I'm just taking these numbers to make you understand what exactly we talk about a risk analysis associated with this. Okay, so this becomes now 0.35. Okay, even if I say this building is also having a chance of say 0.7%, 0.7 probability of getting affected, then I will define another R4 as 1 into 0.7 into 0.7. So this comes approximately 0.49. So 0.5 approximately, whatever you can say. So now with this particular example, now I am trying to give you an idea about how the risk propensity is taken care of. Okay, so in the first case, when I'm saying that the risk is very, very high, then I'm sure if one of you or few of you are in these particular settlements, you are going to demand the stopping of this particular option, or we are going to demand that this particular thing should not happen, or the rockfall should be controlled, or rockfall should be taken care of. Okay, now I'll give you the second case. Okay, in the second case where we talked about the big building being in front and the small settlements being behind. Okay, there I'm sure now there will only be half people who will be interested. For example, people who are living in this building in this particular phase, they are more vulnerable, so they will say that there should be rockfall, the rockfall protection should be done. Whereas the small hutment, which was probably somewhere here, okay, they may not be happy, or they may not be saying, okay, we have nothing to do with that particular thing. Okay, so in the second case, when I'm talking about this particular situation, when the small hutment is in front, okay, where the second building was not vulnerable, then here this particular settlement people are going to demand on the rockfall to be stopped, whereas the other people who are just behind, who understands that the vulnerability is not at risk, then they are definitely not going to they are not going to face any issue, or they are not going to point any issue. That's where again, so the problem will be less. Okay, later if suppose they are also getting a probability, then again there is a risk. So when we talk about a risk analysis, then I'm sure when this particular situation comes in, then people will be more worried, should I say, to get into the risk. Whereas when in the other cases, there is a probability of people again getting into understanding of this. So now the point is, why are we discussing all this? Is depending on this, there are different mitigation measures. For example, if you give me this particular mitigation measure, then probably I have to look into option how I can stop this particular rock by going for this netting, meshing, or blasting, or whatever options do I have at the place. Okay, the next option, when I talk about R2, then probably we will say, okay, let us do one thing, let the rock fall. The only problem is protecting this building, so then probably I'll construct a wall over here so that the rock hits the wall and the hutments need not be changed. Okay, so that option is there. So I will probably check up this particular option here. If at all I am going to this particular option, then I will say, okay, we will do one thing. We will probably have intermittent measures and a fall over here so that the fall doesn't go further. Okay, I am sure I can make these hutments. I can move these hutments. Sorry, I'm doing a lot of drawing, so sorry for that. Okay, so in second case, what I can do is probably I will ask the government to shift these settlements from here. Just an option. Okay, I will ask the hutments to be removed, and I will go for some intermittent construction, something like this, where the rock doesn't enter into the area or the affinity into this particular point. Whereas when this is the particular situation, then probably I don't want to shift, because now if I have to shift this, I also have to shift this. So instead of this, I may invest the amount in constructing a barrier, or constructing a barrier somewhere here. Constructing a barrier somewhere here so that the risk can be reduced. So as you can understand, the option of your mitigation measure is changing with respect to the risk associated with your particular problem. Okay, if I could make this clear to you, then the whole presentation now should make some sense on what we are going to talk, and how this particular mitigation measure can be changed with respect to the requirement in the site, requirement at the location, what are all the important parameters. So however, in whichever case, again, to talk about this is risk, which is H into E into V. So in the same condition, for example, if I remove that, if I say that this particular thing is something like a jungle or some desert or somewhere where no people are living over time, okay, and there is a rock which has been seen that it has come onto the hill and it is going to fall. Okay, so now what is the risk? If I calculate, hazard is 1, definitely there is no element at risk and there is nothing vulnerable. So no risk. So in this particular place, I'm sure nobody is going to talk about making any of the mitigation measure in that particular place. Okay, so that's how the risk analysis becomes important. Again, if you see here also, in this particular case as well, I'm still having the hazard. The rock is still falling. The rock is still falling. But in this particular case, I'm not interested on this particular rock which is falling into a desert and creating no loss associated in this particular place. Okay, so that's where we have to talk about disaster risk reduction, not about disaster risk mitigation or disaster reduction. Okay, or disaster management as we call it. Okay, these days the world has started to change the word of disaster itself into disaster risk, because we have to control the risk. Sometimes it may so happen that there can be a good amount of chance that the some slide or something happens, but still all the people are safe in this particular location. Okay, so now when we look into this risk management process, then it has various terms and terms. I'm sure earlier this slide would have been of any interest. These days, because of the COVID and how the government is working on it, we are sure we are having a very good idea on this risk analysis. So if you people are fine, then I'll probably take it into the terms of COVID. No more talking about landslides for this particular slide, because it is easy for all of you to understand, even though you don't come from Himachal or you have never seen a landslide in your life. Okay, so now the question is always establishing the context. So someone from some country has understood that there is something like COVID and this is going to create a major issue, so they have reported it to WHO, whereas WHO has identified what is the risk associated with this. Then they understood that it is been transferred by touching or by contact. So the first thing which has come in for us is, okay, if it is going, then what is the point of this? Then they did risk analysis. Then they understood that there is a severe problem of life of people, and they have evaluated what can be the chance of a risk of this particular thing, because again it is what you call it is contagious. So they have to go for some typical understanding, and not all of them are susceptible to COVID. So that is why they have gone to risk treatment. What is the risk treatment? Now in the risk treatment, they have understood how this risk is going to be it can be reduced. I'm sure in the starting days, we never talked about having any vaccine, right? Vaccine was not at all ready. So at that particular point of time, we did not go for any permanent treatment. We have just went for something to avoid or reduce the effect associated with the with this particular problem of COVID. So we went for simple masking, social distancing, sanitizing, and all these particular things. So we have treated the risk. Now it has been under monitor. Okay, now state government, central government, district government, everyone has been very consistently working on COVID situation. They have been consulting, they have been communicating. Then slowly when the vaccines have come in, then the risk treatment has changed. Now also they are monitoring how many vaccines have been delivered, what is the stage of vaccination, how well these vaccinations are working and all. So when we talk about anything associated with risk management, then risk management is not a rocket science. Okay, when we talk about landslide risk management, again it is the same thing. It's about managing the risk. So it is not at all anything which is existing in the books, or it can be only the way it has to be followed. It is only understanding the process. It is always understanding the process and accordingly making the decision. And when we are making a decision, it is still under some uncertainty. It's not that when you're treating, you're going to 100% treat the risk. I'm sure again all of us can understand this particular point again in COVID situation, that it is definitely difficult to eradicate COVID, at least for the next 100 years. We just have come down to very less percentage in polio, and we are still fighting with smallpox and chickenpox related aspects. They are very, very low. It is not that they have been eradicated from the space or eradicated from our particular country. Okay, so that's how the risk management needs to be evaluated, again based on different steps and based on how the new process have started coming. So looking into all this, always when you look into disaster management, it is always about identifying the danger, then what is the frequency, what is the loss, or what are the elements of risk. Just now we have I just tried to show you a small example on how all this can be taken care of. Then we are talking about assessment and severity of risk. Then there is something called acceptability. Okay, so a typical example again, if I give you for Himachal Pradesh, there are a lot of what should I say? There are a lot of things coming up. For example, this bungee jump, or recently we have been contacted by someone who is interested in developing some what do you call this games in all these bungee jumps to paragliding, Okay, then rock, there's this flight jumping and all these things which have become very famous now. Okay, so there, when you are coming there, you are actually signing something that I am accepting the risk associated with whatever is going to happen if at all some disaster happens. Okay, like this again, always there is an acceptability. When once you are getting onto the road of Himachal Pradesh, you probably are accepting the point that you are going to travel through this particular terrain which is prone to dangers. Okay, and in most of the places the same is put as a board on the it's put as a board on what you call this on the road, saying that this is a rockfall zone, this is a landslide zone, there is a chance of a hazard in this particular area, accident prone zone. So it is expected when you are traveling in this particular thing, you are accepting that you are entering into this particular zone and you should be careful about this, and there is no one associated with any loss happening in these particular places, because sometimes it is not possible for everyone to act in any different conditions. So that is what we call it as acceptability. Now, whatever we discussed about this vulnerability elements, all these particular elements, how are you going to understand? They are going to be understood by heuristic methods, statistical methods, or probabilistic methods. For example, heuristic methods is something which is pulling up after the improvement in machine learning, whereas heuristic methods are something which is from human, or we should say it is a natural intelligence, it's not an artificial intelligence. Okay, so here people, for example, in Himachal Pradesh, if you have ever traveled or if you have had any particular experience, the vehicle drivers or the taxi drivers, they are so good that they simply stop at a particular location and this is there is a chance that landslide can happen, let us wait here. Okay, so they did not do any statistical analysis, they did not do any probabilistic analysis. What they know is only depending on their understanding on the stat and their understanding on the particular point. Okay, so it cannot be brought into mathematics, at least till date. Okay, so that is what we call it as heuristic method, which people know or people inherit themselves into their what you call this, into their understanding. The second is statistical analysis. Now we need to do a lot of processes by which we can understand how this problem can happen, or how this problem can be numbered, and depending on the data, depending on various aspects you can measure. Similarly, we have probabilistic methods, reliability analysis, Monte Carlo simulations, point estimate methods, event tree analysis. Like you should be doing n number of problems associated with these particular problems, and then you will be developing your own methods by which you will be understanding what is the chance or what is the probability by which the slide is happening or the rockfall is happening, and what is the vulnerability scale, and what are the elements at risk. All these are done by using these probability answers. When you're doing all this, then as I told you, we get some numbers, like the way I told you, risk is H into E into V. So finally, what we are going to do, either we are going to calculate it in numbers, or sometimes we do only qualitative analysis. So that's why I call this as qualitative risk analysis method. Okay, so in the qualitative risk analysis, you can do a simple scale which looks something like this. You can see I'm putting consequences as low, medium, high, and I'll put the same hazard as low, medium, high. Okay, similarly, if you want to do a very detailed risk analysis, then you can split not into 3 but into 5 but into 7, however you are looking at what scale of this particular risk. Okay, so based on this, for example, I'm sure to the end of this particular course, or maybe to the end of particular class, you also give something called as feedback to the faculty, or feedback to any of this, including your buys on Amazon, where you give star rating 1, 2, 3, 4, 5. Okay, so similarly, you can put these matrices also into the star rating 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, how the consequence is behaving, how the behavior is behaving. I don't know if you have given feedback in Amazon. They ask about 2 major feedbacks. Number 1 is the quality of the product, 1, 2, 3, 4, 5, and the second is quality of their delivery service, 1, 2, 3, 4, 5. Okay, so the same way you can see consequence and hazard. Okay, so this map you can prepare, and you can say the point which is falling as a high and high is definitely going to be high. Okay, whereas high of consequence and medium of result this can definitely be again put into high. Always the question is always in this particular line. Always the question is always on this particular line, which we call it as medium, where we are unable to understand whether this goes into high or whether this goes into low. Okay, whereas when I say low, again, where the consequence is low, I expect low risk, as just we discussed. Okay, similarly, where the probability is very high, then I don't want to take a chance when even the consequence is low, whereas the hazard probability is high, then probably I put it as a medium risk. Okay, so that's where we have to understand this is all qualitative, this is not quantitative. Okay, so based on this, you can change. So for example, if you will see in your particular place how your hazard and vulnerability are getting in, then accordingly you are going to put a risk map associated with this, and you are going to see whether your particular landslide or rockfall is falling into low risk zone or high risk zone or in a medium risk zone. Now, if it is falling on low risk, then probably people or the government or any administration may not be really looking forward to spend crores of rupees to stop that landslide or to create a situation. They will see how the risk can be averted and how the risk can be reduced. Similarly, if it is going into high risk, then you cannot expect the government or any agencies who are working on landslide to avoid this particular condition of high risk condition. Okay. Now, always, as always, the medium or the middle people always are the one who is going to face a lot of problem. So in this particular zone, it becomes very difficult to understand how to tackle these situations. So depending on this, the landslide risk reduction measures can be taken. So one of the case study which I have taken up from Norway, I'm just trying to show you that they have indicated this risk by using different indicators. It is hazard indicator and this is consequence indicator. So in hazard indicators, we have some parameters such as earlier sliding, height of slope, inclination of slope. Okay, so higher if there is earlier sliding, then this particular place is more somewhere in moderate understanding to have a landslide. If the height of the slope is very high, then the risk associated or the hazard associated with the slope is again very high. If the inclination is high, then the chance of sliding is very high. If you have a flat slope, there is no landslide. So that's how we see how this particular thing. And what I'll do is I will give some critical weightage to each of this. A critical weightage to each of this. For example, earlier sliding, okay, out of, if I say the top is 3, I'll give it 2. Okay, height of slope is very important, 3. Inclination of the slope, yes, it is also very important, 3. Okay, we call it something as over consolidation ratio. Again, it is something of very interest to soils which are like clay type of soil. So I will also give it a good weightage 2, or maybe in fact 2. So pore pressure is one most important parameter. So in this, if the pore pressure is building up, then it is 3. If the pore pressure is reducing, then it is actually very good. It will not allow the landslide to happen. So it is -3 + 3. Okay. Similarly, thickness of clay, higher the thickness, higher is the slide. So 2. Sensitivity, yeah, higher sensitive soils may not be good, or the sensitivity may not play most important role. So I will not give much conditions, because in Himachal we don't find sensitive soils, at least in Himachal. Wherever there is erosion, there is a good chance of happening of a landslide. So I'll give it 2. Where the human activities again are high, then again I'll see a weightage of 2. Okay. So I will give the same weightage for also consequence in, for example, number of dwellings. If the number of dwellings are high, then the risk is high. If the human living in these particular areas are high, then it is very high. Okay. Roads are always susceptible. Railways have a low vulnerability. So I will give 2. Power lines are always susceptible, but there is no life loss associated with this. So I'll probably give 1. Okay. If there are buildings, then it should be having a scale of 3, probably. Okay. And lastly, effect of floods. If there is a rockfall happening and there is a chance that there is a flood creating, then it is going to create an adverse situation. So again, I'll give it something like 2. So I'm just giving you an idea how a qualitative analysis will be done. So based on this, now you will see what is the weightage, and accordingly what is the score you are going to give in your particular case. Okay. So for example, if the height, as I told you, if the height is high, then the vulnerability is high. So I give it 2. If the height is more than 30 meters, then I give a rating of 3. If it is 20 to 32, 15 to 20 meters, 1, and less than 15 meters, I'll say the slope doesn't have any major importance. Okay. So based on this, we will try to see, for example, if I say that my particular site is coming in this yellow zone. So how do I calculate? So this is 2 into 1, 2 into 2, 2 into 2, then 1 into 3 in this particular zone, 1 into 3. Okay. Then again 3 into 2, 6. Then if suppose the sensitivity, if it is less than this, so let it be 0. Okay. So erosion, it is somewhere here. So it is 3. And somewhere here again, when you talk about, then it is 6. Then this is going to give me some number. Okay. So this number, the highest in this is always 51. So I will take this number, add it and divide it by 51. So I know what is the percentage effect of this particular slide. Similarly, I'll do the same with the consequence analysis. Again, I'll try to get some number. Okay. I'll multiply these numbers and then I'll get a factor called risk. Okay. Now I'll see what is the maximum risk associated with this. It is 51. here it is 45. So the maximum risk I'll be expecting is 51 into 45, whereas the risk associated, the least risk of course is 0 in both the cases. Okay, so R max and R min is going to be 0. R min is 0. So I have my risk at the site. Then I'm going to calculate what is this number, and I will see how near or far is this from this particular situation, and accordingly I will see whether I should give it green or should I give it red or should I give it yellow, again depending on different conditions what I'm getting from this. So accordingly we'll develop a map which looks like this. For example, in the hazard map, if you see, we are seeing that there are more hazard map, 1, 2, 3. Okay, whereas in the disaster risk map, if you are looking into okay, here you can see high, medium and low. Okay, whereas in the disaster, now I'm making it into 5 scale. So you will see now out of these 3, now the higher risk is only in this particular region. High risk, very, very high risk. Okay, so the high hazard is not the same which is happening in the high risk zone. Okay, then the second is definitely in this zone and in this zone, which is still lesser than what you were looking in the earlier hazard map. Okay, so that is how now the world is looking into this particular option, which is called as risk analysis. So just to give you an idea on a small scale of how you can do the risk analysis in your, at your particular location. So based on this risk location, again, I will come back to the point that what is the landslide risk mitigation measures do we have? So in a place where you have a higher risk, I am now going to talk about structural measures. The area where you are going to have low risk, there I am going to talk about probably something which is non-structural measure. Okay, and if you ask me what to do somewhere in middle or the medium risk, then again the question goes back to you. As again we say, always the middleman are the one who suffers the most. So try to understand which line you want to take up according to your location, according to the interest of the people and the administration, how they want to consider your particular situation. Okay, so based on this, we typically have these 2 locations, as I told you, structural and non-structural mitigations. Sorry, just a minute. Okay, so in this particular aspect, when we are moving ahead, I will just try to give you a small idea about the structural mitigation measures. So for a structural mitigation measure for landslides, we have 3 options: active measure, passive measure, and remedial measures. Okay, so what are active measures? Again, the first always starts with engineered cutting of slopes. So if you have engineered slopes, they're always good. They can be reduced, or the problems can be reduced in this particular option. Number 2 is by constructing retaining walls. Okay, so if you are constructing retaining walls, then we are seeing that the risk associated with the landslides are going to be less, or the hazard associated with the landslide is less. And we have some option which comes on nailing. I'm sure if you're looking into some tunneling projects which are going very much in Himachal, in this area, you will be understanding what are the how the nails can be useful for controlling the landslide or all these particular points associated with the landslides. Then we come up with something called as passive measures. In these passive measures, probably as the name says passive, they are not going to stop the landslide from happening, but it will reduce the effect associated with the landslide. For example, here we are just draping the soil by using this net. Okay, so if at all the soil fails somewhere in this, then the soil is definitely failing. It will come and probably reach here. It is not going to fall onto the road. Earlier, if the net was not there, then they should have fallen on the road. Okay, now it is not happening. Okay, similarly, here also you can see the same thing happening. Now it is controlling the measure by which the fall is happening. Okay, so these are nets. Then we have barriers. Again, there are good amount of work which is going on. If you have visited ATAL tunnel, you will be seeing a lot of barriers in this particular location, where you will see that the rock, if at all falling down, rock will still fall, but this rock will be falling on the net, but not falling onto the road, like the way probably it was earlier without nets. Okay, so it is still, so that's why I call it as passive measure. It is not going to stop the rock from falling, but it is going to hold. Similarly, again, when we talk about shotcreting or meshing, then again, we are doing the same. We are trying to reduce the risk. We are not allowing the water to go inside the soil and thereby create the problem. So we are controlling it by using these particular options on shotcreting or by meshing. And the next option we are talking about is by the concept of real-time monitoring. So if you have some sensors located in place, and if they are giving you solutions, if they warn you that there is a slide which is going to happen at the particular location, then probably you will be safe, or you will not enter into that particular zone. So that's why we call early warning. For example, the same way, if suppose the meteorological department declares that you're going to have a rain in the next 5 days, then you prepare for it accordingly, right? So we will make sure that you're not washing many clothes, or if you are washing, then you are putting probably inside your home itself. Or if they're predicting snowfall, then you will make arrangements either to go to visit the snowfall area or not. So similarly, we are also giving you early warning so that you can take care of this particular solutions. Apart from this, there are few remedial measures which are very interesting. If you control the drainage in the soils most of the time, then the landslides can be reduced, or the landslides can be controlled. Okay, they are remedies. They are like Ayurvedic medicines. Okay, so they will not allow. They will improve your system, and thereby they will improve your system, by which the landslide may not happen. Especially here, the landslide happens only because of the rainfall and the drainage rainfall by the drainage issues. So thereby, if you control the drainage, then I'm sure that half of the problems will be solved there and there itself. And the second option definitely is bioengineering. These days we are going for a lot of rainfall, a lot of deforestation, and thereby this deforestation is going to create a lot of issues. So thereby, if you are looking into the options of bioengineering, then this is going to definitely reduce, or this is going to be a remedy for most of the hills, at least for Himachal Pradesh, to what I have understood. And currently at IIT Mandi, I am working on these two options on early warning system as well as bioengineering. However, I am going to talk more on early warning in this particular presentation. So again, coming back to the same point on landslide risk mitigation, we have seen good amount of options on structural measures. Now let us see what can we do on non-structural measure. In non-structural measure, if you divide, then this particular options divides into into three options. One is regional, second is zonal, and the last is local. Okay, so regional is like a part of your district. Okay, zonal is probably a valley, should I say, and local is exactly on that particular side where you are expecting the landslide to happen. Okay, so let me take you through three of this. So on the regional threshold, normally we put a rainfall threshold. Okay, so again, if you look into this meteorological department and all, they are going to give you an early warning on based on the rainfall which is received at a particular location. So if you have had options on this, you should be getting some messages from the concerned authorities saying that if the rainfall is going to go for 2 days, more than 2 days, then there is a chance of landslide to happen. So you need to look at it. Similarly, if the amount of rainfall is going more than 100 mm, then definitely again there is a warning issued saying that the rainfall is going to be very high. So there is a chance of landslide to happen. Then next, when we come to zonal, where we talk about data-driven models, there we are going to bring in a lot of parameters from the field. We are going to see a lot of parameters like geotechnical, geological, and all these exploration methods, by which we are going to understand how this data can be useful for understanding the zonal probabilities in your particular location. And lastly, when you understand that one particular site, for example, like Kotropi, or one particular site which is just in your vicinity, where you saw that the landslide is definitely going to happen, or the crust formation or the crown formation has started, there probably we will go for a field scale monitoring by using different techniques which are available. So as a part of this particular work from IIT Mandi, we have started working on options where we talk about what are the options of looking into the field scale monitoring. This has become one of the major work which is done by our particular group at IIT Mandi. So I'm focusing on this, and I'll also touch a little on data modeling or data-driven models. So in this, when you look into what are the existing monitoring measures, then we have seen that there are a huge number of options available at our points, which is one by using GPS methods. There are a lot of global positioning systems which are set by Government of India or in any major authorities who look into how these GPS locations are changing, and accordingly they do it. One major thing which has come in very recently, in fact, after the Uttarakhand disaster, that is LIDAR methods. So they do this particular LIDAR. There is a flying flying options like aeroplane or a small low-lying aeroplanes or something, where the LIDAR is connected with it, and they try to see how the profile is changing over the time, and they will try to see how the distress has been associated with one particular location, and accordingly you will be able to see the LIDAR images associated with this. And then next we have something called as a UAV, which is an unmanned aerial vehicle. These days drone. If you are having drone, then definitely the drone is the one which is going to give you an idea about photographies at different locations, and accordingly you can find out whether that particular location is susceptible to landslide, or if there is a movement which has initiated, then you can also do by using imaging. Then we have something called as radar satellite method, where you have a slightly low orbit satellites which collect the images from on the Earth's surface. So these low resolution photographies by using satellites can be used to understand any deformation profiles which are getting in place. So if I get a time slightly to the end of the presentation, I'll try to show you one of these method, how this can be done. And next we have conventional geotechnical engineering methods, which we talk in the name of piezometers, inclinometers, or geophones, and etc., which can be used to understand the movements happening in the soil. When all these are existing, I'll tell you the major issue with this particular problem is, for example, satellite imaging is very difficult to get because the satellite covers only maximum of 6 days to 12 days. And there can be season when you have clouds, there can be season when you're having fog, there is a season when you have various options, during which these particular methods become a little difficult to be associated, and definitely they are not real time. Once you get the image, then you are going to then you are going to work on the image processing, and then only you will understand whether the movement is going on or not. Okay, so it is not real time, and as I told you again, it's going to dense. And second most important thing in this is the resolution. The satellite is going to give you a resolution on 30 meter by 50 meter, whereas the landslide which may happen in your location can be hardly 10 meter, 20 meter, which may not fall into the grid of your satellite itself. Okay, next, unmanned aerial vehicle. Definitely you need to have timely survey. It is also not real time. It is also going to take a lot of it is also involves a lot of money. And of course lidar itself is the name lidar itself, when you speak, then the amount directly goes into crores of rupees, whereas each lidar image, if you have to take across a particular location, then again this is going to take time. This is not real time, and also a costly situation. Similarly, GPS is also a very costly establishment, for which you need to have again communication from the satellites, and that becomes very difficult. When we talk about the conventional geotechnical engineering landslide measures, then these all are very costly, and few of them definitely becomes difficult. For example, if I want to install a piezometer or something, going on the top of the hill, boring the hill to 10 meters, 15 meters, I'm sure you cannot take a drill 10 to 15 meter drill bit on the top of these particular hills, which I showed you in the starting of the slide. Okay, so to look at, while we are looking at all this, then we understood that they have a lot of issues, and that is why probably not much of them could have come to this particular place for getting into existence in most of our locations. So that's how I myself, when I was talking the same to my faculty colleague from computer science, he gave a very wonderful idea. He says, earlier probably the technology was not so good, but these days all of us carry smartphones in our hand, and whenever you are using Google Map, or whenever you are using these Ola or Uber services, then you know the mobile takes you to that particular location. It knows whether you are going left or you are going right, and what speed are you going. Okay, it gives you so many alerts on the movements. Again, we are talking about the same movements. Okay, so we are talking about the same movements, and it knows where you are moving and which side you are moving and how fast or how slow is your movement. Okay, and accordingly it judges what is the time by which you can reach the other location. Okay, so if this can happen by using this smart technology, then probably there can be a chance of the same technology be used also for landslides. Because when you talk about landslides, we are talking about different movements, like the way in the starting slide I told you, topple, fall, slide, flow, etc. All are movements finally. Okay, so we understood this particular technology, and without taking much time, we now started working on this, where we have categorized this particular location from Mandi district. This is the place I told you, from where the district center is somewhere here and IIT Mandi is somewhere here. Okay, so to come to our place, you have to travel these 15 kilometers. Okay, so these 15 kilometers, we saw so many landslides. So we tried to understand already from whatever landslides happened in the site, we tried to collect information. This is what we call it as data from different locations. So what all types of data we have collected? Initially, we started with the site characterization by using geological data. So we see what type of geology is present in these particular locations. And then we collected samples from most of the locations, almost like 82 locations we have identified, and we collected soil samples, disturbed, undisturbed in most of the natures. And we tried to see how these particular parameters are changing over the places. So we could see there are you can see the maximum and the minimum values of the soils, which is of the parameters which I have received from the site. So you can see there are a lot of parameters. If you are a geotechnical engineer, I don't think there is any requirement to tell you what exactly these parameters we are are talking about. Okay, so these particular parameters, when they have come in, then we have collected from 82 locations and 22 parameters. Okay, so the data we had was 82 by 22. If you give it on any system, then the system starts hanging because of the amount of data which you have fed in. And most important in this is 58 landslide locations and 24 non-landslide locations. So you have a parametric understanding to understand how these particular sessions can be, or how this particular data can be handled. So looking into this particular location, looking at this particular point, we have looked into the data modeling by using machine learning option. And in the machine learning option, we can work out with so much of data by using from different areas. So that's where we have come in with machine learning algorithm by which we can understand or test how this particular thing can be done. However, we had two important parameters here. One is to identify what are the factors which are important to be monitored in the site, and two, how these which of these particular methods can give us what confidence on how whatever we are trying to get up from this particular solution. So based on this, we started doing machine learning. So if there is anyone who is attending from computer science, for them this is like probably they should be yarning at this particular point of time, because they know all of this what I have presented. So we talk about them in the terms of true positive rates or false negative rates. Again, the same which you should be learning from COVID as well. We always talk about the testing in true positive and false negative. So this is all about the test which we try to do. We have performed different types of models to understand the accuracy, the specificity, sensitivity, and other analysis which are used to understand how good are these particular parameters or how these particular models are working with respect to the field, which from the data which we have collected. So this particular analysis, we can say that this goes into data-driven model, because I have did it over a location and over different points and different different parameters. So lastly, we found that there are some parameters which are giving us a very good understanding on the susceptibility of landslides at a particular location. Okay, so the combination of these particular parameters are giving us a very good idea on the chance of happening of a landslide in the site. So they are the first 5: relative compaction, porosity, moisture content, and permeability, and angle of internal friction. Slightly later, as a geotechnical engineer, we can understand that not all the parameters are virtue, or they have their own operations. So we try to understand the combination of how this particular works. So we could understand that if at all I have to select a particular location where I have to point my sensor, then probably I will use these parameters on relative compaction, porosity, saturated permeability, and internal friction. Whereas at a particular site, if you want to measure what is that particular parameter which is important to understand the chance of a happening of a landslide, then it forms as the field moisture content, because as the moisture content changes, the compaction changes, the permeability changes, as well as the strength of the soil by friction also changes at the location. Now, like this, there are various parameters I've identified in different parts of the country, in different parts of the world. Okay. However, we see that there is one particular parameter which has been bugging in most of this particular understanding, which is natural moisture content. So, which says that if you follow the moisture content, then you are getting a good idea about the susceptibility of this particular place in a landslide. So, this paper is currently in the stage of acceptance, and it should be falling out soon for reading. So based on this particular understanding, as I told you, that the moisture content becomes most important. So that's where we have started looking at what is the type of the analysis we have to do to understand the landslide, or to understand the happening of a landslide. So for this, as I told you, first what we need is to find out the displacement or the movement of the soil. So we have put in accelerometer sensor. So this accelerometer is also called as gyroscope. All of your mobiles are having this particular option or this particular sensor already embedded in your mobiles, which tells you which is the one which helps you in tracking or moving. When you're moving, this is the one which tracks your movement. The next, all the landslides happen because of the rainfall, at least in this particular area. So that's why we need to have an idea about what is the rainfall happening in the location. And definitely we found out that soil moisture is the important parameter. Then apart from this, we also try to understand what type of forces are getting developed in the soil, whether they are drain forces, undrained forces, saturated, unsaturated, and all. So we are also trying to get an idea about it, the pore pressures, by using force sensor. So the same force sensor again is in your phone. The capacitive touch, whichever you call it, has this particular sensor embedded in the screen. That's where it understands your force. And then Apart from all this, we are also collecting weather parameters, which is light, temperature, and humidity, which is again an indication, which gives you an indication of how this particular slide or how this particular basically on the prediction of this particular movements which are happening in the site. And all this data we are trying to collect by using this MEMS sensors are integrated with a microcontroller board, that is your Arduino board, to say microcontroller board, and that microcontroller is put in with your GSM module, and this GSM module collects all the data and uploads into the cloud. So we had developed a simple algorithm where all your parameters which you are developing goes into the microcontroller board, and from the microcontroller board it goes into the GSM, and in the GSM we have modeled a thresholding algorithm, and in this particular thresholding algorithm we try to see, or we try to compare whatever data is coming. So we have a comparison algorithm which goes like this. Okay, so when the data comes in, it sees whether the data is falling here, whether the data is falling here, whether the data is falling here, here, or here, or here. Now what is this? This we call it as error. Okay, this we call it as range. This we call it as low. This we call it as medium, and this we call it as high. Okay, so when the data comes in, then it compares where is this data falling. If it is an error, it is thrashed. If it falls in the range, then it keeps collecting the data. Once the data is collected, then it sees whether it is falling into low, medium, or high. If at all it is low, then we release if it is going to high, then we are going to release an alert based on different situations. And this particular algorithm, whatever we have developed by using these sensors, we could apply for a patent here. We could apply for an Indian patent. And because we did not find any of this particular solution already existing across the world, we immediately have upgraded to do an international patent. So these patents are awaited. We are hearing it soon. So in the meantime, we could, by using the by the help we received from the landside from the district administration from Mandi district, we could take these particular locations into, or these particular sensors into the field, where we could set up our station, which looks something like this. All our sensors are in this box, which are powered by the solar power, and our rain gauge is on in the arm of this particular thing. And you can see the wires which are going here are carrying the sensors into the ground, where we embed it into the ground to look into the moisture content, acceleration, moisture content, and all the other parameters. The temperature sensitivity and all are fixed along with the solar panel itself, so that they can collect the ambient temperature collection. So once with all this data is collected, it is put into the cloud. It compares, it does the data analysis, and if at all it is going, if at all it's crossing the threshold as I discussed, it will be either raising it as a form of an alert, or if you can have a mobile based application, or at the site itself we are also having a hooter and blinker system by which we can alert the people. So based on this particular location, now we have started looking into the machine learning at this particular at different locations. And in the machine learning, we are seeing how best this particular data can be dealt with. And in machine learning, normally we try to classify the data into testing data, training data, and testing data. And we try to work out different types of analysis, such as multivariate, univariate, multivariate, and various neural networks associated with understanding of this particular movements, or to bring it into the prediction scale. So by which we can able to predict what is going to happen in future by using the same methods, which are like univariate or multivariate. And in this method, so for example, if I show you this particular data, so we collected this data over the time, then split it into this part is training data and this part is testing data. And so in the training data, we try to now look at different models, bring different models, and see how best we are able to understand, or how best we are able to read the data. So you can see typically in few locations, you will see two different lines. Okay, one is blue and the other is red. The blue one is the displacement which was happening at the site, and the red is the one which is predicted by using our model. Okay, so to train or to look into this particular data, we call it as a training model, and it is as a error parameter. So we try to do RMSE, that is mean standard error. So RMSE is the one which gives you what is how good is your model working. So it says that there is a slight amount of error associated with our movements, but whereas in the testing also it clears. So we need to work a little more on this particular idea to understand how best can we predict the model by using different analysis. So now we have many locations. So for example, in this particular thing, you can see that our prediction has gone a little better, though still you can see a lot of variations in the movements happening in the site. and the movements which are predicted by our particular sensors by using our own models. Okay, so sorry, yeah. So we are increasing our stations to get better of our method. So if you can see the RMS associated here, now our error has gone almost to like 0.1%. So we can tell you that at a point I can give you almost like 99.9% prediction at a given location. Again, this particular location, all this particular data which I'm talking about is all time dependent. Okay, and the more amount of data I'm going to have, the more amount of analysis I'm going to do, and the betterment in the results I can give you. So at a particular scale, when we have recently published a paper in a major journal, in this we could publish that we are able to bring it on weeks scale when we had a data which was running for more than 2 years at a particular location. Okay, so based on this, these are few of our observations. Of course, we have been discussing much about it, and of course, as I told, we have good amount of patents and publications from this particular work coming up. And before I say thank you, should I say that I have a quick video to show you in case I have some time, Dr. Mahesh.
Thank you very much, sir. If any participant having any question, they can ask the sir.
So just a minute, Dr. Mahesh.
Participant having any questions, they can ask.
So, Dr. Mahesh.
Yes, sir, speaking, sir.
If I'm audible.
Yes, sir, you are audible, sir. Yes, sir, you are audible.
So I actually have a quick video to show. If you
yes, sir, absolutely, you can show that, sir. You absolutely show that.
I can show it. Thank you.
Dr. Uday, can you hear me?
Yes, you're audible.
Okay, yeah, please tell me.
Okay, I was just looking for an option if I can share you a small video which can give you a more
yeah, definitely
about the sensor which
you can directly I think share from your side. I think it will work.
Yeah, I should be doing it. So just give me a minute. I'm just taking out the
share along with the computer audio. Please keep that in mind when you are sharing. So computer audio also has to be shared together, right? Okay, thank you.
Just doing it. Sure. Okay, so this actually video has been done by the world famous to say the BBC Click, who have visited IIT Mandi. They spent
Dr. Uday, your video is still not
ready. Yeah, it should be coming in a minute.
Okay. Now, yeah, it's there, right?
And I don't know, it did not ask me. So can you just confirm if you are able to hear it? Are you able to hear?
Yeah, we can hear it. Yeah.
The voice of the video.
Right. Voice is also coming.
Oh, sorry.
हिमाचल प्रदेश के हैं। हर साल तेज बारिश और लैंडस्लाइड्स के कारण पहाड़ी इलाकों में रहने वाले लोगों को काफी परेशानियों का सामना करना पड़ता है। कई लोगों की जान भी चली जाती है। पर क्या नई टेक्नोलॉजीज का इस्तेमाल कर हम प्राकृतिक आपदाओं का सामना बेहतर तरीके से कर सकते हैं? स्वागत है आपका क्लिक में। मैं हूं उदित मेहरा। कार्यक्रम में आज देखिए एक तकनीक जो भूस्खलन से पहले दे सकती है वार्निंग। ऐसी एनिमेटेड मूवीज। ये तस्वीरें हिमाचल के मंडी की हैं। यहाँ कुछ ही मिनटों में मौसम किस ओर करवट बदलेगा इसका अंदाजा लगा पाना बेहद मुश्किल है। क्लिक की टीम जब मंडी और आसपास के इलाकों में पहुंची तो मौसम सुहावना था, लेकिन अगले 2 दिनों के अंदर ही ये रास्ते हमारे लिए खतरनाक साबित होने लगे। करीब 48 घंटों की लगातार बारिश के बाद कई जगहों से लैंडस्लाइड की खबरें आने लगी। रास्ते से गुजरते हुए ये डर लगातार बना हुआ था कि पता नहीं कब कहां से कितने बड़े पत्थर आ जाएं। हर साल पहाड़ों के बीच रहने वाले सैकड़ों लोग लैंडस्लाइड्स में अपनी जान गंवा देते हैं। क्या इन्हें बचाने का कोई तरीका है? आईआईटी मंडी का दावा है कि उन्होंने एक ऐसा सिस्टम बनाया है जो खतरे से पहले वार्निंग दे सकता है। मंडी में 10 ऐसी जगहों पर जहां लैंडस्लाइड का सबसे ज्यादा खतरा है वहां ये डिवाइस लगाई गई है। इन्हें सड़क पर लगे अलार्म और लाल बत्तियों से जोड़ा गया है। जमीन में होने वाली किसी भी तरह की हलचल को ये मशीन रिकॉर्ड कर सकती है। किसी भी तरह के खतरे की स्थिति में यहाँ लगे अलार्म बजने लगते हैं। यहाँ से गुजरने वाली गाड़ियों के लिए ये एक सिग्नल है कि यहाँ लैंडस्लाइड्स हो सकते हैं और वो आगे न जाएं। जिस सेंसर का इस्तेमाल आपके मोबाइल फोन में लैंडस्केप और पोर्ट्रेट मोड को समझने के लिए होता है, ये मशीन उसी की मदद से मिट्टी में होने वाली हलचल को पकड़ती है। विमानों में भी मूवमेंट ट्रैक करने के लिए इसका इस्तेमाल किया जाता है। इस मशीन में एक जीपीएस मॉड्यूल है जिसकी मदद से जिले में बने कंट्रोल रूम में भी ये मैसेज भेजे जाते हैं। वहां बैठे लोग ये फैसला करते हैं कि क्या कदम उठाने चाहिए। इस मशीन में कई सेंसर्स भी लगे हैं जो बारिश, तापमान और हवा के दबाव से जुड़ी जानकारियां भी जुटा सकते हैं और इनकी रियल टाइम मॉनिटरिंग भी की जा सकती है।
करीब 1 इंच पर साल के हिसाब से अभी भी हिमाचल बढ़ रहा है या हिमालयास बढ़ रहा है, तो इसकी वजह से एक टेक्टोनिक मूवमेंट एक आता है। और इसका जो ट्रिगरिंग फैक्टर जो बोलते हैं ये होता है बिकॉज ऑफ दी रेन, जहाँ पे बारिश होता है इसकी वजह से यहाँ पे भूस्खलन का ज्यादा प्रॉब्लम बनता है।
लेकिन क्या इस मशीन को बड़े पैमाने पर इस्तेमाल करना मुमकिन हो पाएगा?
इस मशीन
What does AI mean for business leaders and for business managers? How can it be converted into value and opportunity?
इनकी कीमत सिर्फ 20,000 रुपए है और ये 100th ऑफ अ कॉस्ट है, 1/100 है ऑफ जो हमारा कन्वेंशनल मॉनिटरिंग सिस्टम होता है। इसकी कॉस्ट करीबन करोड़ों में होती है।
आईआईटी का दावा है कि आर्टिफिशियल इंटेलिजेंस और कई दूसरी तकनीक की मदद से इस सिस्टम को और बेहतर बनाने की कोशिश हो रही है। इससे मिलने वाले डेटा को भी स्टडी किया जाएगा। इससे आने वाले समय में न सिर्फ यहाँ बसे लोगों और पर्यटकों के लिए एक बेहतर प्लान बनाया जा सकेगा, बल्कि पर्यावरण की सुरक्षा के लिए भी साबित होंगे। किसी डिजास्टर या एक्सीडेंट के वक्त उस स्पॉट पर पहुंचना बहुत मुश्किल है। ऐसी परिस्थितियों से निपटने के लिए जापान में एक रोबोट बनाया गया है जो उन जगहों पर जा सकता है।
Okay, I think the video was good, was full.
Yeah, I think it was perfect. Yeah, I think there was a little delay, but that is very much understandable, right?
Okay, and otherwise also the video is available on YouTube if at all somebody wants to.
Right, you can provide the link of the video also in the chat box.
Sure, I'll do it right away.
So are you done, Dr. Uday?
I'm done.
Okay, so thank you very much for because there was a lot of demand to cover this topic of early warning and mitigation, and then some Himachal region into this talk. So I think you have very much justified it. Thank you, sir. Thank you for taking out time. Now we can take questions from the audience now.
Yeah, sure.
Yeah. Dr. Uday, can you I was just wondering, yesterday also I was discussing with Dr. Shantanu Sarkar also, can we also try to install rock sheds? Because you might have seen, recently this Kinnor casualty that has taken place, right?
Yes.
So So, how's your what's your perspective about this? What do you call it? Rock shed concept, an installation of it. Is it costly very much?
Yeah, it actually is. Should I say very costly? And definitely, again, the cost can be reduced by using even more understanding on the geology, especially. Most important point here is to understand what is the scope of controlling the rockfall which is happening at the location. And again, if we can reduce the velocities by which the rock is getting entrained, then yes, the cost can be reduced by a good amount. We have submitted a small proposal initially to NHAI, but however, it seems again the cost always runs out of the project cost which is allocated. So that's where we missed actually.
Okay, that sounds good. And because yesterday Dr. Maria was there from Italy, and she was, also talking about landslides. But the interesting thing that I noticed there was they were having, landslide triggered because of some volcanic, activity.
Okay.
And also, the flow that takes place in case of that volcanic sort of thing is something very. It's like a flow. It's not a landslide. It just flows.
Yes.
Right. And but at the same time, what we see here in the Himalayan regions, that is totally different. So yesterday also we were discussing that can't we come together to come up with a landslide inventory, different type of, not landslide word, but different type of slides that takes place throughout the world, and try to document it together.
Right.
Based on their characteristics and proposed remedial measures for the same.
Yes. Yeah. Actually, should I say that when I started my work in Himachal, I initiated from this particular line. Okay, but again, somehow people and also the funding agencies and all, they're always interested in something of technology more than a particular study as such. Okay, so should I say I thought that okay. Probably let us show the technology, and whenever the technology is challenged, then definitely we can come back to the study. That's where currently I have also recently given a proposal to a funding agency in DST, where I'm trying to look at this particular study. Apart from this, of course, there are a lot of interesting studies which can be taken up depending on, again, various participants whom we have here. The another point is the bioengineering. You know this again very well. So what type of plants, what type of trees can be really of help in this particular environment? Okay, especially when you're talking about this flow type of slides and especially the debris movement and everything. I think all this can be taken care again by most part of the nature itself by these plants and roots. So yes, there are good amount of studies which can be done in this particular line.
Right. Thank you for that. So another thing, yesterday also I asked Dr. Shantanu Sarkar, because in Himachal, the landslide or this sort of disaster activity is now increasing day by day.
Mm-hmm.
The number of casualties that has taken place this year are already more than the casualty that took place last year. And one of the reasons for that is human intervention in terms of construction activities and the widening of roads. So the idea was, whenever any construction activity or any project is going to get implemented, then we always have in our mind that we have to submit one pre-feasibility report or detailed project review report, right? Whenever a project is being, the idea comes up. So when a widening of the road sort of a project is coming up, in these hilly terrains, especially in Himachal and Uttarakhand, don't you think that it's also very necessary to come up with a detailed project report when regarding when this road is going to be constructed, how much it's going to impact the slopes, and how many landslides are going to get triggered because of that, right? And how much it is going to cost the state or that agency to mitigate those unstable slopes. So that was another thing that we were discussing yesterday, because the cost of the project is, let us assume 50 crore, 100 crores, And every year we have to invest a lot of time in stabilizing those slopes which were made unstable of that construction activity. And finally, whenever we talk throughout the world with any expert on landslide, they always say the best solution for landslide is prevention of landslide, right? To prevent it or to avoid taking that path where it can get triggered up. So what is your take on this thing?
Yes, actually, this is something which have been pending from my side for last almost like 6 years now. My initial discussions with agencies like NDMA as well as SDMA of Himachal Pradesh, we always wanted to do this particular job as soon as possible. And luckily, after the funds which we received initially in 2018, we also conducted few workshops which we are able to make people understand on how exactly the major problem. Again, let me tell you, Dr. Mahesh, on this is whenever we are talking about all this, there are two things involved. One is funding, and the second, the most important, is the manpower. So here it's very difficult for us to get to say any common people or someone who is probably staying for 2 years, 3 years, 5 years working with us, and then they're looking for their own jobs and their own settlement. I thought it would be a good idea if, with the collaboration from the state government itself, if we can bring in an active agency like PWD or GSI or someone who can get settled in Himachal Pradesh, and then it's understood, right? It's a multidisciplinary aspect. It's not 1 or 2 or 5 or 10 people can close the things. We need hundreds of people and the major manforce on this particular aspect. So that's where I'm interested again in collaborating with various agencies. And in fact, we are also talking on the same, both of us. So it should be again a very good coordinated team. And definitely this is possible. It is not at all that it is not possible. In fact, I come to hear a lot of case studies through NDMA, the amount of work which is done by Uttarakhand and now Mizoram and Nagaland. I think they have already come into race. They are submitting so many detailed project reports on the landslides and all these particular things, which I don't know whether should I say that it's something like a state like Himachal Pradesh, where we have NIT, where we have IIT, where we have universities, where we have so many established government agencies and everything. We are somehow lagging in this particular line. I think we need some push. The moment this COVID and everything ends, we should get ourselves on this particular stage. Otherwise,
I perfectly, I can't agree more than it. But I definitely, can assure you that we have to take it up now. And definitely, day before yesterday and yesterday also in the evening, we had a conversation with the authorities, and they were saying that now they are, because of these large number of casualties this year, they are also getting very much serious now. Yes. So I think IIT Mandi, NIT Hamirpur, and Himachal Pradesh University Shimla, because of its location, can play a very much significant role into that. And definitely, I think that center thing is also going to come up soon. So yeah. So I think we are on it, and we are looking for a positive outcome. So thanks for that. So dear participants, if you have any query, you can raise your hand, and then I can unmute you. Then you can ask your question. Please go ahead. Yeah, Mr. Sridhara is there. He has a question. Yeah, Mr. Sridhara, you can go ahead, sir, please.
Yeah, thank you. Am I audible, sir?
Yes.
Yeah, you are perfectly audible.
Yeah, Uday, sir, thank you so much for the talk you have given us. And my one question is, when you are doing this multidisciplinary task, that is actually you are learning machine learning and going with algorithms and deep learning process or big data and all. What are all the challenges you face? One is interacting with the other part, that is maybe from CS or from electrical or else whatever that. And what is your learning process from basic geotechnical, and you are actually moving into the other disciplines? What are all the learning process and the challenges you face?
Yeah, this is a very interesting question. Thank you very much, Mr. Sridhara, for the question. First of all, so of course, luckily being in IIT, normally we have a very different culture altogether. So should I say that the first part of your question, where we're talking to people, is very, very easy for us. I mean, my own colleague who sits just beside my room. So if I have to knock, I just have to talk to the next person who is sitting in my office. So that becomes easy for us. And the other side of the story is always interesting. For example, if you are looking into geotechnical aspects, initially we were talking about very simple lab tests. So I mean, should I start on the point that our own father of soil mechanics, Terzaghi, comes from mechanical engineering? So I mean, we should understand probably there itself that this particular part is not confined to civil engineering. Only the application is for civil, whereas all people from various points can get into this particular field called geotechnical engineering. Not only geotechnical now, these days of course civil. So when we talk about the same, when you're using FEM analysis, there is a lot of mathematics. Okay, when you're using nodes and coding and everything that comes from computer science, people have learned this, and I'm sure if we get an opportunity, normally in IIT Mandi we boast on this, that we do more coding than a proper computer science faculty. Okay, we want to have a coding competition on this particular aspect sometimes. Okay, so we keep pulling our tails. That's a different story altogether. But yes, the major problem with this particular concept when you're talking about machine learning, artificial intelligence, is all about data. Unless you give me that huge data, you cannot work, or none of your data, none of your none of your model, none of your thing will work or will run to the requirements what you have. So you can see that's what I told you very clearly in the presentation, that we have selected a site which had 22 locations and 82 locations, and from each of the locations we conducted 22 samples. So you can, if you are a geotechnical engineer, you can understand how much time it takes for us to do all these tests, starting from specific gravity to particle size distribution to liquid limit, plastic limit to direction tests. Okay, so the data development in all this becomes a major serious concern in most of this particular analysis. So again, we are looking for options how we can cross over this.
Yes, sir.
If I could answer all your questions, or
yes. Thank you. I think this your approach only actually will take us to the near to the natural phenomena. This probability approach or else deep learning approach. But with the traditional approach, I don't think we go near to the phenomena that happens due to nature. Thank you, sir. Thank you, sir.
So that might not be a correct point actually to say otherwise, because if that was not possible, then I don't know, even if I get data, I don't know how should I do a slope stability analysis. Okay, so yeah, everything should be context. Yes, it's good that there are a lot of people who are doing this, and we are trying to see how we can go further, a step ahead of this. Thank you.
I think that's the reason you are actually going with many patents. Thank you. Thank you so much.
Yeah, thank you very much.
Thank you.
Yeah, thank you.
Thank you, Sridhar sir, for your question. And I must say that you are one of the most active participants of this workshop. Thank you for that. Yeah.
Actually, so I think I have few questions, if I can quickly come out.
Please.
By Dr. Deepak, who has given, the Landsat warning installed by IIT Mandi has become defunct at few locations. So I'm very sorry, sir, for that, because that particular incidents which has been given in the newspapers have come in because they did not have an idea. We gave the indication to the district administration that we have started testing the sensor, so we had to check before the monsoon season. So we have simply fired out the we have simply taken out the hooters and blinkers just to make sure that the sensors are working in the site. And then I think this has become a negative on the news, and they have published about this. I am very sorry for this disturbing news. And then the next question is interesting from you. Is there any study correlating the earthquake and landslide hazards, particularly in Himalayan regions? Again, I mean, the answer should be more or less the same which I have been giving to Dr. Mahesh. So we are still in the process. So currently we had a success on simple landslide, rainfall induced landslides. Now with my friends, the one who just presented before me, Dr. Ashutosh, and I have one more friend from Dr. Mahesh Reddy, who comes from the earthquake and soil dynamics related area. So we are now looking into aspects of correlating this particular point of earthquakes and landslide, and one of the proposal is with the funding agencies. So if we get that money, I'm sure we are on it otherwise. So the first study we are trying to take up is from Shimla district, from the town of Shimla, where we expect that the hazard of Shimla for landslides as well as the earthquake is very, very high. So we are taking it up, and quickly in the meantime, we also have a publication in pipeline where we have already done this zonation on earthquake induced landslides for this Mandi area, just to give you a small idea about. Yeah, I think these are the only two questions I have.
Yeah, otherwise also they can always reach out to you, Dr. Uday.
Sure, sure, very much.
I think you would always love to interact with them. So my request to all participants is that if you have any other query, besides it, you can always write to Dr. Uday. You can also contact him, and both the things are available on the website.
Yes, and
of IIT Mandi.
I'm also dropping my email ID to the participants so that
Right.
everyone has to do it. Luckily, because being in IIT, our email ID becomes simple. You remember my name Uday. It is uday@iitmandi.ac.in. So it goes very simple.
Right. So thank you, Dr. Uday, for your time, and thank you very much. Thank you very much, sir. And we'll be in touch. And definitely next time, I have promised Professor Chaudhary also that we'll be hosting you in person in Shimla for a workshop.
That will be my requirement as well. Thank you.
Sure, and definitely it will be fulfilled from my side.
Sure. Thank you very much, Dr. Mahesh. Again, a wonderful audience and good questions also from different people. And I wish you all major success and learning from this particular workshop, which is very well coordinated by Himachal Pradesh University, and especially by my colleague, my friend from IIT Bombay, Dr. Mahesh Sharma. Thank you.
Thank you, sir. Thank you very much.
I will be leaving the call then.
Yeah, please. Okay. Thank you.
Bye-bye.
Bye-bye. Okay, so dear participants, our next lecture will be delivered by Dr. Aninde Pine, who is a senior scientist at CSIR Central Building Research Institute, Roorkee. And the topic of his presentation is slope stabilization using different reinforcement techniques. So he will be joining. We have a time. You can take a break, but my request is that you please do not log out of the Zoom session, and then because Zoom is taking the attendance automatically. So if a person leaves out, then then it becomes difficult for that automatic transaction to go ahead. So my request to all of you is to remain muted in muted form and join back by 3:30 p.m. because Dr. Aninde Pine was traveling today early in the morning, and his flight got delayed. So I think his session will start not at 3:15 but at 3:30. So my request to all of you to please be there in time. Thank you. And if you have any other query, you can always write to me. You can always text in the group. You can always message me. You can always put your query here also in the chat box. So it would be great. And again, I would like to remind all of you that only those participants who's having attendance more than 80% and are scoring more than 60% in their quiz will be given this AICTE certificate. Because we don't have any role of giving certificate, it is directly given by AICTE only. So my request to all of you to keep that in mind. To all those people who wants to get certificate of this workshop or program. Thank you very much to all of you. So we'll be joining back at 3:15 p.m. for our next session. Please don't leave. Please remain part of this online Zoom program. You can keep yourselves muted and take a break. Thank you very much. Fine, sir. Can you hear me?
Good afternoon, Mahesh. Can you hear me? My audio is clear.
Yes, sir. Yes, sir. It's perfectly clear. Thank you. Thank you for getting connected. Yes, sir. Thank you. So I think you can also hear us, right?
Yes, it's clear.
Okay, okay. So, sir, we'll start at 3:30.
We'll start at 3:30. Just give me 2 minutes. I will arrange everything.
No issues. No, you take your time. 6 minutes are there. You take your time.
Thank you.
I will start at 3:30. Thank you.
Okay.
So, good afternoon to everyone. I hope you can hear my voice clearly. We'll be starting our next session at 3:30 p.m. We have with us Dr. Anindya Pine. So he has already joined. I hope all the participants have joined back by 3:30 p.m. Thank you. Okay, so I think Sir has also joined us back. Good afternoon to Dr. Anindya Pine and to all the participants. I hope all have joined back. So we have with us our speaker, Dr. Anindya Pine, Senior Scientist, CSIR Central Building Research Institute, Roorkee. The title of his presentation is Slope Stabilization Using Different Reinforcement Techniques. So thank you, sir. Thank you, first of all, and a warm good afternoon to you. I knew that already that you were traveling, but yeah, that happens every time that there is a flight delay. So thanks for accommodating this lecture in your busy schedule. Thank you very much. About brief introduction of Dr. Anindya Pine. Dr. Anindya Pine has done his BTech in Civil Engineering from India. He obtained his master's and PhD in the field of geotechnical engineering from Academy of Scientific and Innovative Research, New Delhi, ACSR, which we call in short, New Delhi, India. And he is a recipient of Innovative Student Project Award that is given for the PhD work he received in the year 2017, was given by Indian National Academy of Engineering, INAE, which we call in short. He has also received ICMAC Excellent Paper Award for the year 2017, given by IACMAG. He has been nominated to represent Indian Geotechnical Society as a corresponding member of the International Technical Committee, TC 207, on soil structure interaction and retaining walls of the International Society for Soil Mechanics and Geotechnical Engineering, ISSMGE, for the term 2018 to 2021. His primary research interests include earthquake-resistant design of geotechnical structures, probabilistic analysis of geotechnical structures, site-specific ground response analysis, rock mechanics, slope stability analysis, and application of machine learning for pattern recognition problems. He has published more than 25 journal papers and is an active reviewer of more than 20 SCI journals. So with these words, Dr. Anindya Pine, I again welcome you it would have been great to host you in person in the beautiful hills of Shimla, which is still pending for next time. But still, thank you, sir, for taking out time. I understand that you are very much busy these days in personal as well as professional life. So thank you once again. Now over to Dr. Anindya Pai. Thank you, sir.
Thank you, Mahesh, sir, for such a nice introduction. First of all, I'm really sorry that I'm 15 minutes late. Actually, it is because of flight delay. My flight had some technical issue, so it got some delay, 1.5 hours, something like that, because of the Calcutta night time. But now I'm ready. So I will share the presentation then.
Yes, sir. Please go ahead.
Okay. I think now my slides are visible. My slides are visible.
Yes, sir. It's fully visible.
Okay. So I will take roughly around 1 hour and maybe 20 minutes or so, 20-25 minutes, and so that we can have some time for discussion, because that is very important. So because it is not a one-way process that I keep on talking. So if I know about your problem, or what kind of problem you are these days are dealing with, or you are trying to solve, so that it will be helpful for me also. That becomes a learning experience for me as well. And maybe I would like to get associated with you, or maybe in some other ways I can help you. So basically, first of all, I'd like to thank Mahesh, because for giving me this opportunity to interact with so many participants from all over this India, not only from Himachal. So today I will be discussing mostly on slope stability aspects using different reinforcement techniques. Now we all know that now these days you have seen that there have been many unfortunate incidents of large landslides or large rock falls, starting from Kedarnath 2013 in our Uttarakhand to the recent one in Himachal Pradesh, where many tourists got even trapped into it, and even some of them got died. Some of them died actually. So, and also there was a major infrastructure threat. One bridge got collapsed. We have all seen that video that was circulating around the WhatsApp platforms. So, these kind of slope stabilization problems are now very recurrent. Like not only in Uttarakhand, not only in Himachal. Now it has started in Kerala, Tamil Nadu also, even, and also Maharashtra. Earlier, Kerala, Maharashtra, Tamil Nadu didn't had so many cases. Now, with the developmental activities like hill cutting and all the other related activities, and also we are increasing the population in the hilly region also. So we need more space. So because of that infrastructure development, if we can take the nature with us, like with properly stabilizing or understanding the slope, that how it will behave if you construct something, or if you are disturbing the slope. So with keeping all those aspects, if we can progress, I think that will be one of the best solution, I can say, or long-term solution, both from us, from our side of view, like from the developer side of view, and from the nature point of view. So keeping in this view, I will be discussing different slope stabilization methods. In some of them I have worked extensively and currently also working. In some of them I know, but I have not worked extensively. Maybe I will work in maybe coming 2 years. And some of the topics, even Mahesh is also expert, I will say, because he has done in one of the topics like soil nailing, has contributed significantly in terms of new nailing technique and new type of nails and all those stuff. So I have been familiar with his work professionally and personally, both for last maybe 7 or 8 years. So it's been long time. So I will start my presentation. So basically, first of all, I would like to thank my organization, Central Building Research Institute, and also the parent organization, which is CSIR, Council of Scientific and Industrial Research. And also, some of them you may not know, CSIR. Nowadays, it is in talk. So ACSR is an organization which is a part of, not part, but it is a kind of, you can say, supplying the actual manpower resources to CBRI or the CSIR labs, which are helping us to thrive in the research, because without good student, we cannot thrive. Right? So I will also like to acknowledge ACSI in a big way. So this will be the outline of my presentation. First of all, I will be, I think, Mahesh, I think there are people who are not from civil engineering, I mean, not from geotech also, right?
Yes, sir. Yes, sir. Yes.
Some of them
They are
might
from
be
civil engineering.
but
Yes,
maybe
sir.
structures,
Yes.
materials, transport, and all, right?
Right, sir. Right, sir.
So in that case, that's why I have kept this slide like ground engineering, because all of us may not be aware, but I will try to give you an idea, like what is the ground engineering actually. Then what are the type of reinforcement techniques I will be talking about. Then I will talk about the slope instability. Then one of the most used method for building a reinforced slope is the reinforced earth retaining structure, or it can be wall, it can be slope, like that. So I will be talking about in detail about this stability of the reinforced earth retaining structure. It can be wall, it can be slope. So all those things in detail I will be discussing. It will also have some part of my research work also. Then I will be talking about the soil milling technique. It's also a very versatile technique apart from the reinforced soil retaining, earth retaining structure. So over that I will also be elaborating you through pictorially and through in little detail. So we all know that because we are civil engineer, in our BTech undergraduate we have all studied like geotechnical engineering, like foundation engineering and all those things. So I will not repeat much. So basically we basically deal with the natural materials like soil, rock. So related to that, it is a discipline, I would say, which incorporates number of sub-discipline or number of people also involved in this discipline, starting from geology, hydrology, hydrogeology, geophysics, geotechnical engineering, obviously, civil engineers, obviously. So it is a vast branch, and nowadays, with increase in the interdisciplinary work, this has become very necessity that you have little bit of knowledge or idea or the basic understanding of all these fields like geology, hydrology, some understanding of geophysics also is very necessary. Now we all know that what is the earthwork. So earthwork basically have three components. I'll go very slowly and start from very simple things like what is excavation, filling, and compaction. So we all know that excavation is required when we want to go below or we want to start our foundation, when we want to go below the natural ground level or existing ground level. Then we fill it with depending on the what type of density we want, or sometimes there are low-lying areas that we want to build, so we fill it up with earth materials. And compaction. Compaction is one of the important aspects of geotechnical engineering, because without proper compaction, there can be a lot of problems. Now, this is related to earthwork. Then we come into the reinforcement, because I am going to talk about the reinforced soil retaining structure, right? So reinforcement, we all know, especially the structural people are very much familiar with this. There can be different type of reinforcement. Some of them I have listed. Now there are now different new reinforcements are also coming up, like starting from steel, glass, concrete, fiber, wood, aluminium, rubber, thermoplast. Number of things are there. But what I will be talking in detail here is basically the geosynthetic reinforcement, which are made of HDP, high density polyethylene or high density plastics. That can be of different forms, like in forms of strip, anchor, clank, chain, rope, and many combination of these. So now people are coming up with different combination of these different shapes or different structural forms, like combined with strip, combined with anchor, or chain combined with anchor. There are many combinations people are trying. So this is all about the reinforcement. Now, the concept of basically the reinforced soil retaining structure, because we know that soil is very weak in tension, so it cannot take tension, right? It can take compression. That's it. So when the natural slope is not stable, what we try to incorporate, we incorporate some of the reinforcement elements. So in the right-hand side slide, you can see some of the horizontal lines, right? These are the reinforcement that have been inserted into the slope. So this reinforcement improves its strength and stiffness both. And in detail we'll discuss subsequent slides. So left hand side showed a photograph of typically how a reinforced load look. So there are basically 2-3 components very essential. Like first, the reinforcement itself, obviously. The second is that we need to take care of the water, the water pressure basically. If there is a rainfall heavy area, so water pressure we need to very carefully taken care. Should be taken care. And the drain is the one of the most important component that we give the least importance. So that is very dangerous, I would say. In most of the cases, I have seen that a drain have been a critical problem or a problem which people do not give attention to. But it should be given the most attention, I would say. So the geosynthetics, I will be taking about today the geosynthetics, right? So it's a class of different type of reinforcement HDP, high density polyethylene material. So depending on the shape and its utilization, it has been categorized into different names. Okay, so but the whole of this branch is this bunch is called the geosynthetics. So it starts from the geotextile, then geogrid, then geonets, geomembrane, geosynthetic clear liners, geofoam, geocells. These are the latest variants, and geocomposite, like a combination of any or 2 or 3 of these. So that becomes a geocomposite. So people have came up with different shapes, different use, depending on its use basically it has been, and also the shape it has been categorized. So we'll go a little bit in detail about this type of geosynthetics. Geotextile is one of the most used geosynthetics, I would say. So it looks like the word you can understand. From the word, the name itself, you can understand geotextiles. So it kinds of a fabric kind of a textile means it comes in terms of a rolls, right? Rolls of geotextile. It behaves a cloth kind of a thing. So basically, they are very less susceptible to biodegradable because these are synthetic material, obviously. They are extremely flexible. You can bend it or you can give it any shape you require. These are porous. So basically, we use to build drains, or if you want to filter the water, or if you want to stop the migration of finer particles to clog the pores, then we use this kind of geotextile. So you can see one of the example I have given here, that somebody wants to build an underground drain. So what he has done, he has wrapped the whole material with a geotextile. Inside that there are gravelly kind of moram kind of a thing, and then there is a drain, perforated drain. So the water comes in, the finer particle doesn't come. So this geotextile arrests all those fine particles, and it doesn't allow it to percolate. There are several applications, but I am giving just an overview that how things are going. Now, about the geogrids, this is one of the other variant of geosynthetics which are very much in use, or widely used, or you can say massively used. So it can be different forms, like from the name you can understand. Grid means it has a pattern, like it can be uniaxial, like in only one direction. It can be bidirectional, like square kind of a thing, the bottom photograph, see. So there can be different variants like of geogrid. So the main purpose of this geogrid is to provide the tensile strength into the reinforced soil. So the tensile strength will be carried out by these geogrids. Now we have geonets. So basically, these are other variants of geogrid, you can say. It comes in a roll. All of this material mostly comes in a roll, so because it is easy to transport actually. So it comes in a roll. So you can it acts as a net kind. So it is used for paving the roads. Even it can be used for making the crate wall, for a temporary kind of retaining structure. So there are many applications. Another important aspect, one of the important member of this geosynthetic family is geomembrane. So geomembrane is basically, you can say, is a thicker version of the polythene bag. So basically, they are same material, HDP, high density polyethylene, and they are impervious. So that is one of the purpose for it is used. So it is generally used to store liquid or waste in a manner that it doesn't allow the hazardous materials to percolate into the soil or in the environment. So basically the purpose is that. It is generally also used to store the storm waters in many European cities. So that because it can store a lot of water if you can lay it in a low-lying area. So this has a very important application from the geo-environmental. Right? It doesn't allow the hazardous material or the toxic material to percolate into the ground. So one of the many, and also it makes it is generally used in landfills or in this thing wastewater treatment in wastewater storage facility or this thing. I will give an example, good example. In one of my projects where we were drilling in for NTPC in Gambe Basin. So we had to store the drilling muck, which is mixed with some chemicals, which are very costly. So the chemical engineer had the process to extract the chemicals that are used for the drilling process, because a 3-kilometer drill is a long drill. It's a long process. So you need a lot of chemicals, bentonites, and mixed with a lot of chemicals. So those chemicals are very costly. So what they used to do, they dig a pit, very big pit like this. They used to store the muck into it, the wash out material into it, which had the chemical, and they have a separate pond just beside it, and in between that they had a processing unit. So they used to process the waste and get the chemical that they want to reuse. So this kind of practical, very useful material, one of the materials is this. Then we have geosynthetic clay liners. So geosynthetic clay liners is you can say it's a composite kind of thing. So it is geosynthetic is there, and there is a clay material also there. Like clay material means very low permeability of the order of maybe 10 to the power -7 or 6 or 8, something like this. So this is also used for mainly the geo-environmental aspects, landfill lining or lining for slopes and all those things where you don't want the water to percolate, or you don't want the leachates or the hazardous toxic waste to percolate into the ground. You will go for this kind of material. And there are different variants. There are different techniques to design this kind of geosynthetic clay liners, because you have to properly design it, that what type of liquid you want to store, or what type of particle size you are targeting, or what kind of material you want to stop the ingress into the soil. So depending on this, the clay liner is decided. Then there is another variation that is called the geofoams. So basically, geofoam is a big it's a variation of thermocol, you can say, simply. So these are also used mostly for where you want to reduce the weight on the structure, or you want to reduce the weight on a retaining wall from the backfill. So suppose you have a wall, you have a backfill which is exerting a lot of pressure on the wall. So you want to reduce the pressure. In those cases, people sometimes use this kind of geofoam to reduce the earth pressure. Another one of the important variation you can say is the geocell. So these have been in limelight for the last maybe 3-4 years, depending on this versatility and easy to use, and also for different applications. So geocell is kind of a 3D structure. Till now, whatever we are discussing, except geofoam, all are 2D structure, you can say, like the plane or sheet kind of thing. But this is a level up basically. So it's a 3-dimensional structure which provides the additional confinement to the material you want to reinforce. So it has a wide application in road construction, especially the base and the sub-base, where you want to reduce the thickness of the base layer, or you want to reduce the thickness of the sub-base layer. So you can use this kind of material which gives the additional confinement, and you can actually reduce the thickness. And also people are now building soil retaining structure out of this, because they're very easy to construct. You have big rolls of it, you just spread it, just pull it, so it will form a 3-dimensional structure, and you fill the in situ material with large gravels, like what photograph I have seen in the top, I've shown in the top. You can just fill it, and you can build a retaining wall instantaneously. And also another important application of this you can find in case of footing on loose ground, or you can say footing on soft soil, or very soil on with a very less bearing capacity. So you can replace that soil, or you can fill that soil into these geocell buckets, and you can build a much more better foundation soil to rest your foundation. So this has been very popular nowadays, and a lot of applications. Basically, this is 3D structure. And there comes the geocomposite, as I told you. It combines different elements of geosynthetics, like starting from either geotextile or geogrid or clay liner with something like geomembrane kind of thing. And there can be a different combinations. So this has been really popular nowadays, the geocomposites. Now I have been talking till now the different type of reinforcement techniques that people encounter, or people like. Now where to apply? Right. So because we are, I'm working in Uttarakhand, so it's a hilly state. Most of part is hilly state. Mahesh is working on Himachal Pradesh. It is also mostly hilly state. So we face a lot of slope instability problem, lot of landslide and all those things. So in these cases, this type of geosynthetics can be very useful. Starting from the protection of rainfall erosion, from construction of different type of infrastructure over this reinforced slope. So these kind of geosynthetic materials very useful. So I have given some of the photographs of slope failures, of, mostly threatening the connectivity, road network. And in some cases, major infrastructures are also involved, like what we have seen in the Rishi Ganga incident, like our hydroelectric, one of the construction hydroelectric power also was. So this kind of natural disaster can hamper any big infrastructure activities. So in one slide, I have tried to like sum up. Not everything is there, obviously. Most of the things are there. The remedial measures for unstable slope. Like first thing you can do is you can modify the geometry. That is the most common way people do. Like you reduce the slope, right? Or you give a burn, or sorry, or you can give a grading. You have a gentle slope, then you have a bench, then a gentle slope. Like this, you can grade. So it also sometimes affects, or it also sometimes helps actually. Or you can give some retaining structure. It can be gravity retaining walls. It can be gabion walls. You can be reinforced retaining earth retaining structure. It can cantilever. In different forms people provide. Drainage, and I've already told you, the drainage is one of them. Like you should provide the surface drain, and also the most important sub-horizontal and sub-vertical drains. Sorry, not borehole, drains. It's actually drains. So it collects all the water that has been coming from the upslope to the. It should not get inside, right? Basically, the concept is that goes like. Then internal slope reinforcement element, like what I have been discussing, like either bolting we can do depending on the strata. Nailing and bolting, I would say they depending on the type of surface we decide. If it is a kind of a not that rocky surface, so you can simply go for nailing driven nails or routed nails. And if it is a rocky strata, or you can say the jointed rocks are there, like one of the planar failure may occur or wedge failure may occur, so you can go for simple rock bolting. Anchors, where you have a larger forces are coming on the slope, so you can go for a large stepped anchors, which are of very deep, like 15 meters, 20 meters, maybe more. And vegetation plantation. That is basically for both the purposes. Like from the it protects the slope from the surface erosion also, and it gives a very pleasant appearance. I will show you in the subsequent slide how good it looks actually when you vegetate it. Now, reinforced soil retaining structure is one of the most you can say used nowadays, the retaining structures. So this gives a pictorial view kind of thing, and the right one photograph shows the actual field photograph, not taken by me, taken from the internet basically. So here there are many 2-3 elements are very critical. First is the reinforcement itself, like you all know that without reinforcement there is no reinforced retaining structure. There should be drains, like horizontal drains, vertical drains, all those things. There should be proper drainage aggregate just after the facing. Facing is also important because it gives a appearance, like psychological point of view, it's a good appearance that it is stable. So there are different facing elements. I will discuss in the subsequent slide. Then on the top soil, you provide some erosion protection so that your wall is complete. So why to go for reinforced earth retaining structures? So because we have been building concrete walls or gravity walls or masonry walls or random rubble RRB walls over the maybe for 150 years or so, or even more, 200 years or something. So why we need this kind of wall? Why? So there can be different opinions. So I have listed some of the opinions that I found is actually really helpful. So one of the things is that if you are using reinforcement for reinforced retaining walls like RC walls, so the chance of corrosion involved. So over the time it has a design life. So if corrosion happens, the design life gets affected, and you end up with a distress. Then the economic thing, like you have to import much of the material for building RC walls and all stuff. So, but in here you can use very indigenous material, like you can use the cut slope material itself. So, and it has more deformability basically because it can accommodate large deformation as compared to the actual RC walls like reinforced concrete wall. So it is very prone to it will break, like it's actually brittle material, and very unskilled labor can do basically with minimum super risk. It has a good drainage property because you are building the wall with poisonless soil basically. So it automatically have a good draining element. Minimal excavation is needed and heavy equipment is also not necessary. So this slide gives you an idea about how this reinforced soil retaining structures have evolved over the years. Like initially, the classical gravity retaining wall we used to build like with random double masonry or brick masonry or concrete even. These are big thicker section, like because the gravity is retaining the field, right? So it need a bigger section, bigger foundation, lot of manpower involved, lot of material involved. So then it got slim. It got slim, and it got slim with the help of reinforced. Simply. So the reinforcement element have been introduced. So it now end up in a reinforced RC walls. Then again it got lesser in thickness. We have a buttress or counterfort walls. Then it further improved. People started building prefabricated. Like have elements, you join it and you fill the soil. Also, it's also what? So prefabricated. Then the currently most used or we can say the reinforced retaining structure that I will be discussing subsequently. So this photograph I have already discussed with you that you have different elements involved starting from drainage, reinforcement, you have surcharge loading, facial element, you have a leveling pad. This kind of wall you will find in highways. Like in highways, if there is a overpass or if it's a flyover, the approach road is generally built with this kind of techniques. So this is the typical cross section. These are the different elements. I told you that the foundation soil should be well compacted. Then the reinforced soil, this should be mostly preferred to go for a cohesionless soil. The cohesive soil is not generally encouraged until unless it is very much costly to transport it from elsewhere. So generally we go for cohesionless soil. Then we have a backfill soil. Whatever we want to retain, we want to retain. Then there are reinforcement elements like geogrid, polyester strip, geosextant, different combination I told you. Again, the same thing. Here I have shown you with a this thing with the drainage, blanket drainage also. Sometimes what happens now? Sometimes suppose we want to expand the existing natural slope to make a space, right? So in that case, what do we do? Apart from the existing slope, we provide a drainage so that whatever runoff or this thing is coming, it should not go into the reinforced soil retaining structure. So we provide a blanket drain kind of. This kind of thing has been provided in Pakyong Airport. It has been started operation. We have been working over there for the last maybe 5-6 years, like monitoring of reinforced soil retaining structure in Pakyong, Sikkim. So they have provided this kind of drain, like blanket drain. They have a vertically going blanket drain just below the airstream. So it goes all along, it takes all the water from the hills and drains it in the downstreams. So this kind of things, if you are building or taking care of the water properly, this kind of things will work excellently. It's magic. So now, apart from the reinforcement element and the material involved and the drainage involved, fascia is another. It also adds on the cost of PSA. It has several options, variety of options that can be a wrap around. So suppose you are building on a not so good kind of a soil or air capacity not much, so you cannot put a lot of weight over it. Right? So in those cases, we generally go for wrap around. Then there are segmental precast concrete panels wall. These are the mostly used the reinforced soil retaining facing element nowadays, because all the reinforcement, all these flyovers in Delhi, Haryana, in all the areas, they are mostly built with this technique, the segmental precast concrete. They are precast, they will take it from the factory and put it, and also layer reinforcement and build up. Then sometimes full height concrete panels are also there. Modular blocks are coming up nowadays. You see there is small this size of different shape of concrete modular blocks are also casted in the side and they are placed. Gabion is mostly seen in the hills basically, because there you cannot cast so many concrete panels or take these so many concrete panels. It becomes costly. So you go for Gabion. So Gabion basically the crates are made of your choice, generally 1.2 meter by 1.2 meter or 1 meter by 1 meter, 1 meter cube basically, and then they fill it with large size boulder and things, and they make a wall. Timbers are generally not used. Then welded wire mesh walls are also there. Gunny bag, if you have a budget constraint, or suppose nothing is available, so you can use gunny bag also, fill gunny bag also. Bricks are sometimes also used, but not generally preferred. So I will say the concrete panel, the full height concrete panel wall, gabion wall, and then modular. These are the mostly used facilities. So this gives you idea about the wraparound walls. Like basically, I told you that if you don't have a good foundation style, so you can build the wall with geotextile and geogrid. See, this becomes a geocomposite. What I was telling, either non-woven or woven, depending on the requirement. Actually, you can combine this geotextile with geogrid and make a wraparound. Then segmental wall. Segmental wall, I told you that precast panels are there. All the this approach road in Delhi NCR, this kind of wall. So basically, you have a high HDP geogrid just backside of it, and then the concrete fascia panel of very less thickness, like maybe 1 feet or so. So not even sometimes not even 1 feet also. So this kind of thickness can be used generally for fascia. So aesthetic appearance. So this right side photograph shows a geogrid basically loaded in uniaxial direction, only one direction. Then there are full height panel concrete walls, but these are generally not preferred because these are difficult to construct. That full height we have to cast and then we have to reinforce it. So it becomes a little bit heavy. Then though the thickness of the wall reduces significantly, you can say from the gravity wall it becomes like 1/10 of something, like 1/8 or 1/10. So you can imagine the reduction in the thickness, very marginal thickness of the given. Then sometimes you go for the modular concrete, like you precast this element and you construct the wall, the site itself. Then you have this gabion walls also. So the gabion walls, I told you that there are reinforcement elements are there, and you have a gabion face. Basically, as a gabion are used as a facing element. So you use the local material and construct the gabion boxes. The site is that can be of mild steel wire mesh or polymer geogrids. That I told you, the geonets, they are also used in the gabion walls. Even sometimes large size pocket geocells are also now being used. Now, sorry. So this timber facing, then you have the brick wall facing and gunny. So I've already discussed all this. Now, this will give you overall idea that what type of materials are involved, what actually design philosophy, what should be taken care of, like drainage and material important, what type of geosynthetic use. Now, how do you design this kind of structures? Like how? What is the design philosophy? Design methodologies are there? So basically, the design philosophy goes like this. So basically, we look into the two aspects, like internal stability and the external stability. So internal stability means that it deals with the failure of the reinforcement element itself. Like suppose you have a geogrid, so the if suppose there slip surface or failure surface goes like this, so how this reinforcement element like geogrid or whatever reinforcement element using is going to stop. That calls the internal failure. In tutorial I will explain. Then we have an external mode. Like external mode means suppose you build a reinforced soil structure, but your active thrust from the backfill side or from the hill side is so much that the whole reinforced zone is displaced or rotated or partially failed. So that we call as the external mode or the external stability. And there are different methods available, starting from the working stress method, the limit equilibrium analysis, and deformation evaluation. Basically, these two of these methods are generally used. Like limit equilibrium analysis, this is a force-based method. Like we try to equilibrate or we try to compute the unbalanced force and what are the forces required to balance in terms of reinforcement. And deformation evaluation is that to design the wall basically with certain reinforcement, and we use a numerical method, either finite element or finite difference or in some other method also, whatever numerical method is. But so we try to evaluate that whether our displacement of the facial element or the reinforced soil structure are marginal or within our permissible limits or not, or within the serviceable limits or not. That has to be evaluated. So basically there is a force-based concept, there is a displacement-based concept. Displacement-based concept requires numerical solutions like finite element, finite difference. FLAC can do, Laxis can do. There are a bunch of softwares are available. Limit equilibrium method, we need to use solved equations, like closed form equations. So that can be solved using Excel or MATLAB or any other programming language, Python, C, whatever you name it. So that is a force-based method. So we try to equilibrate the force and we try to estimate or try to calculate the amount of reinforcement required to stabilize that slope. This deals with whatever I have been telling you last slide, that what are the difference between the methods and which one is prevailing. So I will suggest the limit equilibrium method is mostly prevailing because it is very easy to use. The closed form equations are always easy to use, right? It doesn't require much prior knowledge or not any input parameters and all that stuff. Very simple procedure. And the Federal Highway Administration, that the code FHWA code 2002 and then subsequent 2006 also, they promote this force-based method, both internal, external, and all those things. So people generally in India go for FHWA-based design, and deformation evaluation are also done, but mostly in the research domain, suggest, because it requires a lot of knowledge about the deformation-based methods like finite limits or finite difference method. Then it requires a large number of input data, input parameters, like what is the reinforcement stiffness, E model, the soil different parameter for the constitutive model, and all those stuff. But sometimes this helps because sometimes in more detail we want, or sometimes where the problem is too complicated to solve using simple force-based method. So in those cases, we generally go for deformation. Now the internal stability. So basically the internal stability we can divide or categorize into two aspects. Like one is the tensile failure, other one is the pull-out failure. So this basically a force-based method. I told you that I will be discussing mostly on the force-based method. So in force-based method, what happens that we try to identify the critical slip surface, or what could be the critical slip surface within the reinforced zone. Suppose this is a reinforced zone, what could be the reinforced failure surface, critical failure surface in the reinforced zone. And what the maximum tensile force is required to arrest this. Because what happens, there is a failure, the failure is arrested by the reinforcement. Right? Suppose there is a slip surface, it is arrested by the reinforcement. And how does it arrest? It arrests by creating a tension between the soil and the reinforcement interface. So that with the tensile force of this reinforcement, we prevent the failure. So the tensile force has to be evaluated, right? That is our main objective, so that is our main unknown. And the tensile force calculated by this is generally taken care of this aspect. Like it should not break. The reinforcement should not break. Should be able to take the tension, right? And another aspect is the pull-out failure. Now, what does the pull-out failure mean? Pull-out failure means suppose the reinforcement we have embedded into some stable zone, right? There is a unstable, there is a stable zone. So the reinforcement in the stable zone should be such long that it doesn't, when failure takes place, it doesn't come up or pull out, right? So it should be able to resist that pull out force. So that also is very nice. So from that we generally determine what is the anchorage length or what is the extra length we need to provide beyond the critical section. So that is calculated for the pull out failure. So basically in internal we have two modes. One is tensile failure and one is pull out. Now this gives you an idea of flowchart of the whole problem, how to proceed. First of all, you need to select the reinforcement type, whether it is to say extensible or inextensible. Extensible means what I have been talking about, like geosynthetic, geogrid, geotextile, all those stuff. Inextensible because they are extensible because they are plastic material basically, so they can go elongate or they can take large difference. Inextensible means metal reinforcement, like metal strips, then brittle materials like fiber reinforced something is coming up. So all those inextensible are sometimes used. So you have to decide the type of reinforcement. Then you have to critically select the location of the slip surface, failure surface, depending on the methodology. Then what is the reinforcement spacing you want to give? Like generally more than 0.5 you cannot prefer, something between 0.25, 0.3 something. Then you need to calculate the maximum tensile force in the each reinforcement layer or each reinforcement level. That is also very critical. So that has two components, static or dynamic. So if you are designing a reinforced oil retaining structure for plain region or not so seismically active region, you can go for simple static based design. So you don't consider that. When we want to go for a seismically active area, so you should consider the dynamic forces to the calculation, because if the one fails, the supporting structure, supporting infrastructure fails, right? So you need to take care of the dynamic forces also. Then the maximum tensile force that will, then the pull-out capacity that I was telling. Suppose you have a reinforcement embedded, right? It should not come up. When failure takes place, it does not come up. We always try that should be breaking, not pull out. So we make sure that it doesn't break and doesn't. Then how do you do it? Because some of you maybe from the geotech background also. So this section can be of your much interest basically. But how analytically can evaluate the internal stability? So there can be two different concepts like that have been given in literature. One can be deterministic concept, another can be probabilistic. So first I will be focusing on the deterministic, not much about the probability, because then it goes into some different domain. So generally deterministic method is basically driven by the factor of safety, like what is the total force is coming basically for failure, and what is should be the reinforcement you can say force to arrest that failure. That's it, simple, very simple. Probabilistic I will not be telling much. So though you know that there is a method called probabilistic method where the variability of the soil material parameters are also considered. Now one of the simplest method of doing is that the limit equilibrium based method, and one of them is very prevailing nowadays, is the horizontal slice. Now we have all studied slope stability in our undergraduate. So in undergraduate what we used to do, suppose there is a slip surface like from the Bishop's method or Jan Goose method or Northwestern, whatever method you are using. See that the failure mass we used to divide it into vertical slices, right? Number of vertical slices and then calculate what are the interacting forces and stuff. Here, because the reinforcement elements are inserted already, and so in the left side picture, Now we are dividing the slices horizontally, not vertically. We are dividing the slices horizontally. That's why it is called the horizontal slice. A very simple formulation is proposed by the Sahagoli et al. In 2001. So this suppose generally the internal stability failure of this kind of reinforced soil retaining structure are log spiral same or non-linear is. Or sometimes people compare to circular also, arc of a circle or arc of a log spiral. So that's why a non-linear failure surface you can see here. And the right hand side shows all of the forces involved. You have a tensile force, the Tj, then you have a normal component from the stable zone, then you have a shear component, you have interslice forces, you have vertical forces, all these forces are involved, right? So here this gives an idea that what are the forces involved in the unknown. What is the unknown here? Unknown is the Tj, because we want to obtain what is the Tj. Tj is the reinforcement strength that we want or we are designing. Okay. So this gives you an idea about the analytical formulation. So a lot of equations are involved. So basically here the 2n plus 1 formulation is satisfy the horizontal equilibrium of vertical equilibrium of all the slices and the horizontal equilibrium of the whole failure wedge. These are the forces. What are the forces involved? And the unknown is the summation of Tj. Summation of Tj is the reinforcement force we will be designing, or the reinforcement force we want to calculate. So this is a very simple formulation, and based on this formulation you can simply calculate what is the summation of Tj. Now the problem, where is the problem? The problem it becomes critical when we are optimizing the critical slip surface. That becomes a problem. So generally trial and error search, sometimes people have used other evolutionary algorithm like nowadays machine learning has been very popular. So different optimization technique, constraint, unconstrained optimization techniques are also used to obtain the K value. And the critical slip surface will be with that one which gives the maximum K value. The K value should be max. So you have it becomes a optimization problem, constant optimization, not unconstrained optimization problem, or sometimes constant also, depending on the type of failure surface you are choosing. The K you need to calculate from the optimization. So we have developed or coded all these things. So now the methodology in the present study, we are comparing with some of the earlier researchers' work, where they also calculate K for the seismically active region. Right? The seismically active region, there are generally the procedure follows that we assume the seismic forces to be pseudostatic. Pseudostatic means the seismic force is considered to be acting from left to right to left, depending on the critical direction, generally away from the slope, not towards the slope, away from the slope, because it drives the field. Right? So the critical direction should be driving the field. The critical pseudostatic acceleration acts away from the slope, and thus have K value are assigned, maybe based on the IS code preference, or depending on the seismic regional seismicity, or from some other codes or judgment. So it can be given. So this gives an idea that if the seismic acceleration goes on increase, or the seismic acceleration coefficient Kh, which is the seismic acceleration coefficient, goes on increasing, the requirement for the tensile force increases. Like K is increasing, so it is a kind of a increasing order. So it understood that if you are designing a retaining wall in a seismically active region or seismically prone region, so you need to consider or you need to give a design for a higher K value or higher reinforcement than we provided. Now, from the researcher point of view, if somebody is working in this, want to work or working in this area, for those people, basically, suppose you have the pseudostatic method, which I have told you, it has many limitations because it doesn't consider the amplification of acceleration or the phase change behavior of acceleration, because acceleration is not this thing linear, right, or constant for the slope. It changes depending on the strata. So these kind of things have been missing from the literature. So people have been trying or developing methodologies to address this shortcut, like pseudostatic assumption, right? Pseudostatic assumption. So one of the alternative viable alternative, let's say that pseudodynamic methodology. The pseudodynamic methodology is basically improved pseudostatic version of this. What happens here? We are considering a vertically propagating wave, vertically propagating sinusoidal. So earthquake is assumed as a sinusoidal motion, and a frequency, input frequency has been given. The shear velocity of the medium has been incorporated into the formulation, and the depth of the field or the work is also considered. And depending on that, the wave propagation is post the acceleration is now becomes the function of depth and time, which it should be, but in a very approximate manner. Right? Actual earthquake, all these things doesn't happen. So we have something better than pseudostatic method. So the total seismic force you can calculate from the integration of these forces over the whole failure wedge. So that is obtained the what is the QH value, and it's a function of t because it's a harmonic motion, so it's a function of t. That's why the parenthesis, first parenthesis, we have a t, small t in it. But it has problems. It has many limitations. As you can see, this was earlier proposed by Zhang and Steedman almost 3 decades back, right? 30 years back. That time, this was the only, or you can say, one of the only most viable techniques apart from the pseudostatic technique. Then people started to pointing out their shortcoming, the shortcoming of this method. The shortcoming, one of the shortcomings is that major shortcoming is that doesn't satisfy the zero stress boundary condition at the ground surface. Okay, so it doesn't satisfy zero stress boundary condition means that the stress at the ground surface should be free because above it there is nothing, right? So it should be shear stress should be zero. But if you put this, you solve this equation and put z equals to 0 because z is coming 0 at the top of the wall. So if you put 0, then there is certainly a value for all the time. Maybe sometimes it becomes 0, but generally most of the time it is non-zero. So that is a very big, and people have pointed out several times that it actually is not 0. And earlier version of pseudodynamic method also only considered a linearly increasing amplification of acceleration or acceleration increase. So that is also not a very good option. So these are the one of the shortcomings or limitations of pseudodynamic method. It doesn't satisfy the boundary condition. The amplification is unbound. Like whatever amplification value you want to put, you'll put. But it is not the case. You know, it depends on soil parameters. Depends on the input frequency. There are many things. Also the height. So those things are not considered. Now, no consideration of energy dissipation because soil is a natural material. It has a dynamic characteristics or damping value or damping characteristics. When a wave tries to propagate, it tries to dampen it. Material damping is involved. Where is that? It is not considered. So address this limitation. In my PhD and subsequently, many people worked on it using this method. Beleja first introduced this method, then subsequently myself and many people have worked with it, that a modified version of pseudodynamics. So it considered the soil to be viscoelastic in nature, and viscoelastic means it has a elastic component and a viscous component. So elastic component is the first component. The tau is equals to gamma s into g. So that becomes a linear component because it is only depends on strain, shear strain. The second component is eta into delta upon delta y, del gamma s upon del t. So that is a rate of strain. Right? So that becomes a viscous component. That's why it is called a viscoelastic formation. So now we solve this equation and using assuming the soil medium to be a Kelvin-wide soil, and all these boundary conditions are satisfied because I told you the boundary condition is very important. Boundary condition satisfied. The interaction of the incident wave. So once a wave goes up in the medium and hit the free surface, then it comes back. Right. So there is a two waves interacting in a soil medium. So those interactions has to be considered. This method is considered that interaction. That's why it is much improved version of a pseudostatic. That is called a modified pseudodynamic. And but still there are limitations. Though we have addressed most of the limitations, but still it is harmonic, right? Which is not the case. But harmonics gives you a conservative result. In that way, you can say that okay, this method can work because it's a conservative risk, right? Now, suppose we want to assume analyze this kind of structure, then how do we analyze? So we analyze this with this some kind of this formulation. In this formulation, what we are trying to optimize or identify the critical failure surface, which is log spiral in nature here, shown in the dotted line. Right? Now, how do we optimize this failure surface? This failure surface can be optimized with these two simple angular quantities. Okay, so log spiral has certain features. So using those mathematical features, we can optimize this critical failure surface only by optimizing theta 1 and theta 2. These are two angular quantities, theta 1 and theta 2. So here this is the formulation, and the formulation goes like this. The initial radius is calculated from the height of the wall and based on the angular quantities, then subsequently it is solved. And we try to solve the whole wedge forces, and solving the horizontal and vertical equation, we try to calculate that what should be the reinforcement force that I already told you. What should be the K value. And how do we optimize it? We optimize it that the theta 1 and theta 2 should be in between these two. Sometimes these bounds changes depending on the methodology, but this becomes a constant optimization problem or bounded optimization problem. Now this was some of the typical results. Suppose we have 10 layers of geosynthetics of a height maybe 6 meter or 8 meter or 10 meter. So here I have used 5 meter wall and 15 degree inclination. So alpha is the inclination from the horizon. Vertical line. Okay. So it's a very stiff wall. 15 degree means very stiff wall. It becomes 0 degree, that means it's almost 30. Right? So stiff wall will require more reinforcement. Keep this in mind, it will require more reinforcement. And here from this methodology we can actually identify or calculate that in each layer what is the tensile reinforcement force required. The top should have a less value and the bottom should have a maximum, right? Because all the weight of the total field is acting on the bottom layers, right? So bottom layers should have a expected to have a larger reinforcement force. And then another typical observation from this methodology, you can say that K is equals to 0, that is pseudostatic case, or you can say static case, the failure surface is somewhat nonlinear. As the seismicity you are incorporating in pseudodynamic modified pseudodynamic framework, the seismic acceleration coefficient goes on increasing, the failure surface tries to become linear. The failure surface tries to become linear. This is one of the critical observations. Then we try to solve, because this was a part of my research work basically. So we try to compare the proposed methodology with the other available solution, right? That how the method stands, what is the reinforcement requirement is changing, how the reinforcement requirement is changing, which is with acceleration coefficient. So because the modified pseudodynamic method is more realistic and it also incorporates the damping of the soil and also the wave propagation interaction phenomena. Obviously, for a certain input parameters which is shown in this slide, the reinforcement force requirement is more as compared to other methods. Then, apart from the reinforcement force requirement, what is the K, we need to also have the length, right? In the design, final design, we need to give the designer or the constructor or the field engineer the K value, the tensile strength of the geosynthetic that which he should procure, and also the length of the geosynthetic, how much long we should put. The length also depends on the vertical seismic acceleration coefficient direction, you can say. So that depending on the direction, the requirement of the length also changes. The direction requirement is maximum when the vertical acceleration is acting downwards. But at the same time, the K or the reinforcement requirement, strength requirement is maximum when it is acting upward. So there is a trade-off between these two. So both the cases should be satisfied. The design should be like that. The length-wise it should not fail, and the strength-wise it should not fail. Right? So this gives you an idea that if we change the direction of the vertical acceleration force from the upward to downward, upward is positive, downward is negative, the failure surface, the shape of the failure surface or the zone of the failure surface, the failure zone in or the wedge shape of the wedge also changes, but it shifts. That is one of the you can say critical observation from this research work that what is the effect or direction of the seismic forces on the shape, on the strength and the length of the. So this is all about the you can say the internal stability part, like how much reinforcement force we require, okay, and how to calculate that, what are the methodology available, and how do you know that okay this our calculated values are correct or not. I have been discussing in details. After that we enter into the external stability, right? So in external stability, now this if you see here, sorry, I'm going back a little bit. The failure surface cuts all the reinforcement. That's why it is called the internal failure, right? Because it cuts all the reinforcement, and that's why how we are calculating the reinforcement force requirement, and the critical length should be more than, right? In external case, what will happen that because of the active thrust from the backfill or from the hill, the whole wall, the reinforced soil mass may slide or it may overturn, depending on the condition. If you build a slender wall, it will work, or it can slide also, or it can have both, like sliding and rotation simultaneously. So depending on the condition, actually, we see. Now, sliding about the base is another case, and overturning can be another case. So depending on case to case, we need to consider what is the factor of safety involved, how much reinforcement length we require. All those things have to be calculated very meticulously. Then sometimes I told you that some foundation soils are not that much strong or that much, you can say, load bearing capacity or bearing capacity is not that good. What happens that the foundation soil itself fails. Right? You can see from the left hand side photograph the third number of failure report where the foundation of the reinforced soil structure fails. Then you may have a global failure kind of thing, like whole this thing you can say a rotational kind of thing, the whole reinforced soil structure along with the backfill is rotating or fail. That is a global failure kind. These kind of observations are generally made or good from the numerical analysis. Now the same type of algorithm to follow, like according to FHWA, highway station. Then we define the wall geometry, that how much height of the wall we want, what should be the how much inclined slope is there behind the wall, all those stuff. Then the soil property, the material properties that is involved to construct the wall. Then the performance criteria or the factor of safety is to select. Then the preliminary sizing, that this would be the tentative size. Then on the static condition, evaluate what is the sliding, overturning, bearing capacity, and rotational. What should be the failure factor of safety are coming, whether that is within the your permissible limit or not. Then establish the reinforcement length, that this would be the reinforcement length, because now we have the external stability, we are considering the whole wall, so reinforcement length is obtained from there. Then the reinforcement stability may be changed. So both way can be done. Then analytical implementation, this is comparatively simpler than the internal one. So basically we have two patch wedge mechanism. The first wedge is the reinforced soil spur, and the second one is the backfill slope that is retained, what you want to retain. Right? So this the active thrust acting from the wedge B is shown in the PT, the P, capital P, parenthesis T. So that is acting on the reinforced soil, right, from the backfill. And we have a reinforced soil structure, and at the bottom we have a friction, because that is trying that the thrust is resisted by the whole structure. So all these forces MB, FR, P have to be calculated, and also the acceleration acting in the wall also need to be calculated. Weight of the wall also be calculated, and from that you find, satisfying the factor of safety in direct sliding or overturning or bearing capacity, what is the LDS. Here I am talking about the direct slide. Similarly, the rotation also you need to come. So this is how this is a formula that you calculate the P. The P is what? P is the active thrust on the backfill. Okay, so if a planar failure wedge in the backfield is considered and the PT is calculated, then we calculate the driving force, that FD, then NB is the reaction force. Then we compute depending on the what is the frictional coefficient between the geosynthetic and the base material. We calculate the force, and from that we can calculate what is the total resisting moment can be for the overturning, and also for the direct sliding we can calculate what should be the resisting force. Then overturning, so the about the toe or the point E, we generally calculate all the turning moments, and the resisting moment is only the weight. Okay, the WW is acting, so that weight depends on the length of the work, right? So the reinforcement length from the overturning point of view is also calculated. Similarly, when we make this formulation, we try to cross check with other similar analytical computation, similar analytical results. So here is the comparison. The present method and the pseudostatic is very comparable. Modified pseudodynamic is little bit on the higher side reinforcement requirement length, required reinforcement length, because obviously we are, when the seismicity increases, we see that there is amplification. So the total overall acceleration force increases. So you automatically have a larger requirement of reinforcement length. Then this shows you about the relation between the direct sliding reinforcement length and the you can say soil friction angle. So basically, if the phi value increases from this photograph, what we want to explain is that when the soil friction angle increases, the length of the reinforcement in direct sliding reduces. Now, why? What is the reason? Because if you have a high phi value, the cohesionless soil is much more, you can say that the total active thrust on the wall will be much lesser. So lesser thrust, that means capital P parenthesis T is less. So if it is less, then obviously the reinforcement requirement will be less from the moment point of view as well as from the direct sliding point of view. So we always want to ensure that the length of the reinforcement should be least, right? So we want to use a better quality cohesionless soil. Good quality cohesionless soil have a good phi value. If you properly compact it with proper this thing, roller compaction and everything with proper at proper maximum dry density with good quality, you can actually design the wall for a quite less value of this length of the direct sliding. Then, as we know that if the seismically active region we are designing, the seismic acceleration force increases, the length increases, right? And this shows in the failure surface in the direct sliding. Suppose this red line shows the static condition if KH equals to 0. So if the KH equals to 0, the failure surface involved or the failure wedge is very less, right? But as soon as the KH increases, the failure surface is shifting rightward. That means the length of the reinforcement is increasing. That is very good. And also with the inclination angle, everything changes. If you have a very stiff wall, a near vertical wall, obviously the length of the reinforcement will be much. Then the friction between because what is resisting in direct sliding is basically the friction between the soil and the geosynthesis, right? The base soil and the geosynthesis. So that can be increased if you have a better geosynthetic with a better CDS. That is the coefficient in direct slide. It is something similar to the friction angle, the friction coefficient mu value, solid mechanics problem. So if you have a higher value of CTS, obviously you need a lesser reinforcement length. Another important observation from the modified pseudodynamic method is that modified pseudodynamic method, this normalized frequency, that is omega is by Vs actually, that plays a critical. So here the height of the wall, the input frequency of the earthquake motion, and also the shear velocity of the medium is a interactive parameter, or a single parameter is governing the whole thing. So depending on that only, the length of the reinforcement requirement may be calculated. So this is one of the major novelty of my study, that how all these parameters affect the length of the reinforcement on the direct sliding been evaluated and proposed. Then this note the comparison of the length of the reinforcement required for direct sliding or turning. It is also very simple, like with friction angle increases, the requirement reduces. This is also similar kind of thing that if phi value goes on increasing, the length of the requirement overturning mode also reduces. Now, up to this, I have been talking too much about the methodology and all these things. Now, actually, when the problems we face or we go to field, how does it look like? See, this is one of the very good example. I should not say like this, but fortunately I'm saying this is one of the very good example that how you should not design the work. That I have been telling that how you should design. This photograph will show you that how you should not design. See, this has been so poorly constructed, poor material, poor manpower. Sorry, poor. I mean, say, can say poor design, poor workmanship, and after this is a segmental concrete panel retaining wall. Generally, found in the Delhi NCR this approach road or approach highway, this thing approach road. So here you can see that after the construction of the wall, it has gone under a huge amount of deformation. You can see that there is large deformation and bulging of the wall starting from the mid height, right? And there is just beside that there is a window. So now think about this resident, how much threatened he should have been feeling. Right? This wall can go off at any time, right? So this wall is supporting a portion of a airstrip in Uttarkashi. Can you imagine? That airstrip is, though it is not functional at this point of time, though it is supporting an infrastructure, very important infrastructure, this airstrip. So this kind of these things would not be there. So for that, arresting this more deformation, they have built a frame, like steel frame kind of thing with I section, heavier ISMB section, just to arrest the deformation. But this is not the practice. So how do you rectify it? So we suggested that you again, because these are very easily dismantlable, because this is a reinforced modular block kind of thing only. So you reduce the you excavate from the back, and you reduce the height of the wall by removing the facial element, and you reconstruct it with proper compaction and facial element. Or you can build a permanent concrete retaining wall. I will prefer that because there is a resident, right? So this kind of problem we generally encounter. And when after there is a problem, people will come to us that sir is for ठीक करना. So this should not be the way. This should not be the practice. You know. Then I told you that how beautiful a reinforced retaining structure can look like. The last photo. This photograph was clicked by me. This is in Sikkim. This is the hillock kind of a thing that you are seeing in green color. It is not hillock. It is actually a reinforced gabion face reinforced soil retaining structure. And its height is almost, you can say, approximately 40 meters or 50 meters kind of thing. So very large, very high. So it looks like hill because over the year after rain, the vegetation has grown and it appears so beautiful. So you see, if you construct with a proper design, proper material, proper compaction, proper drainage, this kind of thing, this is the appearance of this successful case history. Yes, in some turning corners, there have been problem because the height of the wall in this turning corner are of the order of 78 to 80 meters. That is extremely large, extremely high. So with some this thing, seepage and all those things, or the drain water, this additional hydrostatic pressure is applied. Because of that, there have been little bit problem. So this is another thing that the turning corners, like suppose, because what we are doing, we are assuming this is a 3D structure, a 2D structure, right, on our paper, with the help of the assumption of plane strain condition. So because this is extremely long, so we can assume it's a plane strain. But when there is a turning corner or a bend is there, because this road is not always, or the wall is not always straight. Some corners should maybe there. So in corners, the reinforcement requirement changes. The reinforcement layout changes. So how do you encourage? This is the one that currently the research topics. People are focusing now more on the 3D corners or 3D reinforced solid structures. This is from the researcher who want to work.
Vijay, namaskar.
Then Mahesh, am I exceeding or I have 10 minutes? Okay, I think Mahesh is busy somewhere. Then another topic that I will be talking a little bit. Basically, till now we have been discussing about the reinforced solid training structure. So that can be used. Suppose you are building a new wall or reinforcing a slope. Those conditions this can be useful. But suppose you have an existing slope and there are some failures are there, and you want to arrest that failure immediately. In these conditions, the nailing technique can be very useful. Okay. The nailing technique can be really sorry, excuse me. The nailing technique can be very useful. So basically, nailing are generally was actually involved long back for the tunneling purpose in the new Australian tunneling method, where the railroads are constructed, and it was found that if just simply stitch it, like this is a stitching kind of thing, stitching of unstable portion with the stable portion, right? So this, and then we cover it is shotcrete. So this is one of the very old example, you can say, of the initiation. So there are mainly the steps involved. So basically, it is a top-down approach. So we excavate, we nail it, then we again go down, we excavate, nail it, then go down. So this is a top-down approach, and it's very cheap, basically, very easy to construct and very easy to execute, basically, with least manpower and least intervention or least disturbance to the slope. The favorable condition, I have listed the favorable and unfavorable condition. Favorable condition is that if you have a stiff to hard, fine grained soil, very close to most dense soil, sometimes weather, rock, or in weak plains or gaseous soil. Unstable is that if it is not a good, poorly graded question, the soil, if there's a groundwater table is very high, it is very difficult to operate. And if it is a cobble or boulder starter, so your nail may hit a boulder or big boulder or cobble, it can get damaged or it can divert. The purpose is not so. And also very soft soil or organic does. So it has some limitation, it has some benefits. Depending on your problem and your cost involved, can actually go for sometimes. So basically there are many components are involved here. The reinforcement element, actual nail, then the felicine element is there, the top plate is there, fascia plate is there, and then the shotcrete, the temporary liner. So these are some of the photographs. Not suited for a large underground seepage. When there is seepage problem is there, then it becomes difficult because you constantly want dewatering so that the construction work doesn't get hampered. Then this shows a typical cross section of a nail distinction. So this is not a drilling nail. This is a routed. Sometimes driven nail. The basic difference between driven nail and routed nail is that the construction procedure. Driven nail, by what you can understand, it will be just this, you can say, hammered into the unstable slope, so that the unstable slope is stable, is stiff to the stable part. So just hammering, you can say, by pneumatic hammer or hydraulic hammer, whatever is available. And there can be grouted nails. The grouted nail means you dig a big hole into the portion on the slope, digging through the unstable portion till some depth in the stable portion. To insert the nail, give a space between the hole and the nail, and you fill the space with annular space with the grout. So you have a grouted nail. So that grouted nail can be tightened at the top with the help this thing, top plate. Sometimes they are precast also, the pre-stressed also, depending on the tensile force requirement. Then final cover of the concrete is also provided, depending on the requirement or the aesthetic also. So it is like tender grout, then corrosion protection also needed. The fascial element, it's shotcrete, some horizontal bar, welded bar, vertical bearing, other components can. So other components are basically connection components are very important, and the drainage. So I told you, drainage is most important thing, right? This kind of thing. Then there are threaded solid parts are also there with normal tensile strength, nominal tensile strength are needed, because generally these steels are very high tensile strength. Yeah. This was some of the photograph of bolted nail, this thing nail slope with the facial arrangement. This was the testing of the grout. These are some of the ASTM and FHWA standard I have been mentioning. So if you are using, you should follow these kind of things. What should be the minimum spacing? What should be the minimum grout strain? Generally, grout are tested in small cubes, like this small cube, 10 centimeter by centimeter cube, because grout strength is very important. Because you see, suppose this is a nail, this is the annular face of grout. So nail is there, grout is there. So basically, failure occurs between the interface between the grout and the soil. So grout strength, the grout shear strength, all these things are very important. So that should be taken care. Sometimes what happens, these bars, these reinforcement bars are generally of mild steel or steel. So those get corroded. Over the time, those get corroded. This problem was not there in the geosynthetic. Right? So they are not non-biodegradable, non-corroded material. So these are big because here this is the metallic reinforcement. So there is a high chance of collapse. So now people are coming up with coated bars like epoxy coated bars, some anti-corrosive coated bars. Sometimes people come up with glass fiber bars which doesn't corrode because it's made of glass fiber material, composite material. So there are a number of options are now coming up. But again, you see, suppose you have an anti-corrosive coating on it, but it gets damaged at the time of installation. It may happen. So in those conditions, this kind of things fails. Then this was the after finishing, the drains have been provided. Then this is the construction sequence. First, because I told you this is a top-down approach. You excavate, drill the nail, install the grout, install the strip pipe of the drains, and put the initial circuit facing, then custom the subsequent level. After you reach the required height, place the final facing. This was the excavation steps in pictorially, very beautifully explained. We have a cut, then you install do the grouting, put the nail, do the drilling, put the nail, do the grouting, then place the final initial this thing, then lay the drain, strip them, and then put the final finish. And in steps we do. So, like first 1, 2, 3, drop down approach, and this left right hand side shows you the final finish. This thing. So generally, it has been observed nowadays in most of the construction projects, especially in metros and this underground passes, where they are using extensively this kind of nailing techniques. And the tensile reinforcement, yes, it is to be designed, but generally these are very high strength material. So with nominal reinforcement strength only we generally go. But the extent of the failure surface is to be just correct. Because the reinforcement should be beyond your unstable zone. Otherwise, the whole unstable zone will come up with the nail. So overall stability is sometimes also important, like instrumental stability, general global stability, and global stability of the whole this nail slope are also. So the nail pull-out is another issue because sometimes what happens that may not fail in tensor because it has a very high tensile strength, but it may fail in pull-out. So pull-out length should be sufficient. Pull-out length should be sufficient, or the embedment length should be sufficient. But this gives you an idea. Like suppose it should be beyond the critical slip side. Internal, the left-hand side shows that the reinforcement is way beyond the critical slip size, right? And the pull-out resistance is achieved, or the pull-out resistance is sufficient. Sometimes general global stability, the failure surface is such a deep that the nail doesn't reach, or it doesn't go beyond this failure surface. So then the purpose is not solved. And also sometimes global stability, so that how the overall this nail slope is behaving. Then there are two limit states: the general geotechnical limit state, there are structural limit state. Geotechnical state means that the sliding occurs, or the nail breaks down. Okay, then then the nail fails, or pull out happens. Nail pull out. The geotechnical and structurally, nail may fail, fascia may get deformed, largely deformed, all those things. And also sometimes the punching shear failure happens on the this thing, fascia element. Sometimes head get damaged, it starts. So these are some of the overall. This will give you an overall idea about the nailing techniques and what should be taken care of, and how this nailing can be useful, what under what condition. I told you in what condition you should not go for. If you are encountering a bouldery strata or a river deposit material involved, so in those cases this kind of thing really do not. But if you have a weathered rock kind of thing or very steep soil, recurrent slope failure, that in those conditions, then can be these solutions can be very. And for the condition where you are building a new reinforced soil slope, you can go for reinforcement technique using geosynthetic that I have told. So with this, I think I came to the last slide. So basically, I hope you have got a glimpse of what actually happening in this area, what are the problems involved, and how actually a nail slope should be designed, or geosynthetic reinforced wall should be designed, under which condition it is applicable, under which condition it is non-workable, the solution is not feasible. All these things. So with this, I think I'm done. Not 25 minutes, maybe 26 minutes. I think I'm done. Over to you, Mahesh.
Yeah. Thank you very much, sir, for making us learn about soil reinforcement and telling about how these reinforcements actually work mathematically, what are the forces and how the forces act. So that's a fundamental science. So dear participants, you can ask questions from our speaker if you have any question. You can also raise your hand in this Zoom so that we can unmute you.
Or you can just Google my name. Also, you will find related papers. You can mail me.
Right. Right. So I also wanted to tell everyone that Dr. Anindya Pine has published some of very prestigious papers. So you can always refer to his Google Scholar ID also. He has done some wonderful work in the area of computational geomechanics, basically. So if you have any query you want to ask here, you can definitely ask here. Otherwise, you can always get back to him through his email and contact numbers. Both are available on the CSIR CBRI website. Otherwise, if that also don't work, then you can always get connected to me. I can definitely make you get connected to Dr. Pine.
Yes.
So, sir, because I think today we had all Dipankar sir students. Ashutosh was there. Yeah. Uday was, but all were discussing about landslides and some of the fundamental things that we are discussing since yesterday. So, because I'm taking point of view all the experts, we were discussing today also because in state like Himachal, the number of landslides that used to take place have increased exponentially this year in comparison to the previous years. And the major reason for that is human intervention, and because of construction activities that are going on due to widening of roads. There are a large number of projects by NHAI that are because of which it is going on. So we were discussing the way we prepared detailed project report before inception of any big project, right? So why not to prepare a DPR that if this project is takes place actually in the field, then how much slopes and how much our landscape is going to get affected, and what will be its implications in terms of cost, in terms of human lives, and how we can quantify it, because that is also a cost, right?
Exactly.
So
That's
so
a,
I
that's a
think that
very,
is also
very huge loss actually.
right, sir. Right, sir. And environmental cost is there. So because we are spending lot of crore of rupees every year to stabilize those landslides, and finally we all know that the best solution for landslide is to bypass it, just to prevent it, or just bypass your road to construct road from some another thing, another path, take another path. So I think that was one of the thing, because lot of money is being spent every year, and we are not able to finally mitigate, provide a sustainable, efficient mitigation measure for a longer duration time. It's a very difficult process. So I think I just also wanted to take your point of view regarding coming up with this sort of DPR that can be made before any construction activity takes place, especially in the Himalayan regions. Thank you.
Very nicely put question, Mahesh. Actually, we have been also discussing in person also for this thing last year. Actually, we are doing a lot of landslide research, but actually it is not helping. Truly speaking, even whatever we are doing, it is not helping much, because you see, landslides are occurring. In some cases, they are actually unavoidable, or you can say uncontrollable. So much mass is involved, so much big landslide is happening, so much material is involved. It is no remedial measure will be sufficient, I would say. So best way is that until unless we have a holistic this thing approach, like taking into consideration of the geology, hydrogeology, like how the water is playing role. Because as we all know, they see in December, January, don't see much landslide. Why? Because there is not much rain. So in monsoon season, so much of water is there, and if you are constructing without taking care or without respecting the water, you are going to land in a deep trouble. So that's one of the most critical thing, I should say. We should be taking care. We should be taking care of the water. If you are draining it properly, okay, if you are giving it proper slope or proper maintaining a proper trace, I don't think it is a much of a problem. Like in certain areas, yes, definitely, you cannot help it. Simply cannot help it. Or what you said that either you you make a tunnel, or you bypass it with some other hills, so that it doesn't happen, or when it happens, it doesn't bother us. Doesn't fall in our part. So I think holistic approach is missing, and another important thing is that. The agencies involved in this activity should take all these things from the DPR stage that we have told. From the DPR stage itself, I think we should be taking care of how we are going to divert the water. Okay, how we are going to divert the water. What remedial measures are applicable? What is the cost-benefit analysis? All those things should be. Without that, it becomes a futile exercise. Or then again, we spend crores of money to fix it. So that should be taken care.
Absolutely, sir. Absolutely. So thank you very much.
Thank
you very much, sir, for
I think we are in time only. We are in time.
Yeah, you are always in time.
Here, then even also we are in time, because 1.5 hour lecture is too much. I mean, it's exhausting.
Too much. Yeah, but
and also for the participant at the end. That's why the main part I have kept in the front, only pictorially, and for the discussion part I have keep it in the second phase, because people get tired.
Right, sir. Right. I think that's one of the suggestions that we can give to AICTE, because it has been proposed by them to have 2-hour session, and it's very long. So next time, definitely you have to be in person in the beautiful hills of Shimla. So I think it won't be 2 hours then. So we'll keep it. They will keep a break in between, and I think we'll try to make it better.
Sure.
Right. Okay. Thank you very much, sir. Okay. Thank you, Dr. Anande Pine, for taking out time. Thank you, sir. Thank you.
Thank you. Thank you for
Okay, sir. Thank you.
Thank you for inviting. Next time we'll see you in Simla.
Sure. Thank you, sir. Thank you. Okay, sir. Okay. So, dear participants,
I can leave.
You may leave, please. Thank you.
Thank you.
Okay. So, dear participants, with these words, we come to an end of the second day of our faculty development program on disaster resilient infrastructure. I have already shared the link of feedback form with all of you. And what I can also do, I will also put it in the WhatsApp group also. So the two things that I keep on reminding all of you, the first thing is that you must have at least 80% attendance. And the second thing is you have to score at least 60% of marks. So that's not from my side. That comes from AICTE, which gives you certificates for this program. So thank you very much. Thank you very much for your kind attention and being there throughout the day. Apologies if there was some sort of a glitch or a delay or any noise, unwanted noise that might have interrupted you in between. So we'll meet tomorrow at 10:30 a.m. You all are requested to join by 10:20 a.m. tomorrow so that everything remains good and goes smoothly. Thank you very much, sir and madam. So what you can do, you can